speaker, the NICER project scientist, Paul Rosen, who is, no, we actually gone back.
We're keeping the order.
We're keeping the order. Okay, so there was been a bit of a back and forth. Apologies. Okay, so it's Arash, the first presentation, the algorithm lead for NICER. So yes. Thank you. So Arash will give an overview of the NICER products and algorithms that have been implemented in the past few years.
All right. Good morning. So I'm going to talk about the current status of the products, and as you guys all know, we have been going through commissioning phase and Calval phase, so hope to give you a feel where we are by now. I'm representing a big team behind the scene that have been working hard during commissioning and Calval, and their names are on the slide. This is a backscatter map, produced a mosaic using our level 2 geocoded covariance products, all produced automatically with the science data system. So this should be an evidence for the instrument is working, it's stable, the science data system is working. The data here were not fully calibrated, but you see that still backscatter is very homogeneous, no big jumps from tracks to tracks or along track. Overall makes sense. This is all good news for products that were not fully calibrated. You may notice some green dots and also some stripes. So that's, yes, that is RFI, radio frequency interference. I will get to it. We have to deal with it. We are operating an L-band radar. How the products look like? Well, they are very well focused. One of the most important characteristics of the instrument is that we are gaining our white swath with a technique called SweepSAR. I'm not going to go to the details, but we have 12 beams. We are combining those beams on board, 3-tap beamforming. So it is very important to make sure that when we are operating in a DDIRT PRF mode, where PRF is changing along the track, to not have any gaps if the focusing is working. And this is evidence that, yes, the data is focused very well. I'm showing it over Oklahoma corner reflectors, that the point targets are very well focused. The ISLR, PSLR, all are satisfactory. Of course, if we go along to the polar regions, there is more difficulty there. The azimuth focusing, sometimes we see defocusing because of the significant ionosphere variation. But overall, this should represent most of the globe, that the data is very well focused and ready to use. The geometry calibration was one of the items that we got into very early in the mission. We worked with the instrument team, nailed down the system delays, electronic delays, around 2 microseconds was there. Once we account for that, and then look at corner reflectors, we calibrated for an average bias. After that, if we look at the time series of the geolocation error in range and in azimuth, at the top I'm showing you the solid line is the geolocation error. The solid block line is the geolocation error in range direction at the top plot over corner reflectors in Oklahoma. This is updated up to a week ago. And if we go ahead and predict the delay from the independent ionospheric tech data from the GPS, you see that they do correlate almost 100%. So basically, the geolocation error, as expected, is dominated by the ionosphere. If we take out the ionosphere, you get to a geolocation error around an average of 20 centimeters for L-band. It's actually magical. So we are very happy with the geolocation. Overall, seems to be very nicely done, the calibration here. The azimuth is stable. There is one outlier there. We are looking into it. Otherwise, it's very good geolocation. Another activity has been to make sure that we are calibrating the radiometry. After the absolute calibrations over corner reflectors, we have to take care of the relative radiometry calibration, and the results are here for this case over homogeneous targets, we expect the backscatter to be flat. That is not the case before the calibration, which is on the left side, and then after calibrations, taking out the antenna pattern, again, we have 12 beams, taking care of those 12 beams and how they are combined and all that, you see that the backscatter is flat over Amazon homogeneous targets. And if you look at the profile in range, you see that there were variations of around 1 to 2 dBs, but after calibration, we are getting to a variation on average within a quarter dB. So that's pretty good. So by now, I think overall we are happy with the radiometric calibration, but this can be always improved further, and indeed we already have some improvements. Whether it makes it to the release or not, that's a different story. The noise equivalent backscatter, we have very comprehensive products, and whatever I'm plotting here is actually coming with the product. So a few months ago, we looked at the noise equivalent sigma naught for a sample of the products. Actually, it's the same sample that we released to the public. In this plot, you see that overall, the noise equivalent sigma 0 is pretty good. It's better than our requirement, around 23 dB, minus 23 dB was the requirement, but you see that we are way below for 20 and 40 megahertz. For 77 megahertz, there was a misconfiguration of operation, and that has been identified. We have already worked with the instrument team that has been fixed, and we have looked at the test data. The 77 megahertz also is coming 3-4 dBs better. So overall, noise equivalent sigma 0 is pretty good for this mission. What are you guys gonna get? Well, for imagery, you are gonna get the regular range Doppler SLCs in different modes. You get, we are posting everything to 5 meters in azimuth for RSLC, and for range direction, it depends on your bandwidth. And then we are geocoding those products, geocoded SLC, so those are global. As the data come, they get produced and provided to you all. And the next product is the geocoded covariance. So that's where basically we do a little bit multi-looking. We do radiometric terrain correction, and then after that, you see that the targets features are showing up here. I'm showing RGB. R here is HH. G is green is HV, and blue is HH again. So whatever is green here is dominated by HV, so that's vegetation. Whatever is very bright, that's the urban. Whatever is red or close to red, that's more dominated by the HH. So maybe sparse vegetation over mountains. So those are analysis ready. The GSLCs are very exciting for doing interferometry of your own, and the GCOVs are for many analysis ready to use. Since they are geocoded, and since I already told you that ionosphere is a big deal at L-band, again, no surprise, this is evidence that the correction of the tech for the geocoded products is working. So if you look at the descending track on the right side, where we have a lot of data from the descending over our corner reflectors in Oklahoma, if we wouldn't have accounted for the ionosphere, the blue dots shows the geolocation error in X and Y direction, because this is geocoded now. And we would have meters of geolocation errors, but after accounting for the ionosphere, if we do it with the total electron content, basically with the regular tech that is from the ground to the GPS orbit, that would be the green. So you see that it's overcorrecting it. But then when we account for the we take out the topside tech. We have our instruments, the GPS instruments on the NISAR satellite, and we basically account for that topside part of the tech. Then that's the orange dots that is getting close to 0. So the geolocation of the geocoded products over corner reflectors in Oklahoma is getting to sub-meters at L-band. That is what we dreamed about for several years, and I think that seems to be achievable now. All right, we have interferometry products produced globally, the geocoded unwrapped product, which has also wrapped phase in it in 20 meters. The unwrapped phase is at 80 meters posted. It has the phase itself. You have the wrapped phase at 20 meters. You have the ionospheric phase layer in the product, you have the tropospheric delay, the coherence, the solid earth type. So it's a very comprehensive product, really analysis ready for the users to use. Over cryosphere regions, we are providing those GUNWs, plus we are also providing the range Doppler interferograms, as well as two other products, the range Doppler pixel offsets and geocoded version of those pixel offsets. The pixel offsets are for monitoring and measuring the glacier movements. You see one example here. On the left is the along track offsets, which is impacted by the ionospheric tech variations. So it may take some time to use those along track offsets properly, but I'm sure the community is very, very creative. There are ways already to use them. You can take the ionospheric phase, to kit the gradient, take it out. So there are research there to be done, but operationally that's what it is. And these range offsets are pretty clean and definitely usable. Our colleagues from Cryosphere showed many examples yesterday. The offsets are provided in several layers, basically different resolution to capture different movements and different level of movements. Some coherence maps, actually the two on the left over US and over India is very old, is for the data that are released to public in February. The processor has evolved since then, but this is interesting already to show you that basically the coherence overall in mid-latitude is high as was expected. As we go along to the polar regions, the coherence drops, and that seems to be mainly driven by the ionosphere. Of course, you also see dots of decorrelation circles, for example, over the border of the India or borders of US. They are visible. Those are RFI, and I'll get to them, and we have to deal with them, and there are very promising progress there. Ionosphere, since you already heard about the ionosphere many times, here is one example over Chile. This is some 8, 9, 10 frames, few thousands of kilometers along track over the coastal region of Chile. On the left is the interferogram if we don't correct for anything. And then the second plot is ionospheric phase that is estimated with the split spectrum technique that comes with the product as a layer in the product. We didn't do anything extra. We just got that ionosphere and plotted. A troposphere also is in the product. It's a cube, but you can evaluate it with a DEM, and that's the troposphere map that you have. If we remove ionosphere from the interferogram, that was the main contribution, and as you see, the interferogram is much flat, and then removing troposphere, and then removing solid earth type. So the corrections are working largely, and there are always ways to improve. Here is one example also to prove that the corrections are working. This is over Ethiopia. There was a volcanic eruption that NISAR actually captured it. There is a small interferogram showing the displacement of that volcano. But then I took the time series, some 7, 8 acquisitions or 9, 10, I don't remember. I fit a line to estimate velocity, and that's the first top left plot, so it's very much biased. But if I correct for ionosphere, the bias reduces, and then if we correct for troposphere, it reduces further. So now the velocity is more flat, right? And then the second row shows you the standard deviation of that fit, and you see that it's significantly large if we don't correct for ionosphere, and then we correct for ionosphere, it reduces, and for troposphere, reduces farther. So this is only few month data. With few years data, this is gonna be very exciting. Since I promised that we have to deal with RFI, I'm gonna go back to our global map and zoom into those different parts. Either there are military bases or airports or areas of conflict, you see RFI. So I'm gonna, unfortunately we have been developing multiple algorithms to deal with RFI. They are tested, and one of them is chosen currently. It's with the science data system, but they haven't run globally yet. But I'll show you a few examples of how the algorithm is working. Here is one example over northern part of the Canada. You see on the left before RFI mitigation, on the right after RFI mitigation. So this is working nicely for this case. Another example over Strait of Hormuz that everybody knows by now. You see on the left that before RFI mitigation and after RFI mitigation, very exciting that all those ships were hiding behind the RFI, and now you see them. So the algorithm is working nicely there. Another side of the Strait of Hormuz, again, it is working beautifully. You see that the RFI is mitigated and all those point targets are maintained nicely. There are situations that we have jamming, and dealing with it might not be so easy. In this case, RFI over the urban area. This is still in Persian Gulf. You see that partly is removed, but not completely. So there are residuals in some cases. Not too far from here, over Ukraine somewhere, there is very strong jamming that, again, may not be possible to deal with them completely. However, don't give up. We have multiple frequencies, frequency A, frequency B. There are many situations that one frequency is affected by RFI and the other is not. We have many examples like that. In this case, you see that our frequency BHH reveals the image almost. And there are examples that frequency B is completely clean, the other one is impacted, or the other one is clean, the other one is impacted. And then the interferogram shows signal. Even though the RFI is high, the phase, yes, of course, is corrupted to some extent, but there is useful information there. So even in cases that we won't be able to completely mitigate RFI, I think there is useful information there. We will all learn more about this together, I believe. And then over Los Angeles, that was the other zoom in that I wanted to show. We have the San Andreas Fault there. We have the Los Angeles, so it's an important area. We have a big blob of RFI. We wanted that to definitely go, and the algorithm is doing an amazing job there. How does it look like for interferometry if we wouldn't have, this is the same frame over Los Angeles, if we wouldn't have corrected for RFI, those are the interferograms at the top left, and then you see after RFI mitigation, and then if we estimate ionosphere before and after RFI mitigation, you see the impact. Look at the coherence has recovered over that area that's, I think, Big Bend is called, where is bounded by two main faults there. The southern part is San Andreas, so very important area for science. And then after removing ionosphere and taking care of RFI, the interferogram on the lower right looks very clean and beautiful. We are not fooling ourselves. We know dealing with RFI is tricky. We are looking very carefully. There are situations that when we have very bright targets next to the very dark, we have found only this one so far. We have looked at multiple frames that there is very bright targets over Long Beach, and that is misunderstood as RFI to some extent. It degrades coherence to some extent. But again, looking at the phase did not worry me. We did even phase linking, time series, and all that I don't have time to show, maybe another meeting, and that all looks still promising. Another example over Texas, that RFI mitigation is working and makes interferogram a lot better. And over San Francisco, there was mild RFI, and that is also taken care of. So the calibration is pretty much done. We are under validation activities right now and improvements, but already there has been a lot of interesting science done. The subsidence over Mexico City is very nicely captured by NISAR. The earthquakes in Nevada captured. The soil moisture team are doing great. The volcanic eruption and that time series that I'm plotting is for that volcano is nicely capturing the deformation, the glacier movements over mountain glaciers by Alex Gardner's and team. So overall, I can tell that the level 1, level 2 processor that our team is responsible for is very stable within the NISAR science data system, and it have been successfully deployed. Many cycles, I think we are now at cycle 22, if I'm not mistaken, has been processed. The edge cases identified. Overall calibration is in very good shape, and the RFI and ionosphere that you have heard about in this meeting multiple times, I think it's under control, and of course, always more improvements can be done. I'll stop here.
Thank you, Arash. Perfectly on time. So any questions or comments? We have two here in front.
Thank you, Arash, for the presentation. Can you go back to the Chile example?
Oh, that's too back.
Okay, after you remove the for everything, there seem to be like second-order wiggles, like low-frequency fringes from north to south. Do you know what are producing them?
I don't know. Actually, there are like 10 acquisitions for this one, and we got the worst one. So all of them were significantly more flat. But this one, yes, I agree with you. There is a residual. It could be, I don't know. It could be a residual ionosphere after, this is significant. The standard deviation went down over the entire frame from 2 meters to 8 centimeters. So significant improvements. There could be a little bit residual. But in time series sense, I think it's flat.
Yeah, so did you want to say, so how many frames are there?
I think, I don't remember, but 8, 9, 10 frames. I have a scale here, 300 kilometers, so it's like 3,000 kilometers.
So there are 10 frames stitched and also in time, right?
Yep. Yes. Ramon has a question.
Yes, thank you very much. Very impressive results. Great to have this. Actually, I was wondering about the other frequency, so S-band. Do you have any results of that? And maybe the second question is, I'm a little wondered that there is nobody from India presenting at this Fringe on the S-band results. Could you comment on that?
Yeah, I think I'm hoping that Paul will talk about S-band a little bit. So we are responsible for the L-band. We have a side project to develop ICE3 further to process S-band, so that's decoupled from the project, but I'm a PI on that as well. So there will be a processor for the team if you guys want to process yourself, but our colleagues at India, they are processing whatever S-band that is coming, S and L band over India and over certain targets that there are joint observations. So there will be products. They are not going to be available through the DAC, but they have a system called Budini. I think Paul may talk about it.
Okay, thank you.
So that's going well as well.
Yeah.
Less ionosphere.
Perfect. All right. Thank you so much, Harish. Let's thank him one more time. And we will move to the next presentation.
So the next presentation will be given by Urs Wegmüller. It will be on pulsar 2-3 cross-sensor interferometry.
Thank you, Muriel, for the introduction. So I was supported in this work by Christoph Magnar and Dazio Strozzi. Gamma Remote Sensing is a small Swiss company founded in 1995, so getting quite old now. We focus on microwave remote sensing with main activities, including research projects. Then we have the Gamma SAR, INSAR, and PSI software. We also design, manufacture, sell, use microwave instruments like terrestrial radars or drone-based radars that we play with now and use. And we do services and consulting, and we have significant experience with L-band SAR, starting with JRS usage 30 years ago, and using all the available L-band systems since then. So I will not present a mission as in the previous or in the next presentation, but I will rather focus on small technical stuff. So I'm not responsible for the Pulsar 3 mission or anything, but it's still in this session, the presentation. So I will show different examples of cross-mode and cross-sensor interferometry. So one thing that is different compared to NISAR is that there is a previous mission, Pulsar 2, that is operated in using exactly the same orbit, so you can continue time series. You don't have to restart from zero. And So to map slower deformation, that makes, of course, a big difference, because with a new mission, you have to wait maybe 3 years to get to a few millimeter per year precision, and with continuation of a mission that was already successful for over a decade, this problem is, of course, not there. The Pulsar 3 strip map SLC has a much wider swath width than with Pulsar 2, and the data comes in several sub-beam SLCs. We found that the metadata and the geometry used is fully consistent between the two, so you can quite easily stick these together in one large mosaic SLC. Now, I just give this one slide on the methodology typically used in cross-mode or cross-sensor differential interferometry. So what is different than just using data of one mode is that you have to also determine the common range bandwidths, and the related center frequency may be different from the center frequency of one or the other sensor. And then you do a center frequency shifting and bandpass filtering to only consider the signal that can correlate between the two data sets. You do a co-registration, and this may include also resampling if the two modes or sensors use different sampling grids. And in this, you have to be a little bit careful to avoid aliasing. So typically, selecting the geometry of the sensor with the higher spatial resolution is a good decision. Or you can even oversample one of the geometries if they are higher in one dimension and lower in the other dimension, to be on the safe side. And then differential interferometry is just the normal procedures. Here I show examples of Pulsar 3 strip map and Pulsar 2 strip map spectrum together with a Pulsar 2 ScanSAR spectrum and the Pulsar 3 ScanSAR spectrum. So in the case of the ScanSAR data, along the image in azimuth direction, the location of these spectral bands move. So it's a little bit a more complicated situation if you want to do common band filtering, of course. And for Pulsar 2, we see that you have typically something like 5 small or narrow spectral bands. And for Pulsar 3 ScanSAR, it's 1 or 2 a little bit broader spectral bands. So if ScanSAR data is involved, the common band filtering needs to be done spatially adaptive, of course, because the spectrum varies in azimuth direction. Here an example of a Pulsar 2, Pulsar 3 interferogram with 6 days interval. So having the two sensors operated in the same orbit also gives the opportunity to have further and even shorter interval interferograms. So that's attractive to study faster movements. So glacier motion, or here rock glaciers in the Alps are an interesting target. So to play with different combinations, I selected a test site that includes a Pulsar 2 ScanSAR dataset, and then additional Pulsar 2 and Pulsar 3 strip map datasets, and I form different pairs with short temporal baselines. And also the spatial baselines are short between the two systems. Here we see zoom in on results over a rock glacier, the Murail rock glacier, and here differential interferograms with 6, 14, and 20-day interval are shown, and you see nicely with increasing time interval the phase scales, and so it's very, very plausible that it is caused by more or less uniform displacement rate in this period. So it's a very nice and easy to interpret result, and it's compared with Sentinel data with 6 days for different similar times, and also with aerial photography. And another case, the Teller-Stavains rock glacier glacier is shown here. So again, you see a nice, easy to understand result. With the L-band result, it seems much easier to delineate this rock glacier, for example, or to get a first semi-quantitative estimate of the motion rate at this period. So the velocity change over the year with the temperature, of course. And so it's good to be able to measure velocities with short interval interferograms. Again, the comparison with C-band from Sentinel, and you see with the C-band alone, you're not so sure. You see the motion pattern if you know it's there, but it's maybe not as reliable, or you're not as confident with just the Sentinel data. Here on the left-hand side, Pulsar 2 strip map, Pulsar 3 ScanSAR interferogram is shown. A little bit a longer period, but still quite short. And it is compared with a PSI result generated with a stack of Pulsar 2 data. So if we look at this location, we see that you have increasing velocities up the hill there, so a landslide with higher rates at the top. And then you have a gap at the very top without information, and the interferogram actually shows that there it is moving even faster. So the interferogram provides complementary information, and which is consistent with the time series analysis, but it is adding to the information content. So even using the ScanSAR data helps in this case. Then as a technical challenge, I looked into Pulsar 2, Pulsar 3 ScanSAR interferometry. It's not intended that this is supported in any way by the missions. So I look at the spectrum of a pair, and if I look at the spectrum at line 3500, I see that the Pulsar 3 spectrum band overlaps with one of the Pulsar 2 spectral bands. If I move then down to line 6500, I see that now we have two bands in the Pulsar 3 spectrum, and one overlaps and the other doesn't overlap with Pulsar 2 spectrum. And then on line 9500, there is no overlap at all. The two systems are operated in the same orbit, so the movement of these bands is with the same rate. So if it overlaps, then it overlaps for quite a while. So the second band in the second image corresponds to the band shown in the first image, but it moved a little bit further down. So we applied common band filtering, and so for the Pulsar 3 ScanSAR data on the 6th May, we get from the upper image to the common band filtered lower image. And so you see there are some gaps in the coverage in areas where the spectra don't overlap at all. And on the right-hand side, you see zoom in. So you see that, of course, the spatial resolution is also a little bit degraded. And this is then the differential interferogram calculated. So I masked the areas with not enough overlap. So there it's just gray, it's superposed to a digital elevation model, to the shaded relief. And it really looks like a typical interferogram, and the phase makes a lot of sense. It's not mainly deformation phase, but mainly tropospheric phase. But it confirms that to a certain degree it's possible and also maybe applicable. Then I also investigated persistent scatter interferometry using some Pulsar 2 strip map scenes and some Pulsar 3 strip map scenes. I did this over Mexico City because the time span covered is short, and so there the velocities are high, and so you more easily get a result. One of the Pulsar 3 scenes has gaps in the coverage because of a problem in the data that the direct ground return is at the same time as parts of the image signal. So I masked this because near the gap it's also low quality because only a small part of the spectrum is used. I did only a quick processing, so the main idea is shown here. So there is known areas with large area subsidence, and so to estimate a low frequency phase, I masked these areas. So you see this in the middle, and then the phase was unwrapped and interpolated, and that's estimate for the ionospheric and low frequency atmospheric phase. So this was subtracted for each of the dates, and then persistent scatter interferometry approach was used with a single reference stack. Baselines are short, so I used only a one-dimension regression, only one iteration to slightly improve the atmospheric phase estimates, and then getting as the main result the line of sight deformation rate for the interval. The estimated precision is about 1 centimeter per year with this short stack. So here we see the result. It looks maybe a little bit better than it is because you have these fast movements, this fast subsidence, and so the scaling is between -20 and +20 centimeter per year, and so 1 centimeter uncertainty or error is not visible. Location and velocity rates look very reasonable and plausible. And also zooming in, you see the persistent scatter interferometry really seems to work well between the two satellites. So pulsar 2, pulsar 3 cross interferometry works well. Differential interferogram was tested also between StreetMap and ScanSAR data, and you get the possibility of shorter 6 and 8 day interval pairs. PSI was successful for a combined stack. The drawback, there are some quality issues like higher than wished for noise equivalent sigma 0. You have some azimuth ambiguities, especially visible at cross polarization, and you have some data gaps if the processing is done with fixed PRF acquisitions. And there's some other issues with the Pulsar 3 ScanSAR data, like the data files are really, the one I used was 400 gigabyte, and it was provided in 400 small 1 gigabyte files, and I had to click for each of these and then concatenate the file. So it's not very, I think this will improve over time. To just finish, it's not a validation of the PSI result, but just a comparison with a similar processing done with a few NISAR L-band data sets over the same area. It's different geometry, so don't compare it one to one, but it looks both very plausible and attractive. Thank you for your attention.
Thank you very much, Urs. We have time for questions. Are there any questions? Dirk?
Yeah, thanks also for the interesting talk. Regarding the spectral shift that you mentioned, did you check the burst synchronization for the ScanSAR case? And although, what is the Doppler difference between the two spacecraft then in terms of what creates as a contribution to this shift?
Yes, so both are operated in more or less zero Doppler, so very small Doppler, so that's not really an issue. For Pulsar 2, I have the experience that it is really well synchronized. So there was like a half a year in the beginning where it was not. And then all the pairs I looked at, and I'm using it quite a bit, were synchronized nicely. So I don't know, 90% or more overlap. So the knowledge is there at JAXA, so I assume it is well synchronized, but I did not test it. I'm hoping to see a result of a pair, and I only download another data set when I use it will work. So I have the same question. But I'm pretty sure it is synchronized, yes. No, between the two, it is not intended that you do interferometry, but it's in the same orbit, and so it is more synchronized than intended, because how the bands shift is the same. So if it overlaps, then it overlaps for quite some distance or area in the scene. But also the subswaths are not the same. So maybe if you looked at the missing data in the common band filter, you had many zones, because you have subswath 1 of pulsar with subswath 1 or subswath 2 of pulsar 3, and then one changes and the other not. So yeah.
Thank you for the presentation. So I have worked also with pulsar free, and something I noticed is that like half of the scenes, at least in the Americas, have these black bands due to the fixed PRF mode. So I was wondering how frequent is that issue in your data?
Yes, I think that's, there were more severe quality issues not using a fixed PRF mode. And so the decision was, I think, now to use this fixed PRF, and the drawback is to have some gaps.
Were you seeing coherence drop with the staggered PRF? You also evaluated staggered PRF cases, right?
Yes.
And were you seeing in the PSI or in interferometry, were you seeing coherence degradation? Or
because of these anomalies in the...
Yeah.
Not so much, no. Okay. It's at relatively high coherence levels anyway, and so to go from 0.7 to 0.6 doesn't mean that the phase that you estimate changes much. Okay. So I think the noise is not the relevant error source in this kind of work, but more atmosphere and ionosphere and how you estimate it. So here I used a simple trick and I get a nice result, but that also means that maybe I shift some signal into the atmosphere and so on. So, yeah.
So, no other questions? Maybe one. Here you calibrated with the same point, because there seems to be a not so small bias, no? In the
yeah, it's a slightly different time, and then it's a different observation geometry. So you see it from.
This is the.
So okay. It's not the same component.
Okay, so this is.
I did not scale it.
Velocity, okay.
I mean, you could scale it, and then it would look more similar, but
this
it's
is
not really the.
Yeah, sure. Okay, good. Thank you, Urs.
Yes.
So.
Thank you. Thank you. Okay, our next speaker is Yuzhao Qin. Is going to present an update on Chinese SAR missions for INSAR applications.
All right, thank you, Marco. And my name is Yu Xiao. I come from Northwestern Polytechnic University of China, and today I'm going to give you a very quick update on the recent Chinese SAR missions. And just a quick recap. So 10 years ago, we basically still don't have any SAR data, SAR satellites in the sky. But in the last 10 years, we are actually moving quite fast with some very interesting missions here. And we also have the space agencies, and we are working very hard on the applications. And so today, I'm just going to give you a very quick recap on some of the interesting projects. And so let's start with Golfin 3. And so if any of my dear colleagues was here 3 years ago in Leeds, I did a report on the Golfin 3, so where we first demonstrate the time series capability for Golfin 3, so where we have like a nice subsidence map over Beijing, and we did a comparison with Sentinel with very nice results. And so today I'm just going to give you a brief status updates, and in 2021 2022, there's the constellation with 2 more satellites in the sky. And so together for the INSAR, they can form like a 1 day, 60, and 22 days like revisit time. And there are some like regular updates, like for example, there's actually this onboard application-oriented processing where you can do, for example, oil spill detection on the board and just downlink the results. And we also have the ASI support as well. And so there are some other small things like changing of imaging modes from ScanSAR to TOPS, but yeah, just very regular things. And but one thing that is very unfortunate for the INSAR community is that Golfin constellation is still not really aiming for INSAR at this moment. So it's still mainly a marine science oriented satellite. But we're actually getting good news. So in the next 5 years, we're actually anticipating the next generation of Golfin 3, where we will be heavily working towards the INSAR applications. And then there are some updates from other satellites, and one of the interesting one is Lutan. And so this is the L-band biostatic mission. And so there are 2 satellites altogether, and it's in L-band with a maximum spatial resolution in strip map of 3 meters. And then there's we have 4 and 8 days, so 8 days for 1 satellite and 4 days for 2 satellites. But now the main mission for Lutan 1 is to do a nationwide coverage over China. So actually we use this strategy of doing a 28 revisit time over the entire nation of China so that we can get full coverage. And so the satellite is in operation somewhere in 2023. And yeah, so that's the basic status. So in the first year, there was a period of 1 year where there's this biostatic mission to do the national mapping of topography. And then after this 1 year, now they're flying in this INSAR mission with the 4 days and 8 days revisit time. And here I want to introduce 2 of the projects we are working on. So the first one is we are working with the Natural Resource Department of Shanxi. So Shanxi is where I come from, a province. For some of you who don't have an idea, so the area of Shanxi is more or less same as Great Britain. And so what we are doing is that we are together working with the ministry to provide this monthly de-INSAR deformation map. So there's really no fancy technique. We're doing de-INSAR stacking. But one thing that we're really proud is we're actually able to put this into operation, and we're actually nowadays delivering monthly de-INSAR map for their nature hazard inspections and all the operations. And we're actually helping them to locate a potential nature hazard. And so for the entire area of Shanxi, there's we stitch around 200 images ascending and another 200 images descending. So it's actually quite a heavy work for us. And one more thing we're doing is we're using the biostatic data from the first year to do a countrywide mapping of the topography and also the tree forest height. And so this is still an ongoing work. We're going province by province, and actually one of the results we already have, which is published in Remote Sensing Environment down in the corner, is we have the first results over the island of Hainan. And so we already have the terrain product and the validation with the LiDAR, with the Jedi product, showing quite nice accuracy of the font is a little bit small, but RMSE is around 5 meters for Lutan. And so we're getting more or less the same accuracy for the rest of the country. And hopefully by the end of this year or next, we are going to give a nationwide tree height map and the topography map. All right, and apart from the L-band mission, I'm also going to introduce a little bit about the commercial side. So we have the space station, or Tianyi. And so far there's 6 satellites, 6 satellites in the sky. And so we started from 2020, and the first 2 satellites, Haishi and Chaohu, are not for INSAR, and starting from Fucheng. And there are satellites that are built for INSAR from the beginning. And just last month, we have this so-called Dianjian, so it's the X-band, and the previous one is the C-band. And we're going to have the no inclination by the end of this year. And this is one of the images I'm really fond of to show, for the strip map, you can really get very high resolution details for the city. And some of the specs, and so for the resolution, I mean, it's still quite nominal, standard things, like a strip map around 2 meters, and we get a fairly good PSR and NESZ, stuff like that. And so one thing I want to mention is that from the beginning of the space station missions, we are actually aiming for INSAR. So here I have 6 histograms. This is not representative. I just picked 6 stacks I have from different missions. And you can see for the Sentinel and Tersar is almost within 200, which is good. But for Fucheng, we are actually achieving less than 100 meters for most of the time as the spatial baseline. So one thing also to worth mention is that you can see for the Lutan, because it's L-band, it has a much larger critical baseline. So the most of the baselines are within 1,000 meters. So I see 500, 600, which is good enough for doing INSAR. So for Golfin, it's not intended for INSAR, so they're not specific doing orbit control, so it have a less better thing. Okay, so here are some of the interferograms I show for the space station. It's pretty good for a micro star satellite. It's 285 kilograms. And so I also want to show some of the results. I mean, this is fairly standard. We did a process in the city of Fucheng, where it's named after the city. And in terms of the point density, you can see much better in this C-band, like high resolution data. And we also actually did a comparison with the TARSAX, so where we have like around 20 images here in this city, and another like 25 images of this microstar satellite. And I think the first row is the TARSAR, and the second row is Fucheng. And you can see they are like really comparable to each other because they're like, I believe this one is ascending, one is descending. So for some places you see a difference in the point density, but I mean overall it's like quite satisfactory considering the like low cost of the this like micro star satellites. All right, and the next one that is going to be quite interesting is the geosynchronized star satellite called Lutan 4. And so here I also want to report a little bit of the status. So it was launched in 2023. And just by the beginning of this year, February of this year, it went out of the commissioning phase. And now it's officially going into operational status. And yeah. So unfortunately, we are still not really getting any images from the this satellite, and still working on that. But we did a little like analysis just based on the like open source LTE data. So this is like the prediction orbit we get from the you can get it from the internet. And we actually get the TLE data, and we did analysis for the baseline just to see if we can actually get some nice interferograms. And so here, the first row here that is showing like the altitude of the satellite. So it's like actually varying a little bit. I'm actually not sure they're like doing orbit control at this moment. And so what we did is we tried to calculate the spatial baseline. And so here in the second row and third row here, we picked 4 points on the in the orbit. And yeah, we picked 4 points in the orbit, and we actually calculate like the sequential baselines here. So you can see based on our estimation, it's mostly within like 8 or 4 kilometers. So yesterday, they also mentioned that 4 kilometers as a baseline design. So we see more or less the same. And of course, I mean, this is like sequential baseline. So you can see the satellite is actually drifting a little bit. So we also want to know if in the longer time, for example, 2 month like revisit time, if we're going to get INSAR results. But yeah, we are still trying. And so one good thing for GeoSAR is that the critical baseline is actually much larger considering the altitude. So here we did some like simulations, so for different incidence angle, and like so for like different kinds of like for different kinds of incidence angles, we try to calculate like a critical baseline, and we actually use 10% of the critical baseline setting as what we call as like an engineering feasibility level. So you all know, for example, for the critical baseline of C-band, it can get to 10 kilometers, but usually anything larger than 1 kilometer is not usable. But so we estimated 10 kilometers of baseline should be usable, and we're way below that, so this makes us really confident. And I'm pretty like sure that we're going to get some nice results, hopefully by the end of the year, to give you a heads up on the news in the interferograms for the GeoSAR. All right, and so that's the main part of my talk, and some other interesting things that I want to share. So for example, we're also working with Huawei, and so they're actually producing this very low-cost MIMO radar. It's around 3,000 euros. So in the past, we get radar from Texas Instruments. It's actually quite expensive. And nowadays, we are actually able to use this MIMO radar. So this MIMO radar, we place it on the slope, and it's intentionally used for like Doppler checking the speed of the cars. And we can actually use the other part of its capability to do the slope monitoring. And we're already deploying some of these devices on the slope, and we're getting quite good results. Of course, this is still also work that is ongoing, but I mean, things are looking quite good to us. And also, there are some other interesting missions that I really don't have time to go into. And for example, there's this so-called Hongtu system. So it's like we call it a cartwheel system. So it's more or less similar to the idea of Harmony, but the baselines, the Admiral's baseline is much shorter. So it's we have like 1 main satellite and 3 flying around. And so now this is being operational for like 1 year or two. So I think it would provide some nice like verifications for the idea of harmony as well. And also we are going to launch a dual antenna X-band similar to SRTM, hopefully by the end of this year or next, so that we can get better results here. And the last part, we are also want to commit to the open source world. So here we are actually having this so-called Teresa. This is an open source tool for the Chinese SAR. So thanks to Ramon, we're actually building a wrapper over Doris, and we read some readers, and so that people can use this. And if you go to this GitHub, we also provide some example data there for Golfin 3, Lutar, whatever, that you can test with. And this is still heavily under development, but we actually really want to share our results so that people can actually process the data. And one last question you are going to be interested in and ask is, where do I actually get the data? I mean, so the answer is quite complicated, I would say, because different from Sentinel and NISAR, which are scientific missions as far as I understand. So for most of the Chinese SAR missions, these are actually operational missions, which means that they are mainly used for example, Ministry of Natural Resources, or etc. And they support operational works in the first place. But still, for example, for us in China, in universities, we get this data for our scientific research. So here, there's 3 ways. So the first way is the so-called CRESTA. So this is the official website where you can query the Golfin 3 and the Lutan 1 data there, and actually you can make an order. But yesterday, I just realized that this website is only limited to Chinese IP. I don't know why they do that. It's ridiculous. But so found a Chinese friend and asked them to query the data for you. And at least you can have an idea where you can get the data. And they are not open source data you can download, but yes, if you want to do some scientific research, you're always welcome to talk to me. I am not from the official side, but I can point you to the correct person who, if you have some budget, you can buy some data, and if not, we can see what we can arrange. And for the space station, which are commercial star satellites, so they also have a website, and actually they really welcome communities, scientific communities, to use their data, and they have some hotspots and where you can download and you can play around with that, and sometimes you can even make orders. And yes, of course, if this is too brief for you, you can always talk to me and I can point you to the right person. At the recap, so I think in the last 5 years, we are seeing a lot of very interesting, exciting new missions. And so at this moment, one thing I really would like to do is, first of all, I really want to promote our data as well as our post-processing tools. I mean, it's not down to me because I'm working with the ministries and agencies, so we're working together to do that. But I think things are getting better. And also, we are looking forward to more and more interesting SAR missions in the next 5 years. And I think that's all for my presentation. Thank you all.
Thank you so much. So we have a question for 1 or 2 questions. Yes, Sang-ho.
Thank you so much for sharing. It's exciting to see that the data sharing plan is in place. 2 quick questions. So Chinese IP, can we just use VPN and then access Chinese IP and access?
Yes, you can.
Okay,
yeah,
thank you.
Yeah, I'm not responsible for that, so you need to find your own, yeah.
Thank you. Second question is, Fucheng 1, you mentioned a microsat 250 kg. Do you know the price tag of that mission?
So, again, I'm not from the official, so I can't make the price, but I would say the price is really competitive as far as I know.
Meaning 100 millions, 10 millions?
I really need to talk to that privately with you, not
okay.
in the... Yeah.
Thank you so much.
Okay, any more questions? There's a, yes, front.
Thank you for the presentation. I'm wondering if Lutan 1 has a global acquisition program, so in terms of the data, acquires data, let's say, in America.
Yeah, so I'm not entirely sure, I need to check, but as far as I know, so first of all, we're still doing nationwide acquisition over China, and we're doing acquisitions at our neighborhoods. For example, we're doing Kazakhstan, Uzbekistan, etc. And I think for the other places, we're still mainly just setting up a couple of hotspots and to do acquisitions, not nationwide or continental-wide. But I need to go back and check the website. You can do that as well, yeah.
Okay, we have time for 1 more question or comment. Ramon?
Yeah, thank you, Yusha. I think it's a nice development to see that the Chinese SAR data are opening up in some way. What is the overall development that you see on the level of data sharing? Is it going in the direction that it would be more free and open, or do you see geopolitical fluctuations in that?
I mean, so first of all, I think we're working on that, and I'm talking with like different officials, with agencies, and the people who are in charge for like distributing the data. And I would say there's pretty much a trend that they want to open up. And so for us, this is still like exploring process. I mean, we're still learning a lot, for example, from today, from the policies of NICER and Sentinel. But I think in general, there's a trend of opening up and open, especially more to the scientific community. So I mean, it takes time, but I think we're moving towards the right direction there to do that. Yeah.
Thank you.
Yeah.
Okay, yes, thank you very much. So it's very impressive, as said. But one solution in order to really share data could be to establish kind of super sites, right? Where we can coordinate this also with satellites that we have in Europe and in US, wherever, where we have in principle collected set of satellite data, very locally region, right? Smaller areas where we can share these data sets. This could be really great if this can be established.
Yeah, I totally agree, yeah.
Do you think that's possible?
Yeah, again, I'm not speaking on behalf of the officials. So I think this requires like a commitments from both sides, right? For example, now we have the Dragon project, but now it's also running into some like challenges. And if there's commitment from both sides, I mean, surely we can work hard on our side.
I mean, it can be also outside of China, right? Must not be in China itself.
Yeah, sure. That's something we're also trying to work on. Yeah.
Okay, good. Thanks.
All right. Okay. Thanks a lot.
Good, so for the next presentation, I introduce my co-chair, Marco Lavalli, who will talk about NICER temporal coherence for land applications.
Thank you, Muriel. So this presentation, I'm going to go into the details of using NICER data. So unlike the other two presentations on NICER in this session given by Resh and Paul, who are representing the project, in this case, what I thought I would do, I would take the user's perspective and kind of see what users will experience when they download and access NICER data and start working with the data. So I sort of resurrected some of the work that I had done during my PhD and later in my career related to the land models for interferometric and polarimetric coherence. And so I thought, we have all these models, and finally we have L-band time series that are global and dual pole. And we also have some of the geocoded products that the NICER project is delivering, and you heard some of them in Resh's presentation. And so I thought, what can I see? What do I see in the NICER product? Do I see the expected polarimetric interferometric sensitivity to the biophysical land parameters? So that is really the question that I had in mind a couple of weeks ago before coming to this conference. So I'm going to walk you through the process that I followed just as a user accessing the data. So the first thing, so I'm interested in seeing the interferometric coherence and whether that is really giving us what we expect in terms of land parameters sensitivity. So the first thing that I thought I would do, and probably that's the first thing that everybody does working on interferometry, is to check the baselines. So in this case, I actually asked the navigation team to calculate all possible pairs, baseline of the possible pairs starting January 1st. And so as you can see, this is the actual estimated baseline, measured baseline between two consecutive NICER passes. As you can see, the baseline is actually very, very small. The critical baseline for NICER is 20 kilometers, depends on the mode, of course. But as you can see, most of the time it's below 100 meters. Now, and it's stable over time, as you can see from the orange plot. Now, if you plug this model, this baseline estimate into the models of the baseline decorrelation or the volume decorrelation, you can see that essentially we can consider these two decorrelation sources negligible for NICER. Of course, it changes if you have slope and terrain slope or if you have a 5 megahertz mode. But overall, the baseline for NICER is very, very small. So that was a very good news and made me comfortable that everything that I was going to check and look into the NICER data was not affected by the baseline, and stay reassured that this is going to be the case also for your analysis too. The second thing that I thought I would check was the SNR. So I asked myself, is the SNR high enough so I don't have to worry about the SNR decorrelation? And I think the answer is yes. So here is an actual SNR map from NISAR that you can estimate from a noise equivalent backscatter layer that is delivered with the product. In this case, I used the geocoded SLC product. You read a noise layer, which you can sort of subtract from the main band. You divide the main band, the signal, by the noise, essentially, and you get this map. So you can see that the SNR is fairly high, 8 to 20 dB. If you plug these values into a simple model of SNR decorrelation, you can see that the coherence due to the SNR is fairly high, 0.9 or above. So you don't have really to worry about SNR decorrelation. Of course, if you are of a bare surface, HV polarization, maybe you're in the winter. Here I was in May when I checked this map. But in general, you can correct for the SNR decorrelation, which actually I do in the next few results that you'll see. But in general, SNR is fairly high, and you have seen some of that in Arash's presentation earlier this morning. So the other question that I faced was, should I use the geocoded SLCs or the geocoded unwrapped interferogram? Now, the geocoded unwrapped interferogram is essentially an interferogram generated using the traditional INSAR processing chain. So you have essentially fine co-registration. You have all the correction that you can imagine. And so that's something we like, right? So everything is perfect, co-registered, and so that's the best coherence that you can get from NISAR. The only limitation that this product has, at least for what I wanted to do, is that it's only calculated for HH polarization. And NISAR is a dual pole everywhere, or almost everywhere. Sometimes it's quad pole over land, but it's definitely dual pole over land. And so I wanted to have the ability to look also at the HV polarization, and it's actually important, and you'll see in a minute why it's important to have HV interferograms or cross-pole interferograms in general, not only the copole. The other limitation is at the bottom of this slide. It only is calculated by the NISAR project only for the nearest neighbor pairs. And so what I wanted to do here was to calculate all possible pairs because I wanted to study the coherence over time. The GSLC do offer that ability, right? So the GSLC are simply geocoded SLCs using a sync interpolator. They're phase corrected, so you just cross-multiply two SLCs and you're done, essentially. You filter a little bit over multi-look. And you can do that for both HH and HV. And you can do that for all possible pairs. So this is very attractive. The only problem is that the ionospheric correction can affect, the ionosphere can affect the geocoding of the SLCs and so the coherence. So what I thought I would do, I will first check the coherence estimated from the geocoded SLCs versus the coherence estimated by doing the actual processing, insert processing, and stored in the GAN-W product. And so to that end, I considered a time series of 13 geocoded SLCs and 12 GAN-W products. Here I'm north of San Francisco. I considered the red box because I'm interested in the land. Just incidentally, you see there are some RFI over San Francisco. I did not correct for RFI. I did not need to correct for RFI for this analysis. Everything you'll see is all the processing you'll see in the next few slides are in that red box. Just incidentally, I checked the frequency B, again, as a user, is curious to see what the frequency B looks like. And you can see there is no RFI. I could do interferometry, I could do anything I want with the frequency B. It's nothing, it's a respectable frequency. You can do anything you would do on frequency A. You have a range resolution that is coarser by a factor of 4 or 8, depending on the mode, on the main mode. Here I'm with 40 megahertz over North America. 5 by 5 meters is the posting of the geocoded SLC. So for this presentation, I'm using the frequency A red box. Now, because everything is geocoded, I can easily download the world cover map and in this case, the ladder-based tree height map, which I'm using in the analysis. And just keep in mind, and then as you see the results in the next few slides, that the west part of this image is basically forest. There are mountains and forest with trees up to 40 meters high. The eastern part is mainly croplands and built-up areas. That's important to interpret the results in the following slides. So here's the first comparison of the geocoded SLC coherence and the GAN-W coherence. Here I'm plotting the histograms of these two coherences from the estimated for the nearest neighbor pairs, right? Because the GAN-W is only offered between two 12-day basically coherence images. And so you can see that the histograms are matching very, very well. And so except for this very, very low values, which might be due of coherence, which might be due to the different number of looks, they're not exactly matching. There is, of course, interpolation and resampling that could affect potentially the coherence. But overall, if you look at this particular pair of coherence between GSLC and GAN-W, they're very, very similar. So what I did to convince myself that the coherence was actually well estimated using the GSLCs, I estimated the ratio between the geocoded coherence, geocoded SLC coherence, and the GAN-W coherence, pixel by pixels. And I plot that versus the total or the true coherence, which I consider to be the GAN-W coherence. So if you imagine that the geocoded SLC coherence is essentially the GAN-W coherence multiplied by a penalty factor, that penalty factor is the factor in coherence that you pay for being lazy and using the geocoded SLCs and not doing the full processing, insert processing, as anybody probably in this room would do, you see that that penalty factor is essentially 1. And what's even more important, the deviation here is symmetric. So it's not really biased. So anything that is different from the geocoded SLCs is due not really to a penalty that we're paying because we are using the geocoded SLCs. There are differences, but these are probably due to other factors, not really to the geocoded SLCs. I have to say, by the way, as a disclaimer, that I am a slant range person. I think this is my first time I do an analysis on geocoded world. I always use the slant range geometry, and I put all the layers in this. This is for years I've done that, so this is my first time, and actually I was very pleased to see that I could estimate the coherence very easily in this way. So I was really suspicious that this was working too well. So I thought maybe I was just lucky and there was no ionosphere in this time series. This is unlikely for NICER. If you look at NICER data, L-band, we just passed the solar maximum, there is ionosphere a little bit everywhere. So what I did to convince myself, I checked a layer that is delivered in the geocoded SLCs. That layer gives you the range correction that is applied because of the ionosphere. That is coming from models, the GNSS-based models, right? So that layer is actually, you see that raster. It's a coarse resolution raster. You have 6 to 8 points, roughly, within the 240 kilometer by 240 kilometer frame, NICER frame. So it's plotted here. And what I'm plotting here is the median of that range correction, ionospheric range correction over time. You see that in mid-December, that correction was 2 meters. This is due to the ionosphere, again, estimated from the model, from the tech. Goes down in December, in January, actually, and then goes up, as you would expect as day becomes longer and warmer. And actually, what's important here is that the correction is about almost 4 meters here, which is comparable to the pixel samples, the sample size of the geocoded SLC. So message from this slide is that there is some ionosphere in this time series. We're correcting using the model, and we are correcting properly. If we did not correct for the ionosphere, this would be probably heavily decorrelated. So that gave me some confidence, and so I could finally estimate all possible pairs. So this is the coherency metrics. Dates are here on these axes, both dates. So this is the backscatter. On the diagonal, the top triangular is the interferometric coherence. Here's the interferometric phase. We are in the HH polarization. As you move away from the main diagonal, you're looking at the longer temporal lags. Here are all the 12-day pairs. You can see coherence is higher. And here is the phase. You see some fringes, right? So this is the higher fringe rates of the ionosphere, which you can correct if you accumulate the phase screen that is delivered with the GAN-W product, right? So the GAN-W product do have a phase screen to correct for the ionosphere. You heard it from Meresh's presentation, also the troposphere and solid earth tides. And so you can actually apply that layer to the GSLC-based coherence, which I did here. And you can see it's much flatter. So I was very happy with this result. Again, this is not tropospheric corrected, it's just ionospheric corrected. There's ways to improve the phase. So I stopped here for the analysis of the phase, and I was pretty happy that and comfortable that the actual coherence was estimated properly. I have a similar block for the HV polarization, right? So we have HH and HV. It's very simple to do it once you have everything lined up. And so what I thought I would do in this case, instead of dealing with the ionosphere, the residual, atmospheric effects, I would take the difference between HH and HV interferometric phase. So what that difference does, right, takes away all the common terms to the interferometric phase. And typically, to first order, I think we can assume that atmosphere is common between HH and HV. And as you can see, basically those fringes disappear. And what we're left is something else, right? So this is a time series at the top, date by date, starting in December, going to May or April. The difference between the HH and HV interferometric coherences. We see three different patterns. One, that is sometimes is effectively white, so no differences between the interferograms. And in some other cases, we do see a clear signal, so some differences between the two polarizations when we look at the interferometric phase. And sometimes it's negative, sometimes it's positive. What is this? This is the effect of the moisture that is affecting differently soil and vegetation. And I think that's the right interpretation. I haven't thought through all the equations yet, although I did write some equation, which I'm now showing. And I think that is correct. So if you assume that the HH channel is dominated by surface scattering and the HV channel is dominated by volume scattering, what we're seeing here is the effect of the moisture, or in general, water content, that change the propagation in the soil and in the vegetation differently. And so that's what we're seeing. Now, to kind of prove that, I plotted here the precipitation, these are the blue bars, and the evapotranspiration, that's the atmospheric demand for water, versus that HH and HV coherence phase difference. And as you can see, if you look carefully, each time there is a color, here these phase shifts, 20 or 25 degrees phase shifts, orangey or blue, it corresponds to a dry versus wet acquisition. For example, let's look at this one here. So here on January 6th, there was a lot of precipitation just prior to that NICER acquisitions. These are the green vertical bars, right? So these are the 12-day NICER acquisitions. It's a lot of rain. And so this interferogram is a rainy interferogram versus a dry interferogram. As you can see, there is a significant phase shift. Then there was a dry versus dry interferogram, that's white. And then again, a dry versus wet, and that's the opposite sign. So I think it's fairly well correlated with precipitation and moisture. So I think that interpretation is correct. Keep in mind, these are not closure phases. These are not closure phases. These are phase difference between HH and HV interferograms. They do deliver some information, although I think looking at all the other presentations, most of the presentation were only looking at the copole interferograms, but there is something to be said in the cross-pole interferograms, I think. And NICER is actually kind of showing that as we expected. So stepping back now on the interferometric coherence magnitude only, so I looked at the coherence over time, right? That was my original goal. Is NICER really showing what we expect in terms of modeling? So I've been working on models for many, many years. I have to be honest, I had to modify. I was never 100% happy with long temporal gaps with the random motion over ground model that we developed and improved over the years. So what I did here in preparation for this analysis, I slightly relaxed some parameters. And so I'm going to spend 30 seconds on this model. So typically when you have coherence over land, you can write it as the sum of the coherence over from the ground or the surface. This includes double bounds, by the way, and the vegetation. And the factor that weights these two contributions is the fraction of the ground to volume, is the ground to volume ratio essentially. It's the fraction of the ground and the fraction of the vegetation. This comes from the scattering from the ground and the volume. Both models here are exponential, and they have two different time constants. And there is a beta parameter that is an heterogeneity coefficient here. This is physics-based. There's some basis for this model. But the point here is that when I look at this model, when I fit this model over the coherence from NICER, I actually see a very good fit. So, and I was pretty happy to see that this is true both for HH and HV. So what I could do with this, I could actually stratify because I have a geocoded SLC, right? Everything is geocoded. It's very easy to get the LiDAR map. I don't have to do anything actually. And I could stratify that fitting per vegetation height intervals. So short trees, I fit the model. And then I increase the tree height from the looking at the LiDAR map, and I do that little exercise of fitting the model per height intervals. And what I see here is exactly what I expect. So the coherence is dropping over time, and as the tree increases in height, the coherence drops as well, and the model actually captures that to some extent. So overall, I'm seeing what I expected to see. Now, if I look at the estimated parameters from the model, that's also actually very encouraging because this is the ground-to-volume ratio estimated by fitting the model per different tree height. And what I'm seeing here, again, from coherence observation, interferometric coherence observation from HH and HV, I'm seeing that the ground-to-volume ratio changed between HH and HV, as we expect, and decreases as we increase tree height. That's exactly what we expect. And it's the same thing for the time constant of the vegetation. It's actually a little bit surprising that it's now linear, but it goes up and down. Now, it needs to be verified if this is a good fitting or not, but it is something that I'm observing and could be something that we're discovering with looking at time series, L-band time series. This is my last slide. I wanted to point out that the geocoded SLC do offer another advantage. For those of you who do polarimetry, which probably is not many in this room, what the GSLC does gives you the scattering vector. And with the scattering vector, you can estimate the 2x2 covariance matrix. And from this covariance matrix, you can live in the polarimetric world and do all the polarimetric analysis. With dual pole, it's fairly simple. With compact pole, S-band, we will have a little bit more sensitivity. Full pole, and we have some data in full pole, it's more rich in terms of polarimetry. But you can also hop from one technique, the polarimetry, to the another, interferometric technique seamlessly. So you can estimate the coherence as we have done in the previous slides. So what I did here is to estimate the entropy. I know Muriel is looking at me like I'm over time. I'm done. I'm estimating the entropy using the GSLC, and I'm seeing what I expect. Where is the forest? The entropy is a little higher. And I can actually correlate, because I can hop between interferometry and polarimetry, with no effort, I can estimate I can actually plot the interferometric coherence versus the entropy, and I can see exactly what I expect to see. Stable targets over time from the coherence, so high coherence, also corresponds to scattering that are very dominant, right? So when you have very low coherence is where you have dominant scattering. And by the way, that's also very well correlated with land coverage, you can see from all the colors. That is my last slides. Message is that I think NICER will reveal a lot of interesting results. So, and the GSLCs are powerful, as you saw. Of course, there is more to do about that and investigate, but I think we're on the right track. Thank you.
Thank you very much, Marco. We are a bit out of time, so maybe one quick question.
Should be short. Thank you. Very comprehensive overview. You mentioned your matrix of interferograms. You mentioned the ionospheric correction was done using split bandwidth. So did you do it actually by using the two A and B frequencies, or was this on pre-computed TEC maps?
You know, I'm glad you're asking, because this question was asked by at least 3 people after I did the same talk at user. So when we say split spectrum for NICER, we're not really splitting anything. We're not splitting the band. We're actually using the 2 separate bands.
That's the same, no?
Yeah, and yeah, it's the same, right. So was that your question? If we were splitting the spectrum?
The question did you use pre-computed TEC maps or actually split spectrum?
I'm sorry.
Written on the slide.
Yeah, I know. I estimated it from the split spectrum, yes.
Thank you.
Not pre-computed. The TEC maps are only used for the geolocation correction.
The last speaker of the session is Paul Rosen, NICER project scientist, who will give us an overview and status of the NICER mission.
Good morning. If there's one thing I've learned working on this project for the last 15 to 30 years is that one has to be adaptable. And so Marco has eaten into my time. And I was originally going to be the first speaker in this session and perhaps should have been the first speaker of all the NICER papers because this is kind of an overview, which you've already heard everything about from all the other speakers. In addition, Mark Simons, who is the lead for Solid Earth, was to be here and be in this session, but something happened such that he wasn't. And I have his slides, and there was an agreement to put me at the end of this session and then present as many of his slides as you have the patience to see into the coffee break. So what's going to happen is I'm going to go as quickly as possible through my slides, which is usually not very successful because I talk a lot. And then I'm going to turn around after questions. I'm going to turn around and let anybody who wants to leave the room for coffee break leave the room. And then I'm going to continue for as long as possible because I don't want you to be embarrassed by leaving the room. That's why I'm going to turn around. Anyway, thank you for staying and being here. I'm going to talk a little bit about the interferometric performance, which of course you already just saw from Marco, so you don't really have to pay too much attention. I was the first author on this paper, the only author listed, but NICER is the result of the work of hundreds, if not thousands of people over many, many years. This was a photo taken of the US NICER team right after we fully integrated and packed up the L-band and S-band instruments together at JPL before shipping to India. And then in the INT phase, the mission, the instrument was there, integrated with the spacecraft, and we had a number of science team meetings with the integration and test team. And this is both the joint US and India team. It was quite an effort to get to where we are, but I'm happy to say that so far, so good. So here's the outline of my talk. I'm going to give you a little bit of background for those of you who don't know what NICER is. I hope that's nobody, but it'll be very quick. A little bit on the status, a few early results, just to make a few points, talk about the interferometric performance, which Marco already kind of covered, and a little bit about the products and timelines for release, which many of you may be interested in, and just a quick summary. Okay, so NICER started officially in the decadal survey in 2007. That was a long time ago, and it took a long time for us to get here. It took many interactions with our colleagues here in Europe to see if we could make a mission. And then we ended up, after many years of study and negotiation, with a partnership with India. The decadal survey specified a set of science goals that you see here in the ice sheets area, in the cryosphere area, in the solid Earth area. And these don't always have compatible mission design requirements. So if there's anything about NICER that you don't like, you can blame this slide for that purpose. In working with India, they were very interested in all of these different areas on a global scale. They're also very interested in local applications, and one of the things they wanted to add to the system was some emphasis on coastal processes. And in fact, through that inspiration, we also look at coastal processes around the US as well. But that wasn't really the beginning. The beginning was 1978 for us when CSAT launched about 49 plus years ago, something like 1,400 12-day repeat cycles ago. A lot of lost opportunity in the 49 years since CSAT. But CSAT started it all, started the interferometry craze, shall we say, and we've been trying ever since to get this mission. And now we have it. So this was an artist's animation of what the launch looked like to inspire us to bring the mission to conclusion. This was made in 2016. This was the actual launch of the mission in 2025, July 30th. It was a picture-perfect launch, launched right into the exact orbit we planned with plenty of excess fuel. I'm going to skip the video there in the interest of time. So for those of you who have not heard of what NISAR can do, it's a dual frequency, L-band and S-band synthetic aperture radar system in an exact repeat orbit with precise pointing, precise orbit control, 12-day repeat like Sentinel, but in a different orbit, and full polarimetry using the sweep-SAR technique that allows us to get full resolution while we get the full swath and polarimetry. It uses sweep-SAR with a staggered PRF in almost all modes except for quad pole at the moment to allow us to get complete coverage over that 240-kilometer swath, unlike what's going on with the PALSAR 3 instrument that we heard earlier from Urs. And it is unique in that it is looking to the left side of the velocity vector, meaning that it has exquisite coverage of Antarctica on a regular basis as opposed to the north. And we view this as very complementary with what Sentinel is doing, looking primarily focusing on the northern ice. All right, so here's the mission status. This is one slide on mission status. And I'm sorry, I have to turn this way because I can't read that. So we began official science operations in December of this year. The commissioning phase ran from July through the end of December, and it was quite successful. Had a successful review demonstrating that the instrument was performing as it was designed. We had a few technical hiccups at the time. There was one digital unit that was behaving a little bit oddly, but we raised the temperature on the spacecraft and solved that problem just about 2 months ago. So ever since about mid-October, we started exercising this reference observation plan. We say early November because the first few weeks were a little bit not complete, but we have about 20 complete cycles now, maybe 21 as of today, of these 12-day cycles of data. Over 1.5 million products have been produced to date, and everything for the spacecraft is nominal at this point. The pointing is rock solid. The orbit control is great, as you saw from Marco's talk before that. And all the products are being produced in a forward processing fashion as they arrive at the processing facility according to production rules that we've defined for all the different products that I'll show you in a minute. We have joint observations of L-band and S-band over India, the surrounding countries, Antarctica, Greenland, and many other CalVal sites around the world. There's a limit on how much S-band data we can take, but and at the moment, not much S-band data has been released, but the plan is to release all of that data freely and openly, just like the L-band data from ISRO. And if you have questions about it, we can talk about it later. So here you can see the statistics in the top right. Number of images, we make interferograms on the fly, and we're up to over 3,000 hours of operation, and everything looks quite stable. Very high rate of data every day, and we have not really been experiencing much in the way of collision avoidance maneuvers recently. We, of course, have reports every week to that effect, but we do the calculations, and as we get closer to the predicted events, we end up not having to do them. We were quite worried about this because the orbit is near some debris from blown up satellites. So, yeah, so far so good. So here's a global mosaic, and I'm going to show you some more on, well, first I'm going to just say a few words about the plan. We cover all the Earth's land and ice-covered surfaces at L-band every 12 days from the ascending and the descending parts of the orbit. This is the ascending tracks here. The different colors here represent different modes. Most of the Earth is in this green mode, which is a 20 megahertz, sort of 10 to 15 meter resolution image mode. US is imaged at finer resolution due to an augmentation we received from the Office of Management and Budget. The sea ice is imaged in a low resolution mode, and cryosphere land ice is imaged in a variety of high resolution modes to track the fast ice. So this plan is essentially fixed. We image every 12 days for the life of the mission according to this plan. Every 6 months, we do plan to update the plan based on community input, again, constrained by the decadal survey guidelines. So just so that you know, that one mosaic that everyone has been showing was not just a one-off that took 6 months to put together. This is 3 cycles from NISAR, an HH mosaic of the backscatter. Cycle 15, 16, and 18. 17 had some data gaps due to a spacecraft software update, so it wasn't as attractive to show. But what this shows you, I think, is not just within the 12-day cycles is the radiometry quite stable, but across cycles, across a couple of months, it's actually doing pretty well in terms of its stability. White, so down here we see a RGB composite of those 3 cycles where white would indicate that nothing has really changed at the level of what you see here over that time frame. And you can see most of the Earth is kind of white in the north. As you're getting into the thaw season, you see substantial color change. So I think this is a very good indication of the stability of the system. Since we're in Poland, I thought I would put the obligatory map of the area we're in. This is the city of Krakow. We image this area of the world at 20 megahertz, so it's roughly 15-meter resolution. And this is a standard product that you can get from the archive once the data are available. And at finer resolution, it looks quite nice at dual pole. This is a slightly larger area extending further south, showing the Carpathian Mountains and just the beautiful topography and vegetation cover in the area. S-band data. It exists. The system is working. There are, I think, 55 scenes available on the Bunidi interface that are available to the public if you want to check them out. They have both polarimetric, this is S-band only, polarimetric products, as well as interferometric products that they're producing. All throughout the development of the mission, we have been very careful to make sure that the products we produce at JPL and the products that are produced in India are compatible, both in terms of their formats as well as their accuracy and other performance metrics. So I think once the S-band data are released and their joint S and L-band products are released, I think you should see a nice uniform set of products for really exciting science. This is just one example of products that were produced by our Indian colleagues at both L-band and S-band, showing that there's significant differences in the scattering mechanisms at L and S, as we all know, and it will be very exciting to see this natural laboratory around the world of L and S-band polarimetric, interferometric products that we can all use. So in terms of INSAR performance, I think Marco already made most of these points. To date, we basically maintained the orbit to within 100 to 200 meters almost everywhere. We have this quasi-zero Doppler pointing because of the way the system is laid out. The L-band points forward by 0.9 degrees, S-band points back by the ratio of the wavelengths degrees, around 0.3 degrees. And it is really quite solid over the life of the mission. So we have great coherence, as we expect very often. Of course, things do temporally decorrelate, so not always perfect, but not too bad. I think Marco showed this plot already, so I don't need to spend too much time on it. We had the geomagnetic storm in early January, and there was one maneuver that was made in order to potentially avoid a collision, and that pushed us out over here. Some of you may know Francois Rogez. He was one of the authors of ROIPAC back in the old days. He moved on to navigation, and he's a perfect person for it because he knows what we need for interferometry. And this is just another plot showing the statistics of the baseline. All right, coherence is great. I love this image that Haresh's team put together. It's a coherence map over a storm front. I'm sure many of you have seen these kinds of things before. Storm front, this pointer is not working anymore. But, the storm front you can see in the colors on the right from the radar, ground radar data. The thing I like about this is that it's highly coherent on the right side where it's dry. It's also pretty coherent during this rainstorm on the left side. So we maintain coherence because of the long wavelength, the stable scatterers. Even when it's raining, you see good coherence. There's also fringes that are due to the rain as well, which one needs to interpret. Okay, this is a little animation. I'm hoping it's going to start. It's a little hokey and a little bit blurry. This is Germany, where EUSAR was last week. I just wanted to give you an idea for what you can expect when the data are in the catalog. You'll be able to look at browse images of every product that we make. And I just downloaded a bunch of these browse products and put them into Google Earth Engine. The interferometric pairs that you're seeing here are listed on the right side there. And you can just, one by one, look at the quality of the phase. These are not ionospheric corrected. These are just the natural fringes. Some of these are early products, and you have some artifacts on the right. Those will go away in the final released products. But you can see the phase is, over this time period, every 12 days, quite nice, quite smooth. These are all pretty much ionospheric artifacts that you're seeing. There's a nice ionospheric artifact. But really, their complete coverage, good coherence, and good phase quality. So these are the interferometric properties of our products. We've got these geocoded images. We both have the unwrapped phase, as you saw there. We also provide a higher resolution version of the wrapped phase, and we also provide the coherence for both at the two different resolutions. So if you're not happy with the unwrapping that was done and you want to look at it at a finer resolution, there is a layer in the product. You can go directly to it, and it's geocoded as well. So that's a very useful product for some people. If you don't want to go back to the GSLCs, we have the ionospheric model in the product. We have different ways of doing the co-registration. In the polar regions, we sort of do dense offsets to do the co-registration. In other areas, we do polynomial co-registration. We have the coherence layers and the ionospheric phase correction layer and a tropospheric layer and a whole bunch of rich metadata in these HDF5 files. And I've heard from many people who use them that they're very easy to access, and ChatGPT knows exactly how to interpret the file metadata. So don't worry, don't be intimidated. If you want to see what kind of products are over your area of interest, go to the NISAR website. We have a very nice interface where you click on any one of these frames, and you will be able to see the entire plan for the time series and what mode it's going to be in. Some of these areas do switch modes over time for various reasons, but most of them you'll just see a long time series of the same mode over the life of the mission. These are the products, quite comprehensive. The one complaint we get is that the volumes are very large, but if you ask ChatGPT how to subset them, it will also help you do that, and then you don't have to download all these products and just get the layers that you want. I think you've already heard about all these products from everybody already. So here's my summary. Comprehensive in space and time, all weather, day, night, as you know, 24 centimeter wavelength globally, 24 and 9.4 centimeter wavelength in many areas around the world, free and open data policy, analysis-ready products, and we will start releasing the data next month, unless my science team continues to worry about little details. And I am doing my best to get it out as soon as possible. It's fantastic data, and I think you'll all really enjoy it. So thank you.
All right, thank you, Paul. Questions or curiosities? Sang-ho?
Thank you so much, and I can only imagine how much effort there was on all the details, devils in the details, hardware, software. So big kudos to the whole team. In that sense, I want to ask very particular thing that you mentioned, briefly mentioned, digital unit. You said digital unit has a temperature issue. So there was an odd behavior. What was that symptom, and how did you detect it, and how did you increase the temperature? I asked Claude, but he's still thinking.
Yeah.
I decided to ask you.
It's a good question. It's a long answer. I don't know if everybody wants to hear the long answer, but effectively what happened is the firmware on one of 3 digital units had a race condition that we didn't catch because of the sequence of events for the testing. It turns out we had to update the software after we completed final thermal vac testing, and we took a risk that that update would not have this kind of problem, and as with everything with NISAR, that risk was not a good one. We ended up having a race condition. So, and the race condition has to do with the startup. If you start up the data take, the sample shift of this one unit could be one sample one way or one sample the other way. And that's normally okay. If all 3 units were doing the same thing, we could easily fix it. But because we do digital beamforming from unit 1 to unit 2 to unit 3, the sample shift in this unit without in the other 2 units meant that you get a time delay and therefore you get a phase delay. That phase delay then, when you do it interferometrically, if the other one doesn't have the phase delay, or if it does, you get a phase jump in the middle of the swath, and that phase jump in the middle of the swath then screws up the ionospheric correction and screws up the interferometry. So we could fix it for the first 3 months or so. We put Haresh's team put a heroic effort to fix it as best as possible, but in the overlap regions between these units, there's still a tiny bit of a phase residual. The correction was done, the mitigation was done by turning on some heaters that were used for the heating up the mechanical parts before the deployment. They were turned off, and it's a long story, but eventually we figured out that they could be turned back on again, and we turned them back on, and it basically solved the problem. We had noticed through the calibration tones that are in the data that when this happened, the temperature was typically below a particular threshold. So the calibration signals built into the radar were key for diagnosing this and being able to mitigate it. Yeah.
Okay, thank you. I think since it's the end of the session, we can maybe... Right, there's another presentation, but since it's given by Paul, so I think we can allow one more question.
Yes, just a quick question here for Paul and colleagues. Thank you so much for sharing the details. My question is about the orbit files that are provided with the products or the orbit files in general. Can you quickly comment on their accuracy and what we can kind of expect there from the orbit side of NISA?
I think, I'm not sure we have a specific set of analysis that we've done since launch. The plan was we process the data in the forward sense with our medium quality orbit files, which are produced within a day or 2 of the acquisition. That is supposed to be good to a few centimeters, is what they say. And the reason why we're processing with those rather than the final is because in the analysis done before the mission, the difference between final and medium and final was around like a centimeter or so. So the finals will be provided, and maybe they'll be better by a centimeter or so on average, but we don't think it's going to affect anything in terms of focusing and everything else.
So this means we get this sort of, your medium solution is kind of part of the product and is generally shared when the products are downloaded.
Exactly.
Okay, thank you.
Yeah.
I thought there was another question somewhere there. No?
You have to turn your back now? No?
Yeah, okay. Now you have to turn, I'll turn my back.
I think we can start the next presentation.
All right, please feel free to leave if you want to go to the coffee break. I won't be offended. So I'm going to just really quickly summarize these slides so you can get some coffee. This is a presentation by Mark Simons, who's the Solid Earth Science lead. And there's many, many people on that Solid Earth team who have contributed to definition of the requirements and the data. They're very excited about NISAR because of all the attributes that we just talked about. L-band, ionosphere correction, left-looking, 12-day consistent ascending and descending, and time series that they can really exploit. Lots of different applications. One of the things that really excites people about NISAR is the left-looking capability. This is a simulation that was done by one of our team members, where at the top is a simulated earthquake signature in east, north, and up from an earthquake that occurred back in 2019, the Ridgequake earthquake. If you look at the reconstruction of east, north, and up, if you just use right-looking missions, Sentinel and ALOS, and assume you have all the data from that, you get ascending and descending, but you get two vectors effectively. You can't really resolve the north component very easily. But with NISAR added to the mix, at the bottom you can see that the north component is nicely reconstructed. Very exciting to everybody. This Mark included from Howard's work. It takes us back to our CIRC Kilauea data where we looked at L-band coherence versus C-band coherence over a 6-month period. And it just illustrates the fact that the coherence can be quite good at L-band over periods, even over 12 days. C-band can often be challenged in dense vegetation. So having these two complementary systems is just fantastic. Here's an example from a publicly released data set of an Ethiopian volcanic eruption comparing NISAR and Sentinel. NISAR is on the left, Sentinel is on the right. You can see beautiful patterns in this area in both. But if you look at the details as a cut through here, you can see that by virtue of the longer wavelength, when there's really a lot of deformation, you can track the phase perhaps a little bit closer to some of these disruptive areas than you can at Sentinel. But again, two are extremely complementary to each other. Because of this fringe aliasing that can occur, the L-band has some advantages as you get closer to the fault. You can see here a different signature in this profile at C-band versus L-band. NISAR has, as Marco was talking about, we have the standard products, the GUNW, but we also have the GSLC. So you as a user can choose what is the best product for your analysis. The GSLC certainly has the full fine resolution. We also produce a GUNW unwrapped at 80 meters, which is, you see on the bottom, C, that doesn't fully resolve some of these really fast fringes. But we also provide, as I mentioned before, in the GUNW product, a 20-meter wrapped interferogram as well, which will then resolve more of those fringes. So you have a choice, many choices on how you want to approach. And of course, there's the RSLC. If you don't trust any of these things, you can go right back to the RSLC. And if you don't trust the RSLC, you can go back to the level 0B data. Everything that Howard showed started from L0B. So the data are usable. But you should trust these products. They're very good. The ionosphere correction does make a big difference. In this particular feature for the Ethiopian volcano, it's a fairly small feature. So if you look at the bottom left and right, maybe you can't really tell the difference between what's right and what's wrong there. But you can see on the top, before correction, you have a lot of residual fringes that after correction are removed. So it's important to look at that ionospheric layer. We've actually done an interesting study, I wish I had a slide, where we found places where Sentinel and NISAR were observing the same spot at the same time within 5-10 minutes. And they're mostly arranged around mid-latitudes in some diamonds. And compared the INSAR products from NISAR to similarly produced products from Sentinel after the ionospheric correction. And to me, it shouldn't be astounding, but it was just astounding at how similar the phase patterns were. They were both seeing the same troposphere almost perfectly in almost all the interferograms. So it was quite astounding. And unfortunately, there isn't that comprehensive coverage of these similar times everywhere. It's just a very few places, but it's definitely worth looking at if I were you. Okay, so ascending, descending, left, right, this is what is really exciting to people. There's a few examples here. Palos Verdes is a huge landslide. All those multimillionaires' houses are sinking into the ocean, unfortunately for them. But we can look at it with NISAR in the top, left and right, descending, ascending. We can look at it in Sentinel, bottom, left and right, ascending and descending, and use those 4 vectors to reconstruct what the 3D motion looks like. This is, on the left is a zoom out, on the left is a zoom in, and you can see, as you probably cannot see here very easily, but if you compare the INSAR-derived estimates to the GPS, the misfits are pretty good. They're down in the centimeter range. So this is a very nice reconstruction and really is exciting to our Solid Earth team. In terms of requirements, you've heard this, I think, earlier from Franz. We have requirements that are very specific that we need to validate with data, secular deformation requirements, coseismic requirements, and deformation transient requirements. These are documented in an ATBD document, which is published on the web that you can look at, and the algorithms that they were using to create a product and then validate with ground truth are also published on the web. So you should have the ability to reproduce anything that our science team has been doing and suggest improvements if you have any. One of the things that we're doing is computing structure functions. These structure functions basically look at the noise as a function of length scale. And here's an example. On the top left is an interferogram without ionospheric correction, and the structure function below is not meeting our requirements, which I think is the black curve in there, and that's because of the long wavelength behavior of the ionosphere. But after you remove the ionosphere and note the scale change on the axis, you have much smaller residuals, and we actually meet our requirements there. If you look at large areas, you can see on the top, before ionospheric correction, you have, these are interferograms scattered around the world. There are residuals, relatively large residuals. Once you do the ionospheric correction, those residuals lower. And if you do the structure function analysis for these various sites around the world, you can see that most of them pass. A few of them don't pass, but this would meet our requirements because we don't have to pass everywhere. So I think, and this is just the beginning, we still are improving the products. These were from preliminary products, and I think we're well on our way to meeting our requirements. And I think Molly Zebker yesterday gave a talk that demonstrated how well we might be able to meet our secular requirement, which is very challenging, 2 millimeters per year, and that also is looking very encouraging. I think that's it. I think I did that in record time. Thank you.
Thank you very much, Paul, for the second presentation, the bonus one. So are there any questions?
Thank you for staying, by the way.
Is someone? You can scream, so just... We lost the moderator.
Yeah, yes, in the coffee break.
I was just wondering, the ionospheric correction, if you have the S-band and the L-band over the same areas, probably would do even much better, right? Did you try that?
We are all looking forward to getting access to enough data to really play with that. Yes, it's going to be much better. This is kind of what we did in that Kiloway paper in '96. We compared L and S-band, did a ionospheric light correction, even though Circe is below the ionosphere, and could pull out all the dispersive effects on the ground. Right. So yeah, everybody's going to really enjoy that.
And is there an overview somewhere of all the locations on Earth where systematically L-band and S-band are required?
Yes, so that website I pointed you to, if you click on, so you want an overview, not have to click on a frame and figure it out. Yeah, I mean, that map I showed you, we have versions of it with, go to our what's it called, the handbook, the user's handbook, which is also available on our website. It has all the maps with all the modes.
Great.
Comprehensively.
Fantastic,
yeah.
thanks.
Yeah.
Yep.
Something else? No? So thank you very much, Paul.
Thank you.
we started to use it, but we have a lot of atmospheric effects at the moment still. Yeah, feel this, right? So this is something that's a little bit annoying, but yeah, this is something that we started to
basso. Poi? Ah, ferro famiglia. Ferro famiglia.
Good, so welcome back. I start introducing the session. So we change a bit the focus now and go to P-band. So we have the biomass session, the first of two. And you have a bit of an introduction to the mission, to the processors, to our challenges, and to the things we want to do with the data. So Laurent is still checking his phone, so I start the first presenter. It's Michele Caccia that will be presenting on my behalf the introduction to the biomass mission.
Hello, good morning. I'm Michele Caccia, and I work for ESA in Starion. And I'm going to provide you an overview of the biomass mission. So, an outline, we will see the primary science question, mission summary, observation geometry and acquisition mask, and also a quick overview on the data access and tools. So, biomass is is a part of the family of the Earth Explorer missions. Each Explorer mission is focusing in the observation of a particular Earth system part, and the biomass mission is the one aimed for the forest. So, why is important the forest observation? It is important because, as we can see from this graph, there is where we can see the fluxes of the carbon along the years. There is a very big uncertainty on the estimation. And so biomass is aimed to reduce this uncertainty that has been never reduced in the last 15 years. So for the better understanding of the exact amount of carbon and also a better understanding of the land carbon cycle. So what we need to measure? We need to measure forest biomass, height, and disturbances. This information is crucial and needed most of all where we have least information and knowledge, being in the tropics, being biomass, deforestation, and also regrowth. We have a need of this information at the actual scale of this change occurring, so on a hectare scale. We need wall-to-wall measurement and repeated measurement to measure the evolutions. And to be with a 20% of accuracy comparable with the ground-based observation. So let's introduce a bit some key facts of this mission. Biomass mission is the first civilian P-band sat in space, and this band is allowing to have a meaningful response from the main trunk and branches because it penetrates the top canopy. It has a 12 diameter antenna. It is a full polarimetric system, and it has a repeat pass interferometric orbits. This mission unlocks 3 innovative capabilities to estimate the biomass. One of these is classic pulsar polarimetry. Another one is also the interferometric SAR pole. And also, biomass has also the feature to have a complete mission phase dedicated for the exploitation of the SAR tomography. Other mission characteristics are more related to the observation geometry, is that this is a down-dusk orbit with the sun-synchronous orbit. It has a repeat cycle of 3 days, 44 orbits. It implements the smallest west drift to implement the baseline. It has the principal CPMAP acquisition mode with 6 megahertz bandwidth, and it implements the roll for change the SWOT. And it implements a satellite prioritization in maneuver after each major cycle. This means that once the satellite has acquired the SWOT-1 area. Then it implements a role to cover SWOT2. Then it implements another role to go to SWOT3. And once these three SWOTs are complete, it means that the major cycle is complete, and then it performs a maneuver to start covering another part of the globe. So this slide is better detailing this concept. We have, as we can see from this horizontal bar, each horizontal bar is a repeat cycle. So you have the 44 orbits that I was explaining before. For in the interformative phase, we have 3 of these for SWOT1, then 3 for SWOT2, and 3 for SWOT3. When these are complete, the major cycle is complete, and then the satellite performs a repositioning maneuver. And this will allow to cover other portion of the globe. And this is repeated, this acquisition pattern is repeated 7 times to reach a global coverage. So let's talk about the mission phases. The mission phases, the BIMAS is implementing 3 mission phases. The first one is already completed, is the commissioning. It was started in May and finished in November. Then just after it started the tomographic phase in which we are now. It is 16-month phase that is alternating SWOT every 21 days. We do just 1 global coverage, and after that there will be in the interferometric phase until the end of the mission lifetime. It is alternating SWOT every 3 days, leading to 6 global coverage, around 6 global coverages. Let's talk about the current observation mask. This is a kind of news because before the 4th of June, we were having the acquisition mask that we can see on the left side. On the top, we can see the tomographic acquisition mask, and at the bottom, the SRM mask. So the acquisition that are the area of interest where the satellite is acquiring during the satellite repositioning maneuvers. While on the right, these are the updated acquisition mask. As we can see, we increased the acquisition mask to cover in the TOM phase also the full Africa, and we put also a buffer around the border of the coastlines, and also a buffer around the coastline of the Antarctica. While in the SRM, we increased a lot the ocean part, as you can see, and while we moved some part of Africa in the primary objective mask, in the primary mask, so we removed a piece of Africa, but just because of that. And now we can see where BIMAS cannot acquire because of the space object tracking radar system. BIMAS is a secondary user of the P-band, so we cannot acquire in this area that we can see in this slide. And this is an example of the coverage of the mission within the major cycle 3 SWOT3, which is the current SWOT cycle. And this is more or less what BIMAS is acquiring during this SWOT cycle. Here we can see where we are placed currently in the acquisition timeline. As you can see from the mission timeline web page, we are currently almost in the middle of the repeat cycles 5 of the SWOT3 major cycle 3. So now I'm going to provide a very quick introduction to the products, but more focused on their availability rather than their specification. So more focusing on the products that are currently available. So for the regular user, we have a regular processing of the level 1 products starting from the beginning of the tomographic phase. Then we have a regular processing of the stack processor from the end of May, and now we are going to do a retroactive processing starting from major cycle 3. And then we will go back in time until the first major cycle of the TOM phase. And this is a similar availability also for the level 2A because they are derived from the stack products. And then we will have the level 2B products available just after the completion of the tomographic phase because they are global products. So now we can see a little bit of how the people can access to the data. There is the catalog web client, the Map Explorer. You can see also here the link, where the user can access, download, search and download the data. The catalog web client, there is also an API version in which you can exploit the API to still to search, discovery, but also read the data. And you are very welcome, invited to raise any issue on data availability, on data quality through the AO help desk that is available at this website. A very important piece of the ground segment is the biomass disk service. The biomass disk service is the data innovation cluster. This is an integral part of the ground segment, and it is responsible for the mission product quality and also the algorithm evolution. If you land on the biomass disk info website, you can see all the release notes of the processor, the quality disclaimer, forum link, FAQ page, and so on. The disk also acts as a primary scientific interface between the user and the biomass ground segment. So when a people is asking for something in the portal that I was showing in the previous slide, disk is in the middle to filter and to better assess what kind of request is arriving and to properly direct to the relevant team for the fix or for the reply. The feedback, as I was saying before, are very welcome. It is also invited to be specific in the description so we can better help and support you. And your feedback is very welcome because it can allow us to further improve the product quality. A very important piece of the ground segment is the MAP. MAP stands for Mission Analysis and Algorithm Platform, and this is the way the people are encouraged to analyze and exploit the data. We have also already seen before the part of the data access, but MAP is also a collaborative environment where people can land, can open data, can analyze data, can do prototyping, can run in batch processing, and can visualize and make an analysis on the results. As you can see from the bottom arrow, the people on the top can access both to data access and the map in a very independent way. But there is a link between the environment and the map that eases the access and make it also very faster because they share the same infrastructure. So people can have a quicker access through the map to the data. So if you let me spend few words about the product algorithm laboratory. It is an environment for the data management, algorithmic execution development, result visualization and analysis. It comprises three main parts. The coding part where people can have a sort of Python notebook where they can do algorithm development, prototyping and containerization. While for the processing, let's assume that you have already done your processor, you want to run it on bulk, so for a very huge amount of data, you can do it in processing. And then you can, in the visualization part, visualize the results and also make an analysis. Let's conclude this presentation with a list of relevant resources for the biomass. As I was saying before, we strongly encourage to use MAP. There is the open source for all the processor and tool for the data exploitation available in the biomass GitHub. There is the biomass website, the forum, the disk, and there is also Pulsar Pro Python that is also available in the map. So the message is there is a lot of data, even if we are halfway of the global coverage of tomophrase, we have a lot of available data. So please play with data and let us know if anything can be improved. Thank you.
Thank you very much, Michele. Are there any questions? No, I cannot ask a question because I know the stuff. Also Laurent, so maybe then we can move on and recover the delay of the coffee break. So thank you very much, Michele.
Okay.
So the next paper will be presented by Stefano Tebaldini from Politecnico di Milano, and it will have to do with the ionospheric effects in the frame of the biomass mission.
So, yes, thank you, Laurent, and good morning, everyone. So before I start, I gave this same presentation last week at Oyster, so in case you were in Baden-Baden, you can be less interested than expected, so no problem. Ionosphere. Now, I think that one of the first things to say about biomass is that it is an interferometric mission. I would like to be brave and say that it is the most interferometric mission ever launched by ESA, because it has product generated by ESA that comes from interferometry. So this means that there is an internal processor that is a full interferometric processor, so that starts from the raw data and goes until calibrated interferometric product, and then it generates level 2 product out of this. And this touches forest height, AGBD, forest disturbance, DTM, tomography, ice. So interferometry is everywhere in biomass. And keep in mind, it's not that ESA delivers the data and then the users do their interferometry. No. This time, ESA goes full monthly. And so they decided to do it all, which was a very brave position, in my idea. And it is even braver because we are at P-band. And at P-band, ionosphere is a mess. So if you have some experience with ionosphere at C-band, forget about, really. You see the sensitivity. So one tech unit at P-band is 40 radians of phase error. And this is not a constant. This is something that changes in space and time. So we need to account for this. Now I'm speaking too much, so I need to be faster. Just to recap, we have phase errors like this. This on top is an interferometric phase that you need to compensate. We have co-registration errors because of the azimuth shift. Again, this is something that you need to compensate. And in some cases, the ionosphere is so bad that you have defocusing. It means that in one pass, you have some kind of defocusing. In another pass, you have a different kind of defocusing. So when you form an interferogram, you have two different defocused images. And so you have coherence losses that you cannot recover simply by co-registration. So this is the case I want to discuss in this talk. So differential defocusing. It is super relevant because so it is not an academic study. This happens all the time in Antarctica, and you can say, okay, there is no forest in Antarctica, so it's not super important, but it happens all the time in Siberia, and Siberia is a super important area for biomass. It would entail a major degradation on all the level 2 products, so it's something very important, and it is an uncharted territory. There is no literature about this, because with split spectrum, you can correct the phase, but you do not correct the focusing. With co-registration, you cannot correct the focusing. You can think that you can do an autofocusing of single images. This can work to a certain extent, but keep in mind that working on single images, you will never have the accuracy that you need to correct an interferogram. So we need to do a sort of interferometric, we need an interferometric approach. And the methodology I want to discuss today is based on multi-squint interferometry, which basically means that we focus different looks. So basically we observe the same scene under different squint angles, so like this, and so on. And we form interferograms for any squint. Now, if the wave crosses different ionospheric layers, assuming straight ray propagation, which is not true, of course, but it is a decent approximation, then the phase that is accumulated as the ray crosses the different layers is given by this expression. So basically, it accumulates a phase for each layer that is crossed by the ray. And this means that if you analyze this phase in the azimuth and squint domain, it means that the phase has a particular signature. So if it's ionosphere, it has to be characterized by this characteristic slope. If it is the target, so if it is a geophysical phase, like due to topography, it has to appear in this way because the topographic phase doesn't depend on the squint. If it's mixed, then it appears to be mixed. And interesting, if you do a Fourier transform of the phase in the, so you pass from azimuth squint, you do a 2D Fourier transform, then you have that the ionosphere transforms to a line with a certain slope, and the geophysical phase, so the topographic phase, transforms to a line that is flat. If you have both, then you have both lines. And this will be the main analytical tool that we use to analyze the data. Some example, here we have data from Amazonia collected in the COM phase, so with an extremely short baseline. We have a height of ambiguity of kilometers here. Here you have, so on the left, phase and coherence of the data as they are. So we simply co-register them based on the orbit and on the knowledge of a prior them. Estimated range and azimuth shift. And this is what you get if you do a database co-registration. So as anyone else, we simply cross-correlate so that we find the shift and we adjust the slave onto the master accordingly. So in this case, coherence is fully recovered. This is a super coherent interferogram. And also, if we just remove a phase plane, I would say that much of the phase has gone. So in this case, the standard, the traditional approach to interferometry works beautifully. This is the phase in the squint and azimuth domain for a single range, of course. So you see that it has a particular signature, so with a particular slope. Do not focus on the blue line, that is an RFI, so we don't care about it. You see that the coherence in any squint is very high, so this is a typical ionospheric signature, which is compatible with a single layer at a height of some 330 kilometers. Now let's go to Central Antarctica. Again, data from the COM phase, so the baseline is super short. It means that we expect no phase at all. The interferograms I'm going to show are obtained at the 3 days time separation. In this region, there is no relevant motion. That is to say that there's no reason in the world why an interferogram at 3 days with 0 baseline here should be decorrelated. But it is. So this is the interferogram phase and coherence of the data with orbit-based co-registration, estimated range and azimuth shift. Okay, we can say this is ionosphere. Let's try to compensate for it. Even if we co-register, we cannot correct for this. And the reason is that the ionosphere is so strong that it's not just the shift and the phase, it's the focusing. So this is what we need to account for. Let's take a look at the phase in the azimuth and squint domain. Maybe before the phase, let's look at the coherence. So the good news here is that whereas the image, so whereas the interferogram is heavily decorrelated, if you process the data with sublux, it means that resolution, spatial resolution for any sublux is like 300 meters, so it's very coarse. In this case, we recover coherence. And why? Because the focusing at the scale of biomass resolution that is 8 meters is relevant. At the scale of 300 meters is not. So at this scale, we have coherence. And if we now take a look at the phase, you see that there are slopes, so it's characteristic of the ionosphere. And if you squeeze your eye, you can see that there are different slopes. So quite likely we are in presence of different layers. And this is the Fourier transform of the phase. You see that we have a sort of a butterfly figure because we have an ionosphere that maps to different height, basically. By the way, based on this process, we can also do a tomographic reconstruction of the differential ionosphere, but this is another story, so which I prefer to skip. So this is more or less where we were 1 year ago after the first biomass acquisition. And so we understood that we needed a new paradigm, basically. So we couldn't do interferometry in the traditional way. And basically, we had two aspects to take care of. The first is inversion. So how do we estimate this multi-layer ionospheric propagation? And the second one is correction. So after we know it, how do we correct it? Now, I will be fast here. For the inversion, we set up a sort of a phase linking algorithm. So basically, let's say that we try to apply this model, assuming a single layer, and we estimate the best fit of the ionospheric phase for a single layer. Then if we are not happy, meaning if the residual is still important, then we put in a second layer, and then a third layer, and so on. The beauty of this algorithm is that it works on complex coherences, so it doesn't require a phase unwrapping. The downside is that the solution is not unique. Why? You see this again very clearly in the Fourier domain. Let's say that you have two layers, and you want to understand which is the ionospheric phase of the first and the second layer. So, since they are two lines, you simply need to read the phase along those two lines. Beautiful. And you can separate it perfectly, except in the center. But as a matter of fact, this is ideal because biomass has a finite angular aperture. And this means that you have a resolution in the Fourier domain that is not represented by the two lines. Actually, the two lines become fat, so it's sort of two shapes. And you can see that in the central region, so where the two intersect, we simply cannot tell if the phase is due to the first layer or the second layer. So for high frequencies, we can separate. For low frequencies, we simply can't. And this also involves the target phase, so the topographic phase, the geophysical phase. So it means that we have an ambiguity about the low spatial frequency component of the ionosphere with the low spatial frequency component of the target phase. Having said that, how do we correct for it? We set up this algorithm, which we call sub-band refocusing. It's pretty simple, actually. Let's say that you split your image in many subloops. If you do not undersample, then you can restore the full image, the original full resolution image, simply by coherent sum. So the idea is simply to correct the phase of each subloop. So we counter-rotate and then sum. As simple as that. It is not an exact approach, but it is decently accurate and decently fast, so we like it. We go back now to the real cases. In this case, we have on the left phase and coherence after database co-registration and the removal of a phase plane. So on the left, you have the conventional approach. On the right, you have this method. In this case, up to a phase offset, I would say that they perform the same way. So for this case in Amazonia, there is no really need for this machine. But if we go to, okay, this is another case with a long baseline, so which is representative of what we have in the tomo phase. In this case, we have some, well, the same coherence, some advantage on the phase. You see that this multi-squint method can actually understand that this part of the phase is due to the ionosphere and correct it. This is an acquisition over Australia, close to the biomass transponder. In this case, you see that we have some coherence losses because of the focusing. So not just in Siberia or Antarctica, even in Australia, this can happen. And now you have so those coherence losses are corrected with the multi-squint approach. The phase has improved, it is not perfect. Okay, I told you that there is a low pass residual. Back to Antarctica, or in this case, we have the multi-squint phase, so azimuth and squint, and this is the residual. So basically on top right, we tried to estimate the phase with just a single layer. We took a look at the residual in the azimuth and squint plane, and this is what we get. So as long as we see residual phases, we try to inject a new layer. And for this particular case, I think that we had to estimate, to use like 7 or 8 layers to really explain this phase, this observed phase. And this is what we get. So the interferogram, coherence and phase with database registration, and the interferogram with this method. So coherence now is fully restored. I tell you, there is no baseline, there is no motion, so there is no reason in the world why this interferogram should be decorrelated. And indeed, after this processing, we can restore it. The phase, again, it's the ambiguity about the low frequency components that I mentioned. Northern Russia, so I can go faster, just to say that, again, it is the same case, so we cannot do interferometry over Siberia without this method, whereas we can recover the coherence losses in this way. So to sum up, we set up a big machine. So basically the processor now splits the image in several looks. It does interferometry for every look. It fits this multi-squint, this multi-layer model, and then it does this correction by sub-band refocusing. So it's big. Do we need it? Well, in Amazonia, going for a multi-layer correction is definitely overkill based on what we saw until now, so probably not. But if we want to go to Siberia or Antarctica, we definitely need it, so we cannot live without it. The downside for the time being is this ambiguity about the low frequency components, so we need to inject some other information like a split spectrum or Faraday rotation or some prior maps. This is a work in progress. Let me say that, luckily enough, all the biomass products are based on the phase difference between the terrain and the vegetation. So even if there is a low-pass phase screen, it doesn't impact on biomass product because it goes away when we take the difference between the terrain and the vegetation. So for the time being, we are happy, although there is a lot to do. And this is it. Thank you.
Okay, we have time for questions. There are some. Yes, please. Oh, okay.
Basically, the orbit is a down-dusk orbit, so it minimizes the effect of the ionosphere, I mean, in theory. But then ionosphere is quite tricky, and even though it's a down-dusk, you can encounter such things as plasma bubbles or plasma blobs. So do you have any signature, or have you spotted the signature of plasma bubbles or blobs in the data?
Maybe yes, but I think it is a speculation at this point in time. Let me say that we are about to start a study within the Biomass Plus program with ionospheric physicists, just to help us interpret the signature in terms of the physics of ionosphere. So maybe we will. Thank you.
Okay. You had a question?
It was a similar question, actually. You said that you're happy, but there is a lot to do. I wanted really to understand there what do we need to do? Because what you should
Why I'm happy, or why is there a lot?
No, on the second bit, that there is a lot to do. So is it more like we need more atmospheric physics or something else?
Both. I would say that now we have two search directions. First, I mean, we can recover coherence. Coherence is okay now, and this is great because all the primary products leverage coherence. But we need to get rid of these low pass phase residuals, especially for the DTM product. So much of the research now is focused on, say, injecting other information like farther rotation or the split spectrum to try to mitigate this residual. So this goes in the direction of data correction. And then, as we said, we are starting to work with ionospheric physicists to derive an ionospheric product.
I want to know in general, there are much more things to do in biomass, as you will see in the next presentations, but this is the ionosphere aspect.
Okay, thank you for your presentation. My question or comment is more or less related to the previous question, and you already partially answered it. The first question is if you have any physical interpretation of different layers, I mean related to the different regions of ionosphere, and say without diving into the ionosphere properties, besides the latitude, it is also important the acquisition time, because by night the solar activity is less relevant. So do you have any comment about this before, entering the physics of ionosphere?
So let's say that for the second question, we see ionosphere everywhere, more or less. Yes. Every time, everywhere. Maybe we don't have statistics, but let's say it's always and everywhere strong enough at high latitudes to trigger this correction. And the first question, I just forgot it. Layers, yes. Well, okay, so yeah, I'm not an ionosphere physicist. Let's say that yes, it is compatible with the different layers. I think it's fair to say that the ionosphere is actually a continuous distribution. So this is for sure an equivalent representation. It is just instrumental in terms of correcting the data. The second thing to say is that those are frozen layers. If we have some, say, just a single layer which moves fast enough, this can give you the effect of multiple frozen layers. And this is an ambiguity between space and time that we cannot solve with a single satellite. So it might be that if we inject a motion model that is physically based, then we can reduce the number of layers. But of course, we lose because we increase complexity on the other end. So.
Thank you very much, Stefano.
Thank you.
The next presentation will deal with the biomass interferometric processor and will be presented by Muriel Pineiro.
Hi. Good, so now I'm going to try to talk a bit about how we actually implement all this beautiful processor that Stefano was mentioning in the ground segment of ESA. So first, a brief overview on what is actually our product family related to the primary objective. So Michele already showed this a bit before. So basically we have our raw data, which is then transformed in level 0, which right now it's available for selected users only. And from that up, we have our free products. Basically, we have our level 1 products, which are the normal SLCs, and also our ground projected detected products, so the level 1B. Then we have the level 1C product, which are the stacks, which are either this blob of 3 or 7 images, depending on where we are in the mission phases. And from that, we derive our level 2 products associated to our forest primary objectives, which are in the level 2A case, our ground notch product, which is the main entry point for the retrieval of AGGB, the forest high products, and the forest disturbance. Then we have our level 2B families, where we go away from the satellite geometry and we start to put things together from ascending, descending geometries and combining whatever we can. And we derive our geophysical parameters, so the AGB, again, the forest height, but combined, and the forest disturbance. We are now working together with CESBio and Polimi and Alesis and everyone else to also consolidate our level 3 products which are supposed to ensure the consistency between what we are seeing in AGB and forest height. And this will only be produced after we finish with the validation of the level 2s, which is currently ongoing, and we managed to actually place this in production after a few cycles. We also have secondary objectives, which is very interesting for this conference in particular. So these are also products and processors in which we are currently working on to complement the existing processor suite. And we have there the DTM, so the digital terrain model, and you have a presentation about this in the second biomass session. We are working to derive a forest-non-forest mask from the tomographic phase, which is supposed to complement the forest disturbance map and also serve as an auxiliary product for all the other level 2 products that we are generating. And interestingly, we will have global to what biomass C, tomo cubes, which will be then ready to be used by people to try to derive things from. These are all being done in a project that we call Biotomex, which is pretty much involving all the team that is presenting here today. And the goal is to try to do soon a demonstration with the data from the tomographic phase, targeting to be ready in the next year to the global production of these products. Besides these secondary objectives, we also have the additional products that we want to look at, and in particular the additional domains. So as Stefan already anticipated, now we start several biomass plus activities where we are looking at different aspects of the mission, so going away from the forest into ice, deserts, and oceans. So a bit about the characteristics of our product family. So I'd like to first point out that all the product description, the documentation of the algorithms is all available online. If you go to the biomass product page, and in particular, if you go to this QR code that I put here, you will find the documentation defining the products, defining the product specifications, and also defining the ATBDs, which should hopefully be compatible with the processors which are all publicly available. So just in short, as I say, the level 1A is our single look complex island range data. So this is simple range radar geometry and zero Doppler. The resolution that we get with biomass, it's about 20 meters by 8. And if you go to the level 1B, of course, everything is configurable, but the default configuration that we have right now is providing beta naught in a resolution which is about 50 meters. And then we have about 6 looks. With that, what we use then to derive our AGB products, and what we can use to derive our AGB products or whatever you want to do with it. And our stack products, so the processor is also very configurable, but the default configuration we will get, depending on the mission level, the mission phase, we will get either the 3 images stacked together or the 7 images stacked together in the case of the tomographic phase, all calibrated, that Stefano pointed out, and hopefully ready to use. There was a little bit of a change, well, a lot of changes since we launched, but one of the major changes that we did is that we were initially producing stacks with 3 polarizations only, so we were merging the cross-pole components, and at some point we decided that was not such a good idea, especially because of RFI, which is very non-reciprocal, and then we started now, since the last processing version, to also deliver the stack product with the 4 polarizations. This is about how the product is framed. So what you can see here, it's one of the first images that we acquired in the commissioning phase still. And here you see the data take, which is a longer stripe of data. When we actually go about processing this thing, we define the level 0 slice, which is about 750 kilometers long. And we further cut this down into what we call frames, which are then used to process our level 1 ABC products. And in the end, the frame that you will be able to download in data access, it's about 21 seconds long, which is about 140 kilometers. Just to point out that right now the IOC products are still not reprocessed, but we are working on that right now, and once we finish with the reprocessing, this will be available to the public as well. There is also an ongoing discussion about if we should actually try to enlarge the area that we are processing together, and this is related to the fact that some of the components that we try to correct are a bit slow-varying, and sometimes we end up with calibration which is not entirely consistent between the frames. I put here an example from a user request, actually from David Becker, that was pointing out that we had a bit of a cut when you were going across the frame. So this is something that we are looking at to see what we can improve in terms of the processor, but also we are discussing if we want to process more data together instead of the 20 seconds frame. Then going to the product, this is a relatively recent image over Antarctica where you can see beautiful ice and sea ice. And I just wanted to show you how the product is organized. So pretty much we have a folder which is containing several subfolders where you find the annotation, some navigation data, the measurement layer where you see the actual TIFFs containing the data, which are organized in absolute and phase, not real and imaginary like we have for Sentinel one. And we have the preview with the quick looks. Right now we are providing RGB and hue saturation and value quick looks for you to choose from. In the metadata and the annotation, we provide the relevant information from the processing parameters, some quality information collected from the data, and also the list of all the lookup tables which are available to auxiliate the processing. All the files can be accessed through the API that Michele already pointed out, and you can access individual files within this folder as you wish and need. I just show here there is this border artifact that is something that we have corrected already, but it reappeared. So this is a bug. This is under correction right now, and the fix hopefully will be available quite quickly. Then if we go to the level 1C product family, so these are 2 images acquired within 3 days, and the interferometric coherence, that in this case is quite high because everything was nice. If you actually look at the folders at the product, you will see that they look a bit like the single look complex folders. So each image is actually on a separate folder, and there you can find information of the primary that was used to coexist with all the auxiliary layers which were used for the processing, and of the secondary, and then also the information that comes along with it. You can see also the annotations where you can find relevant information from the processing, how the coexist data has been done, what are the parameters of the calibration. And there is some metadata that should support you to understand how the stack was built, in particular to show which was the primary image which was used, and what is the identification of the stack so that you can put these separate folders together. And all of these are queryable metadata that you can find in the data access. Here is just a little bit of a demonstration of what is inside the folder. So right now we have quick looks for the coherence and the phase, and some statistics showing the statistics of the coherence, and as well as a text form histogram of the coherence. Then going to the actual processing steps, so we have 2 main chains, the level 1A chain that is doing the SLC and also providing some corrections, and then the level 1C. For the level 1A, we have, let's say, worth notice, the antenna pattern compensation, which is a bit different because of the reflector. We have RFI correction, which is also one of the main challenges that we face, and the level 1 part of the ionosphere calibration. RFI has been a big challenge since we started acquiring data. We have different methods to try to mitigate it. Right now, we are using a frequency domain based as per findings of the IOC. We try to do the different channels in a consistent way so that we impact little the polarimetry. But we are doing the correction at level 1 level, which means that when we put the stack together, this is not consistently correct, which can have impact in the interferometry. This is just an example of data before and after RFI correction. And as I say, we are still not fully happy with the RFI correction. So right now we go for a more conservative approach where we are using a spatial mask to activate this correction, which right now it's pretty much on everywhere except on the areas of the primary objective, so except in South America and in the tropical forest in Africa. All the information, it's available in the DISC website, and if you want further information, you can always ask me as well. This is a slide on the impact of RFI interferometry. So of course you see this interferometry as well. So here on the left you see some interferograms with some coherence degradation due to RFI, and you can see very well that it's quite different in HV and VH. And this is what we get after we try to correct. So there is a clear improvement, but as I said, this is not done consistently in the stack, and that can have some impact further down the line. So we keep working on the RFI. So currently the DISC is working on the evolution of the RFI correction algorithms, and we will be trying to look at how this can be better done in interferometric level at some point. For the ionosphere calibration at level 1A, basically we have Faraday rotation, and we also try to estimate an initial phase screen that is then used to correct for range delay and the phase screen at level 1A, and that then it's kind of improved at level 1C, as Stefano already pointed out. In terms of process inversion, it has been a very long road since we launched the satellite, with several processors being patched and updated. We now sort of reached a semi-stable status, and the major evolution has been really in this last version, where we put together in production the algorithms that Stefano was just showing in the presentation before. We also have some minor updates in the calibration steps. We have added lookup tables, and hopefully all of this is visible in the DISC website in the releases notes. So the overview of the level 1C processor, so pretty much it's described here. We have the pre-processing that it's dealing with the geometrical quantities and the selection of the primary image. Then we have the co-registration, and then we have the calibration steps. Right now we are doing the multi-squint calibration as proposed by Stefano, and SKP phase calibration to do to get the ground and to remove the residual disturbances. For co-registration, we have a few options. Either we can co-register based on the known geometry only, or we also use, in addition to that, cross-correlation, which is the default option used in production. You also have an automatic mode that tries to ignore the database co-registration if that's not passing some quality criteria. We also have implemented split spectrum, traditional, but then also using all the baselines, but it has been seen during commissioning phase that that's not very useful with respect to what is there in level 1A, so right now it's not being used in production. And then the main calibration module is the multi-squint calibration, as just presented by Stefano. So this here is the diagram version of his entire presentation, which is right now in production. Just to say that there is all these tests that are done happen inside the processor itself. So right now, the default configuration, we actually let the processor decide, given a threshold, if it should attempt the multi-squint calibration or not, or correction or not. And we are now in the processing of collecting statistics and seeing if we have to tune these thresholds and if everything is working as expected. The final calibration model is SKP. So here we are trying to estimate the contributions due to the ground scattering and also the residual disturbance, so these lower pass components that we are left with. So here, traditional flow, we do the multi-baseline polarimetric covariance matrix. We try to get the most coherent mechanism out of it, and we are left with something at the end that's giving you information of the ground steering phase and the phase disturbance component that's left at the end. By default, this is right now done at 300 meter scale, and it's not applied to the data, but it's provided as a layer. This is the repository of where all these processing components that I was talking about are available, in addition to some supporting tools that you can use to try to play with the data yourself. We also, as I said, have some supporting tools to actually visualize the data. This is nice because the data contains a lot of information, a lot of lookup tables and statistics, so sometimes it's useful to have some sort of analytics that help you understand the data. This is also available in the repository, and it can generate plots, quick looks, and reports for you to assess the data. Then to finish my presentation, this is my last slide, just to say that a bit of advertising. We have upcoming now a hackathon that will happen in the beautiful town of Darmstadt in Germany. And we are really encouraging everyone, in particular students, to participate. And the focus there is to look at some challenges, also with new technologies, machine learning and so on, to try to solve some practical biomass problems. And we also will have a webinar for BioPow, so showing these development tools and processes that we were discussing about. And here you can find information of these things in these links. And that's it. So thank you very much.
Thank you very much. Do we have some questions? Yes, please.
Well, are you sure about the date about this BioPal developer onboarding webinar? Because I think it's...
This slide was done by cloud, so...
Okay, because in the email there was 30 of June. Okay.
Maybe this one is the one open to the general public.
Maybe.
Thank you. Any other questions? And Marco?
So, Muriel, you mentioned that the split spectrum technique was not successful or was not promising, but
it's not that it's not successful, it's more that it's not useful. The point is that we are already doing a sort of phase screen correction at level 1A, and this is already removing part of the slower varying component of the ionosphere. Since we have a very small bandwidth, when you go to split spectrum, we have to sort of, I mean, it is lower than what you get in ICER, for example, and then it's not bringing too much advantage with respect to what is done in level 1A to start with.
Understood. Okay, thanks.
Any other comments or questions? Okay, no. Thank you very much.
Good, so we proceed with another challenge of biomass related to the changes that we have in time, with a presentation given by Irene about the polarimetric effects in P-band interferometry phase triplets.
Okay, yeah, thanks very much for this introduction. So it's a little bit a different topic now. So we are coming now in the exploration of the data using interferometry, specifically the phase triplets, but also including polarization diversity. I would like to acknowledge my co-author, which have done actually the main work of this presentation, which is Noelia Romeo-Pugh and Kostas Papatanasiou, and I would like also to acknowledge Paul Prats for his very enlightening discussion that we had during this process. Okay, let us start with an image of a tropical forest. So that's an image of a tropical forest that you can see. And we need to, in principle, to think or rethink a little bit how we are dealing with longer wavelengths. It's clearly with longer wavelengths, right? We are not anymore only sensitive in very dense vegetated areas, only on the canopy itself. But here we have mainly also contribution from the ground. So we are assuming, in principle, to have equal contribution from ground and canopy contribution. This is something that you potentially can already also see in this image here, where we have a parametric image, an intensity image. The green is representing, in principle, the volume scattering. And we see already we have a river channel on it, and we have also some scattering, different scattering around this river channel, potentially dihedral scattering. If you go now in time, and this is what you see over the intensity, so this is now images from end of May until mid of June, and we see they are looking quite similar. We have on one of these, on the 29, you see some stripes, so still some RFI issues, but in principle, all of the rest of the images look quite nice. So let us have a look to the interferometric coherences here. We have selected interferometric coherences, or let me say this data set is from a very, very early COM phase, because here we had 0 baseline, in principle, acquisitions, which is very important in order also to investigate the phase closures. So when we now look just to the interferometric coherence, and this is now the 3-day coherence and HH polarization, what we see is actually a change, right? We see much more patterns than we would see, or that we see in principle in our intensity image. For example, the patterns here on top, you see it, they're changing with time. These are patches, darker patches, which are decorrelation patches, potentially done or potentially occurred due to rain events that we see here. And we have also these sub-canopy flooding events, which are very close to the river channel. So we are assuming that this is coming from a different stage or gorges in principle of the river itself. So the water level changing during the time that we see here. What is now interesting, if we also look for polarization diversity, so we are just doing now an RGB of red, green, and blue, where the red part is in principle the HH polarization, we see that suddenly it's popping out. So our assumption that we see also the ground is very clear here, so very strongly below the forest, because we have very, very strong scattering of these dihedral on HH, which is in principle an indicator for dihedral component. We see also in blue the VV polarization and a little bit in green the HV. Okay, the question is now, can we separate, or can we say what is changing here? Is it the scattering mechanism that is changing? So that's a little bit the question. So what is really changing here? Do we have a, let me say, a change of scattering mechanism, or is it something else? And how we can, in principle, investigate this is using the phase closures. So in this case, what we do a combination between the first image and the second image, the second with the third image, and then the third image with the first image, in order to have a phase contribution where, when we would have no scattering differences, so relative changes between the two scatterers, which we assume to have, which is the volume and the ground, then in principle the phase should be zero. So let us check this. Do we have zero phases over forested area, dense forested areas? And we can see, no, they are not zero, but they have either they're positive or they are negative, which means in principle this is a strong indication that the scatterers within, so the relative, the scattering processes relative are changing to each other. If we now look in time, we see that we have different patches, so they are even changing with time. So the relative changes of the scatterer, ground and volume again, are changing also in time very strongly. We see it over these patches where we have said these are rainy events, and the other one close to the river. So how to interpret this a little bit? So as said, the forest we assume to have two main scattering contributions with the volume and ground, and this is what we see here in the sketch on the upper plot. And we are assuming to have a reflectivity function here where we have a ground contribution and here the volume where in principle the, sorry, okay, yeah, it doesn't work anymore. Okay, where we see that the volume and the ground actually have a certain amount of a distance, but also a certain amount of intensity. If you look now when we have suddenly flooded areas, so we have water beneath the canopy, then we see that the position of these two arrows that you see here in the green and blue, they are changing. So the relative position is changing, so this means the phase center height is changing, but also the intensity is changing, which means the strength. So in this case, in the second part, we see that we have a much stronger contribution from the ground. If you go now even with higher levels, water levels, then we see that the ground is getting a little bit weaker and that we have a kind of closely same contribution from both parts, but also the distances to each other are changing. So this is what we are talking about, the relative change of the scattering mechanism. So this is happening when we have flooding events. But what happens when we have rain? So we are not seeing really the rain itself in the atmosphere, so this is not what we see, but what we see is a change through the scatter, through the propagation into the volume itself. And if you look now again to the first part of the image, we assume you have a medium day, so we are starting with something where you have a certain volume decorrelation and therefore a certain position of the phase center of the green arrow to the position of the ground. And if you have now rain, what is happening actually is that the error, so the propagation of the wave is changing because we have a strong attenuation due to the rain in the canopy itself, and therefore the position of the error is moving up, so we have in principle stronger differences between the ground and the canopy height. And if you have very dry condition in the lower part, we see we are coming closer together, so this means we are getting also more contribution, a stronger intensity of the ground contribution. So this is in principle how we can interpret these kind of images. So this is now in HV. Let us have a look, do we have also changes in other polarizations? And if we go now to HH, yes, we have also changes, and the changes are differently. So the relative scattering changes are differently displayed in terms of intensity, or here in this case in terms of the phase structure or the patches that we see in the phase. And if you go to VV, again, we see some differences over these two parts. Okay, the question now here is, can we identify where the changes are occurring, either in the volume or in the ground, and how does these changes that are occurring reflect the different polarizations? I mean, that would be also very interesting. In order to do this, we need to separate actually ground and volume, because otherwise we don't know how to separate them well, and what contribution do we have from each of these parameters. Therefore, we are moving the test site in order to now allow to have spatial baselines. Before, we were looking to zero baseline. Now we have a test site with spatial baselines. It's the same. It's a tropical forest, a very dense tropical forest. Here we see it in Peru, where we have also a river channel crossing, in principle, the scene. Below you see, in principle, the baselines, in principle, or let me say the acquisitions that we have with a 3-day repeat. So actually in total we have 10 acquisitions, but we use the 3 and then the 4 because they have an equal baseline distribution. So we try to have the same baseline variation for each of the scene in order not to involve a lot of volume decorrelation with changing baselines. So therefore the baseline is the same for each of the scene, which is around 0.05 capacitor. Okay, let us have a look how these coherences look like. Again, it's very similar of what we have seen before. We see some patches here, so it's clear the total coherence is a little bit lower because now we have also volume decorrelation because we are introducing baseline, and if you introduce a baseline, you have also a contribution due to volume decorrelation, so this is what we see. But in addition, we see also again patches over this tropical forest. Here very well seen in the beginning, but also very well seen then in the later scenes. Okay, that's again, you see the rain patches here very well, these bigger patches, and then yeah, you see them also in the different polarization channels, which is also now here and displayed in this RGB. Very strongly also in HH polarization, but also the other ones. Okay, let us now look how we can separate, right? I said we need a spatial baseline, that's one thing, and the second thing is what we need is a model in order to try to decompose really, or in principle to model first these two contributions, so the volume and the ground layer. This has been done by a very established model that has been last decade developed, I would say, quite a long time ago, which in principle, what we are doing, this reflectivity function that we have seen before, is in principle modeled as a volume layer and the ground layer together, so added together, and in terms of polarization diversity, which is here our W parameter. So if we use these profile, which is a vertical reflectivity function, into our coherence that you see here, then in principle we can model the coherences for each polarization, where we have now two contributions, the volume and the ground. And this we do this in this unit circle that you can see here. So on the blue line, we have all this contribution of ground and volume together for different polarization contribution, and then what we do, we fit a line out of these coherence points and look on the outer border of this unit circle. So like this, we can in principle estimate the ground only and the volume only contribution and everything that is in between, which is blue. Okay, how to do or how to correspond this now with the triplets, right? Because that is where we started from. So triplets, how we generate them is clear using interferograms. So we do interferogram 1 to 2, 2 to 3, and 3 to 1. And then what we do out is a product which we call then the cyclic triplet phase. However, we can do the same using the coherences, because the coherence is a complex measure. We also do the coherence combination 1, 2, 2, 3, and 3, 1. And then we do also here the outer product. So we have in principle the coherence and the magnitude, but also the phase information. Let us check if both are the same. Both will be the same if you have the same multi-looking applied, right, at each of the stages where you do in principle multi-looking. That's very important. And like this, we see that's for the triplets as an example of the phase, now the triplet phase. And this is the phase that we have developed, or let me say, generated from the coherence triplets. Okay. So let us now have a look. So we are using now the coherence. We are generating the triplets out of the coherences, and let us have a look on what we can see. So we see now we are using in principle only the volume part. So that's only the volume part in terms of the phase, what we see here. And you see the phase is quite high. That in general should be like this, right? Because we have non-zero baseline acquisition. So we have in principle a baseline with this, so it should also have some decorrelation. However, these patches are changing again with time quite strongly. So which means we have here a very dynamic range in terms of patches. And then we see also the ground-only contribution here, and also they are changing with time. So that's also very interesting. So it's not only one scatter is changing, but both the ground and the volume are changing. And then we have everything that is in between, and this you can plot in terms of different polarization combinations, for example, HH to VV, which is closer to the ground. You can plot then HH minus VV, the HH, and HH plus VV, and I think at the end, the VV and the HV. And you see you have in principle all these smaller differences with time. Okay, so that's actually also then in principle concluding a little bit our first observation, because the main thing is out of this observation is coming that we do not have zero closure, but we have something that is changing with time. And the question is, what is changing? So the relative scattering mechanisms are changing. And we see that in principle, it's not only one of these two scattering mechanisms that are changing, but we have a highly dynamic system here where we have changes in the canopy as well as on the ground. So summarizing, biomass with its low frequency and Paul-Inzer capability opens up a new, in principle, perspective on monitoring dynamic effects, as we can see. And non-zero spatial baselines allow really that we can separate ground from volume, which is amazing. So we can see what kind of changes appear and which kind of scattering mechanisms. And then biomass data indicate a very dynamic behavior, as we could see in this example, specifically over now tropical forest that we could see due to rain events, but also flooding. And what is also very interesting for us now, the stationarity that we saw in the beginning that we have when we use closure phases is in principle not holding for each, let me say, scatterer or natural target. And therefore, that's very interesting. And we are really looking forward to explore more of these data in order to learn more what is coming and to see also how highly dynamic our nature is actually. Okay, yeah, thank you very much for this.
Thank you, Irene. Yes, Stefano.
Thank you very much, Irina. I am very, very curious about the last slide, the one when you show the, exactly. So this is a separation of ground and volume coherence based on what single baseline Paul-Inzer?
Yeah.
Okay.
It's a single baseline Paul-Inzer.
Okay, great. So my comment is that for the volume coherence, for me, it's perfectly natural that the phases do not close because it is a volume.
Yeah.
Huh?
Yeah.
But the most interesting part is that they do not close for the ground, which means that it's not just a height changing ground. There is also a time varying penetration.
Oh,
so
yeah, sorry, yeah. Okay.
Did I get it right? Or?
Yeah, it's right. So that's actually what we see. So we see both, actually. We were also not expecting to have a variation in time, actually, over forest, over the canopy, because the canopy has always the same baseline. So it should actually stay stable, the phase at least. But what we see, we see
the same baseline, you mean? Okay.
Oh,
right.
But we see a change, right? Therefore, I say, so in principle, both contributions are changing. So we can't really say which one is changing or not. But what we can do now, using Paul-Inser and biomass, right? We can separate contribution and we can investigate them separately.
Thank you.
Yeah. Let's see who arrives first, Marco. Yeah.
But to that, maybe the ground is changing, Stefano, because it's in the double bounds. So some of the phase that you capture in the double bounds is projected on the ground. So there is that missing closure because, yeah.
I agree, but my point is that if it is just, let's say, double bounce is equivalent to a point-like scatterer. If it's just a double bounce that changes its height, then the phase changes, but it closes. If it exactly.
It's a little bit more, yeah.
So it's a contamination of the volume. Wow. Okay.
Yeah, but
okay.
I think we see this in bare surfaces too, no? So.
Yeah, this is a moisture change also,
Exactly.
right, that we normally see, yes. Mm-hmm.
Any more questions? No, so then we can move. So the last presentation of the session is by Laurent. So he will talk about the adaptive cancellation of ground or overlaying volume responses using multi-baseline INSAR acquisitions and the application to biomass.
Thank you very much for the introduction. So this presentation has been given, also I need to make a disclaimer, last week at the USR conference. And it is about the cancellation of some parts, some responses from different parts of the volume when observing a forest. And I will present two applications. One aiming at cancelling the response of the ground, to keep only the response of the canopy, to estimate, for instance, AGB from biomass data. And the other one is trying to cancel the response of the canopy in order to magnify the response of the ground and have more sensibility to other geophysical aspects. So first, a very quick reminder of what tomography is. Tomography consists in focusing in 3 dimensions by using data acquired in multiple interferometry configurations. So using this acquisition, we form an antenna array which enables separating or discretizing the 2D range, 2D resolution cells into 3D voxels. And using this technique, we can separate the response, extract the response from the canopy only, from the ground only, and we can, using models, retrieve some of their characteristics. And this technique is easy to implement, and its reliability can be appreciated on this tomogram, where you see distinctly the response of the ground, response of the top, and no need to use a big model to retrieve the underlying DTM and also tree height from tomographic data. In the frame of the biomass mission, things change a little bit compared to what I showed before, because we had a very nice vertical resolution using airborne data set. With biomass, the vertical resolution is between 25 and 30 meters. And so the picture is more blurred, okay, it's harder to separate contributions. And even in the very rich configuration, it consists of 7 images. We need to separate these 2 contributions. And you see from the tomogram, which is the first ever produced by ESA, that this is not obvious optically. So we need to use models to do this. And it will be even more difficult in the second phase of the mission, where we will use only 3 images, and we need to reach the same, or we want to reach the same level of performance. So to do this, to extract AGBD, most of the techniques rely on an approach which has been developed a long time ago by our colleague here in the audience, Jin Hotoming, who in fact computed, using tomographic processing, computed images at different elevation above the ground and related the intensity of these images to the AGB, which has been measured over using ground measurements. And the fit you can see on the right-hand side of the transparent is interesting. You see that all the pixels are aligned. The ones that were sampled on different sites fit well with this very well shaped, very well known shape. And the fact the reason this technique works well is that the polarization which has been used by Dean was HV, for which the ground is expected to have a very strong, very small response. And he sampled the intensity at an elevation far away from the ground, 30 meters, so that using tomographic processing, we expect to have almost no echo from the ground. In the dual baseline case or configuration, this will not be the case anymore, and then we need to use signal processing to try to cancel the response of the ground. A solution has been proposed some years ago by our colleagues from Polimi, which relies on very simple signal processing technique, the two-tap notching filter, which consists, in fact, when you are subtracting two images with an adequate phase weighting, you end up, in fact, you are implementing an equivalent technique in the spectral domain. You're weighting the reflectivity density of the forest, which consists of a Dirac and of a bell-shaped response for the canopy. You're just multiplying this reflectivity density by a sine shape. Okay, and if the sine minimum corresponds, the zero corresponds to the elevation of the ground. In fact, you are killing the ground contribution and keeping only the canopy. Okay? So it's very clever, very economic. You need only two images, and the resulting image is theoretically free of the ground contribution. There's another way to do this, to do full tomographic processing using a set of images and using this relationship between the cross-correlation, the interferometric cross-correlation, and the f of z, which is the reflectivity density. You see that there's a Fourier relationship, so we just need to invert this Fourier relationship to retrieve f of z, and once we have it, we can separate the two components. So it's another way, it's richer. In this case, you need many interferometric images. How to do this? There are several ways. Most well-known are the beamformer and Capon. And here I showed a rather awkward motivation for a way of computing the beamforming and Capon solution, which consists in resolving a constraint optimization problem. We'll see later that this is, in fact, useful for our case. So if you using a parameterization of this problem with the identity matrix, we end up with a beamformer solution, which is a simple Fourier transform. And if we use another matrix, we end up with a Capon technique, which has a better resolution and nicer spatial properties. These techniques are good, but they do not prevent fully isolate the ground and volume response when performing tomographic acquisitions. Here I represented the transfer function of a typical biomass configuration, and you see that when sampling the intensity at different elevation above the ground, 15 meters, 30 or 45 meters, we are still sensitive to the response of the ground, which is represented here by these yellow blobs. Okay, we have some leakage. If there is a strong double band scattering occurring exactly at the ground elevation, then it will modulate our analysis, and then we'll be sensitive to this phenomenon. Okay? This is due to the relatively coarse resolution of biomass in elevation. And how to solve this problem? There are different solutions. One of them consists in slightly modifying the optimization technique or statement I showed before by incorporating a constraint to have a zero gain at the elevation of the ground. And if you do this, you end up with a closed form solution, which is a bit more complex than the original one, but easy to solve. And you don't need to implement specific signal processing techniques to realize it. And with no additional complexity, you can actually set a zero at the ground elevation, and you still can scan the intensity over the supposed location of the volume. Okay, this is what you gain. You gain liberty. You can also use signal processing tricks to widen the zeros on the ground if you're not really sure about its location. It can be 5 plus 5 or minus 5 meters above the supposed elevation of the ground. There are some solutions doing this. And here, this adaptive ground notching technique is applied on this first ever tomogram dataset, which has been acquired over the Tumucumake Park in Amapá, Brazil, at the border between French Guiana, Suriname, and Brazil. And the first step of this technique is to actually capture the ground elevation. If we want to cancel the ground, we need to know where it is. Okay? If we don't know where it is, then we will apply 0 somewhere between the ground and the canopy or below the ground, we will miss it. So the first step is to apply a ground notching technique. And I will recommend you to follow the presentation by Francesco Barna and Francesco Salvaterra, which will be given this afternoon, and which explain how they do this. In fact, they estimate the position of the ground and then compensate it on the tomogram. When this is done, you can apply your favorite notching filter. Here I represent a different solution. The first line is the original tomogram. The second line is the solution when you use only 2 images, solution from Polimi. And the other lines are the beamformer and the Capon, which are made fully adaptive. Here they are set to the elevation of 30 meters above the ground, but you see that you have a much better contrast and many more zeros. You are, in fact, notching everything which comes from the ground and below the ground. Okay. So you are supposed to have a better isolation. The application on the data reveals that we have some slightly different features compared to tomography. The main reflectivity features are preserved, but some of them are slightly attenuated because with this technique we are really notching what comes from the ground. So some points, especially in the regions where there are rivers, may be affected by a strong double band scattering, which is not fully cancelled using tomography processing only. Okay. In the 3-image configuration, we have a loss of resolution, and here you see that the usefulness of the proposed approach is more obvious. The simple ground notching technique has only a 0 at the ground elevation and can integrate some echoes that are originating from other positions, while the technique we propose has a better expected ground-to-volume leakage factor. Okay, the application gives something. We compare here what we get with 3 images on the right-hand side to what you get with 7 images on the left-hand side, and you see no big differences. And we further qualify this technique by comparing it to the original notching technique, and we see almost no differences at the elevation of 30 meters. The difference is that with this technique now you can scan at 40 meters, 25 or 50, the elevation you want to use. Okay, so there are different applications for this technique. The first one which comes to our mind is the estimation of AGBD, of above ground biomass density, using a reduced configuration, interval baseline in some mode. And the second one, which is maybe more interesting for the community here, is to, in fact, extend the cancellation in the elevation to the canopy region to see more accurately what occurs on the ground. This might be interesting to people doing, differential sign interferometry, or people interested in measuring the hydrological network, or measuring the ground properties, basically. So I will present the application over these 2 data sets. One, the Tumucumake Park dataset I presented before, and the other one is the Manaus surroundings. So Manaus is the city located at the bottom of the right-hand side image. And you see that this region is characterized by the presence of water. There's water everywhere. So for us, it means strong contributions originating from the ground. Here are some Pauli color-coded images. On the top, you have the original image. In the middle, the image after ground notching. We see a dramatic decrease of reflectivity because many scattering mechanisms involving double bands scattering are located exactly at the ground level, and when you cancel them, you get this kind of results. And the last image corresponds to what you get when you apply notching at the canopy level, and we see that this provides an image which has a reddish color, which is characteristic of double band scattering. So we have a more quantitative analysis using a polarimetric decomposition. We choose the IRIS one because we like it, but you can use the one of your choice. So on the top, you have the volume component, original one, in the middle, the one after ground notching, and the bottom, the one after canopy notching. And here we had a big surprise to see that you get, over most of the image, a stronger decrease in volume scattering when you cancel the ground than when you cancel the canopy. And this is super counterintuitive. Okay, we had to think a bit about this paradox when analyzing the images. And in fact, this can be explained using this analysis that were performed in the past. Here on the left-hand side, you have all scattering mechanisms occurring over a forest using the first-order radiative transfer solution. Okay, this is a usually accepted representation of scattering. And in the former study, involving indoor measurements, we try to quantify these different scattering mechanisms, and especially in the case where there are no trunks. We made trees without trunks, so we had a volume lying over the ground, okay, standing over transparent support, and we were able to measure these scattering mechanisms involving reflection on the ground, volume, and back to the radar. And this can be very energetic because it follows a specular path, and it is characterized by a very strong HV component. Okay, so it does not have the usual features of double band scattering, and it is exactly on the ground, at the ground level. And if we combine this analysis and the one that has been performed some years ago by Mariotti, Alessandro, and Stefano on tropical forest, they found out that double band scattering, the intensity of double band scattering is highly modulated by the spacing between the trees, the tree density. Because when you have double band scattering, it involves all the two sides of a dihedral. And the longer the side, the stronger the scattering. Okay? And in this case, over the rivers, if we go back here, over the rivers, we have this double band scattering over very wide open areas. This is why we have such a strong volume on the ground. So this was a surprising finding, but it could be explained finally. And when we look at the double band scattering, we found that when notching the canopy, we reveal all the network of rivers that could not be appreciated from the original image, okay, where double band is saturating. And we found many places where you have coherent and specific scattering. We can follow even very small channels. The same analysis was performed over the Manaus area, and we see from the ground notch image in the middle that this decrease in volume scattering is obvious over all these channels and rivers. And this is confirmed by the volume maps that you can see on this image. Okay, you remove a lot of volume when you notch on the ground. Okay? So taking HV as a scattering from only the canopy in our case is not really correct. And we perform this double bands decomposition. Here we can give two remarks. The first one is that after canopy notching, we really can follow all the rivers and different, okay, the contrast between homogeneous forests and small patches or rivers is enhanced compared to the original image. And in the middle image, you see that after ground notching, there is still some residual double band scattering. This can come from double band scattering in the trees, but we believe this might be due to variations of the water level during the acquisitions, which prevents us from actually cancelling very accurately the double band scattering, which is located exactly at this water level. Okay. So this is something under investigation. So here we give these are my 2 or 3 last slides. We give a look at some detailed parts of this Manaus image. You have in the middle this double bands map of the original image, right-hand side after canopy notching. You see that the contrast is enhanced, and what we see here are basically human settlements, buildings, something where double band scattering occurs and facing the radar. Here, the same analysis is performed in the middle of the forest, but we found that after canopy notching, we have some blobs which are distributed over the image, and the density of this blob is larger when we are close to areas affected by humans, where you see there are some deforested patches, there might be some small houses, and we can try to detect this kind of settlements. And the last example is really, in this case, in the middle of the forest, and we see that after canopy notching, we end up with some blobs on the ground, which are likely this is still under investigation, unlikely to correspond to water, to areas where you will have water below the forest. So if we confirm this, it would be a nice finding for biomass. Otherwise, we need to find a real explanation for this. But these blobs are so coherent that we expect we can find something. And this concludes my presentation. So in this here, we generalize the ground notching formally proposed by our colleagues from Milano to the case of tomography, which gives us the ability to scan in elevation, and by also changing the elevation of the cancellation action, we can either choose to cancel the ground or the canopy, and this gives us more insights for analyzing the geophysical patterns of this part of the medium using, for instance, star polarimetry or other techniques. Thank you very much for your attention.
Thank you, Laurent. Are there questions? No? No question? So thank you very much, Laurent. With that, we conclude the session. Enjoy lunch, I guess. So, see you later.
Later is the round table, no? There is a round table later on.
After the...
At the end of the afternoon.
Yes, yes.
Remind people maybe, no?
I will remind in the second.
Yes, okay. You can also do it at the end of the... It's important, huh? Because they are breaking, you give me. Because they are breaking my... No.
family to live in. There is no one for the summary.
It's in everything.
But if you prepare, exactly. You can give the summary section. This is my man.
They were put there, but there is no one from the chair.
Just read the slide.
Ce l'hai qualcosa? Tipo qualche seed question, no? No, ecco, vedi, bravo. Marco mi ha detto, ma 2 settimane fa dovevi mandare, chiedere seed question, ma io se non hanno visto la sessione, ma come mandano seed question? Non esiste. No, niente, però Fourier forse già qualcosa pure. Quindi tutto sempre là nella cartella dove sono presentazioni.
But they're still playing. Okay, so welcome back to the biomass session. Now we are waiting for someone more to show up, and so we'll be starting in a couple of minutes. Okay, so shall we start then?
We don't have slide?
But now they're coming.
Okay.
Thank you very much.
Wow. Okay.
Okay, so we can officially reopen the biomass session. Welcome back. I am Stefano Tebaldini. I am chairing this session with Hoton Mindin, who is also the first speaker. So, Dean, the floor is yours.
Okay, thank you for introduction, Stefano. Okay, we are starting a little bit slowly because there are not so many people here, so I speak a little bit slowly, so don't worry. So we're going to show you some first results from biomass research, and to do that, we have to discuss a little bit about the technique, how we calibrate the data before we moving on. So this work is a lot of contribution from many colleagues from CESPIO, from Bolimi, from Nanyang Technological University, from India, and from Tomosa France. So we want to discuss about the biomass for forest, but let's go. Okay. So first of all, one question we have to answer about is radar data is stable in forest, because that is the key question. If we don't have a stable signal, we don't have a coherence, we cannot do anything with the analysis. And for that question, we take a lot of experiment before, about around 2010, something like 2015. We do a lot of comparison, crowd-based experiment to understand what exactly the the temporal decorrelation in forest with the B-band, because we know very well B-band, okay, is about 70 centimeter, it's long wavelength, but is it stable enough in the forest for our understanding, for our processing? Because when we do star interferometry, or even with star tomography, we need many images as a function of time, because there's no way to have all the images at the same time. So we always have a temporal decorrelation. And at that time, we end up with something like 3 or 4 days, and then we propose to ESA, and the ESA, they finally happy with the 3 days proposal. And then we have the biomass now. So one of the first data, when it come out, I try to see it first, and then we try something like, okay, we select some area in forest. One of the first data are published in archive by ESA. We download some data, and we do a little bit exercise to do correlation and to subtract the tomographic contribution, and then we see some clean interferogram like this one. So it's a huge happy for us, because why? Because with the clean interferogram like this one, we have the clean signal from the forest structure. Of course, there will be a little bit residue for the atmospheric or orbit determined, but we will discuss this later, how to remove this one. But basically, that's before to do anything for later step, we have to be sure that our correlation is perfect like this one. We have to see, okay, is the signal is coherent or not? If no, we have to find a way to dealing with this one. For example, this morning, Stefano discussed about multi-screen, something like this one, right? So basically, that is the first step. We have to be sure everything is correct. And from that one, we can go play with the data set. For example, we go to the spectrum techniques. For example, that's the tomosat. Basically, that's the tomosat is the one that allows us to distinguish, to find where the signal comes from, where the scattering comes from, at what height. For example, in vertical, we see the elevation, and in horizontal, just slide in along the azimuth track. So basically, with the data from biomass, we have something like very large azimuth, like 140 kilometers, with respect to about 21 seconds by each frame. So we see this profile, and we see, oh, what happened? Is there anything? And we see, okay, where the forest come from, where the layer of the ground, where the forest high. We don't have no idea. Because why? Because the data it look like, okay, with a strong signal, we tell us which high the signal come from, where either radar energies go back from as what high. But in general, we don't learn much about this interferogram, this tomogram. Why? Because we have some problem with the residue atmospheric, and also with the orbit determined by the satellite. So we have to find a way to make this blurry or smear focusing like this one, to make something more useful, something more understandable for us to find some parameter that we are interested in, for example, forest biomass and so on. So we found the problem is something related to the residue of the atmospheric and orbits that we discussed already. And also the second one is we work in the forest. We want to something like, we have to reference something, because if we see the forest like from -100 to +100, like the previous one, it's difficult for us to focus where it should be the forest. So we have to focus the preference, for example, in high preference. So usually that's we refer to the preference heights related to the 0 meter for the topography. And one way to do that is we take the unit capability of the biomass mission. That is we have the where, the multi-baseline data, because we have a systematic 6 or 7 acquisition for the data. And also we have a multi-polarimetry information. So we tell us what kind of scattering information we have. So in the same data set, we have the multi-baseline data for interferometry, and we have a multi-polarization for polarimetry analysis. So if we are able to join, to put together for all information together, so basically the way we do, we try to put it in a form of the covariant matrix like you see in the figure. So basically that's, for example, we focus on the cobalt. So it's just a part of the image to show you how it's a function of the multi-baseline. And then after the block of the cobalt, we go to the cross-bond. We see something like cobalt and cross-bond. There is not so much for correlation. And then we go to the cobalt coherence, for example, RVV, and we see some coherence. So we put it all together in the form of matrix like this one. And then we're able to jointly decompose it based on what we call the sum of canonical products. So basically that we have the covariant matrix like this one. This is the case here. So we have the cobalt. So each one will be corresponding to interference matrix information. So we have, for example, 1, 2, 3, 4, 5, 6. So 6 or 7, it depends on each area. But usually we have a 6, that's enough for us to process it. 7 is perfect. And then with each polarimetry here, we put in the form of matrix here. And we're using the technique of what we call the sum of canonical products. So this is the canonical operator here. So we are able to decompose it in a certain scaling eigenvalue here. And then from that, we can able to synthesize some way of a constant here to synthesize it into the crowd-only contribution and volume-only contribution. So basically, that's the R, G, and RV here. So basically, that's just the block, matrix block, with respect to the number of acquisition, our acquisition here. For example, 6 or 7 by 6 or 7 by 7. So 3 by 3 here, usually we take the average of the cross-bonds of VR and RV. So usually we have cobalt and cross-bond like this one. So basically that's the CK here, so the RK here, so corresponding to dimension of this one. So, and then how it actually we work in here. So we try to combine just based on a certain kind of linear combination between the first canonical product, but the second one based on a certain linear combination here. And we do it the same for the volume component. So basically, and then we try to optimize to find where the coherent mode is more stable. For suppose that we have the G and V, and we find something like related to positive definition constraint, because we have to be sure that the RG and the CV and the RV here should have the positive eigenvalue, because in that case it gives us something fixed information rather than non-fixed information. So usually that we take the one which we have the maximized coherent, we assign it to the RG, that is the most coherent one. So from that, we do something like phase linking algorithm to extract the best phase, what is the corresponding to from the radar bus to the forest floor. So that is the optical bus from the radar to the forest floor. So we have that optical bus, and then we remove this one. So we call this one is the crowd phase contribution, and remove this guy to our original singular complex data. And from that we can do some analysis later. Here just some figure to help you to figure out the previous one is for the part of the image. Here just one individual pixel. So basically, as one pixel, we see for example, we see the cobalt, the crossbone, and something is one we see. So if we put together like RV, just for coherence like this one, we see not so much different. But if we do some decomposition and we synthesize like this one, and we got this one, so basically we exploit all information, the diversity information from polarimetry and interferometry together to get something like to pick up the crowd only here. So basically the idea is if we have the crowd, it should stick to the stable target. With that, we do again. So with that, we do again. It's our previous tomogram. So we're not really happy to see this one. But now with the phase calibration, we see the signal very clear. So with the gyrometer, which related to our topography layer. So by such kind of processing, we are able to compare forest or whatever it is. So always we don't dependent on the topography. We always refer it to gyrometer here. So the wildlife here is just the way up we derive the forest height based on a certain calibration with the data, issue data. So, but basically that to get this one, we had to do a little bit step of phase calibration and so on. We got this one. So for interferometry community, usually that's you have this one only, because when you have this one, you see this one, you're not really happy, but you have to combine with the polarimetry. That is the key point from biomass mission, because usually with the interferometry community, they just rely a lot in the cobalt VV or us only. They're not really like the crossbone because they worry about the random volume scattering. But with the forest, everything is random. We need to exploit the diversity of polarimetry to get useful information, and to got this one. So, okay, so now we move a little bit more interesting to see the slide for in a certain area here. For example, that's the slide. That's one of the tomogram we got from the data. So what we see here is the first is when we see something new, we just try to refer what we learned in the past, what is the lesson we learned in the past, and we see something interesting, something like, okay, it's not really strange for us, because why? Because with the cobalt or with the crossbone or with the cobalt, this one we see with the crossbone, we see there is a strong interaction in the canopy layer. So that's we learned from the airborne combat already. So it means that with the crossbone, we have a strong interaction in the random scattering. That's why we have a strong scattering like this one. With the cobalt, we see something, but not really strong. But in any case, there is interaction in layer by layer for all polarization. And one of interesting is about his open space. There is no forest, and we see some phenomena, some signal from underground. We don't know is this a signal. We can see something underground, or maybe some problem with the phase calibration. But there is some signal that we are quite excited to see. That's one. So. And of course, we even know whatever the forest high, we can see some signal underneath the forest. For example, we see the crowd interactive, the crowd contribution, very strong signal here for all the polarization. Okay, and now we move a little bit to another area to see how it's going on when we have a little bit more simple scenario. Okay, just forgot to mention, before that we talked this one, we talked about how to apply this one. So actually what we do with the biomass is basically that's what we want. So that is our main objective. We want to quantify the biomass or the carbon, forest carbon. We try to reduce its uncertainty. So to do that one, we have to find a way how to have the best estimate. So here just we use an example. Here we have the optical image, where here we have some beautiful color composites from the radar, and here we have some data analysis from tomography. So we have a layer by layer, here 30 meter, and from that we use some knowledge. We try to reduce the biomass here, but here we don't have much data to talk about. We have to waiting for the real tree data to do some validation with the biomass prediction. But here just one of prediction, and one of the quite interesting because it's quite a positive one. It's called the contrast very clear in the forest and where it's a non-forest area. So we move to another scenario where we have some simple structure forest, because we know very well in a certain area in South America, in Brazil, for example, they plant a lot of the tree, what we call the eucalyptus plantation. So basically, they have many plantation area here, and they are also very well controlled. So we have some data here. So we try to take one data set biomass in that area here with test 7 image with information related to at the end of December last year. So the structure of this plantation is quite simple because what you see is all vertical here. So inside the forest, they almost no branch, just a small leaf on the top of the canopy here. So we have quite simple of structure here. And what is our expectation? We will see. Okay, so here just a very quick example that here it is original data with the tomography. We are able to slide the forest layer by layer. So we see how the forest, how the scattering is interacting with the forest, and how the construct when we go far away the ground. So and then we try to using some in-situ data to plot this one. So basically that we have a certain cluster of in-situ data. We know very well how high it is, and we try to take the average of energy product from radar, which depend on the top of the ground is too high. So we have the co-bone and cross-bone here. And what we see here is, for example, in a 30-meter layer, we see the very high contrast, the very high sensitivity with the co-bone, which brings back to the forest high, with the forest plantation high, with not really sensitivity with the cross-bone here. And this is really opposite to what I understood, because in the past we always have the able component in the natural forest. We don't have such component in the plantation forest, so we don't know it before. But it makes sense for us because why? Because with the structure like the plantation forest, we have the vertical structure. It means that we have a very weak depolarization interaction. So that's why we have the signal of the crossbone very weak, even in the 30 meter here. So that's why it makes sense we have the co-bone. So we take some knowledge and we retrieve some information and so on. I will show you maybe in the near future, but here is the conclusion. So basically that you see we had to do crowd calibration to make on work, but you don't worry a lot because here I work on the level 1A, so at SCS, so don't worry, because if you want to work and you worry, don't want to worry about fake calibration, you just start it by level 1C, everything fine. It's do it for you, so don't worry. Thank you for your attention.
Any questions?
Thank you, Dean. So one question would be, when you showed tomogram, there were some points below the ground level, right?
Right.
So is it, in your opinion, due to the specific scenario that you're investigating, or rather kind of some drawback of calibration?
Oh, that is the one question I already mentioned, that we don't know, is it a phenomenon we really see something underneath of the ground or something problem with the phase calibration, but we have to investigate. We already mentioned, yeah. But if we are able to see something underground, it will be fascinating. Yeah. But that we are trying to investigate. Right.
Thank you.
Thank you.
Any more questions? So if not, thank you again, Dean. And we can pass to the next couple of talks, actually, given by the man who knows the details of biomass better than anyone else. Francesco, please.
I don't know. Hello?
It's true.
So, hi. Let's start with digital terrain model retrieval. I will try to give you an overview of the process. And it's not just that, it's also about phase calibration. So some things Dean showed, but let's go into the details. Just a cold start slide, but I guess you know, thanks to the previous presenters, what biomass is, more or less by now. But it's nice to see in a nutshell, no? It's first P-band mission in space, which is very nice, a new challenge, a new sensor. And this was motivated by the need to probe the entire forest structure down to the terrain, so the long wavelength we need. Of course, it comes with challenges. You saw previous presentation, and you will see some also in this one. And the cool thing is also that biomass implements operationally full polarimetry, interferometry, and tomography. You see an example here of this very nice tomogram in South America, and also polarimetry at ground and canopy level have different colors according to different physics. Most of the products of the mission, the primary ones, but also the secondary objectives, ice and desert, and you will see these also in later presentations, rely on interferometry. Of course, polarimetry is very important for system calibration and also target characterization. But interferometry is really the conditio sine qua non in this mission, because it's really a game changer. No? It enables to estimate forest height, forest biomass, also subsurface structures, and so on. We are now in the tomographic phase, which started about December last year, and is going to last until beginning of the next year. So nominally, we have these 7 stacks with 50% of critical baseline spacing in between the acquisitions and 3 days repeat, which gives roughly 20 meters vertical resolution at the equator. And then the mission will be a 5 years phase of dual baseline Pol-INSAR. So we will have to go more by models. And speaking of interferometry means really speaking about phase calibration. You see a little example here from an old airborne campaign. So if you don't remove from the phase all the nuisance effects, mainly due to atmosphere, so you saw Stefano's presentation this morning maybe, mainly ionosphere actually, and also baseline errors, then the tomography gets defocused. You saw also Dean's presentation before mine. Whereas if you do calibrate, then the tomography gets nicer, you have proper imaging. And so the starting point is really co-registered and calibrated images. And in particular, in this presentation, we see one special opportunity of biomass, which is under canopy terrestrial model estimation. So more or less, the processing is like this. So we start from level 1 stacks, single acquisitions, calibrated at single acquisition level. We do co-registration and stacking, which is standard processing based on a DEM. Then we may have some optional filtering, but most importantly, we have ionospheric calibration, because without that, you saw, it's really challenging to go further. And then, and this links also very closely with Dean's presentation, we have to do one more step of calibration. Why? Because we still have offsets, which are variable from image to image. Usually all over the image track are low pass. And if everything went right at this stage of processing, this is mainly due to troposphere, or very residual ionospheric frequencies and low pass leftovers. And so we have this very last step in the interferometric processor, which addresses this. Currently, it's implemented by the SKP decomposition that was described by Dean, but we are also assessing other things. We will see this in the next slide. And then again, the difference is focusing without correcting this, you get defocused. And with this, then you get a proper imaging again. So how do we do that? Well, SKP decomposition is basically Pol-INSAR in a very nutshell. So we have a multi-baseline and multi-polarimetry, and we do a ground volume separation with some algebra. Then we get 2 objects. You see an example here from airborne data reprocessor. So you have full data, Pol-INSAR, and then you get a volume and a ground. Then we have an n by n ground INSAR coherence matrix. We have to take out triangular phases from that to do calibration. And so we have to apply a little bit of phase linking or some other criterion. Then once we do that, we compensate these phases in the stack. We compute coherences, we do tomography, and the phase center should correspond to the terrain already, except for statistical errors. There is another way to do that, which is pure interferometry. For instance, we are assessing the phase linking is basically an estimator that out of an n by n coherence or covariance matrix, interferometric. So you have to pick up one polarization or a combination of polarizations that, in your opinion, enhances this estimation. We get out n-1 phases with respect to a reference. And if you look at biomass coherences, you see they are clearly affected by the increase of baselines because of the very small bandwidth of 6 megahertz. So the wave number shift plays a big role, and as soon as you increase the baseline, you start to lose coherence very fast. So that's why we think it's wiser to apply phase linking using the small baselines, so the step 1 baselines. And in this way, we get nice results. So, for instance, here, for the same airborne dataset reprocessed, you see a focusing of the phase linking phase center, but you also see that this phase center is not ground, of course. Where you have canopy, this is located actually midway and a bit far from the ground. So we need an extra step to compensate for this, which can be tomography or model-based decimation, basically. And this brings to this slide. So we have a clash between precision and resolution, but I would say also accuracy, because in the end, let's say also bias is a big problem when estimating these phases. So basically, these things these techniques are statistical. So we need multi-looking, and to get a decent result, we need some 100 meters. Well, phase linking is a bit more stable, but let's say both need enough looks. And this is actually not a big deal if we consider that these phases contain atmospheric phase screen, because the scale is some kilometer, some tens of kilometers, or maybe more, it depends on the APS component, but this is not optimal for estimating a DTM. So the quick and dirty solution, let's say, is just we estimate in a first step these calibration phases, then we apply this to the original stack, we recompute coherences, and then we try to track, after recomputing coherences with a smaller window, so higher resolution, the ground with the IRS spectral estimation. And this we do with a model, a very simple model, actually. So it's a 2-layer model, so we have a ground, we have a canopy, and these are 2 deltas. And so for both, we estimate a height, and then we have also a coefficient which tells us how much is the mix between these 2 mechanisms in our cell. And this is very easy to treat computationally, but also we saw experimentally that this is accurate for tropical forest at P-band. I suggest you to go and have a look to this publication, which compares different kinds of functions, reflectivities, and in the end proves that 2 deltas are enough. So just some results to corroborate this. This is airborne data reprocessed. We applied both techniques, polyINSAR and pure INSAR, with this extra terrain locking step. So we have a reference tomogram and the outcome of these 2 techniques. And here we have the slope of the terrain in this area. And this is a control test, of course, because being airborne data, the data are calibrated, there's no PS, so we could inject and process and then compare with the reference. And you see that it works nice, so ground is indeed a 0, and you see the canopy, but it's not perfect. No? There are points where this does not hold, and you see the canopy goes to the ground. And these points are mainly, I would say, the points where slope is steeper. And this is also linked to the fact that the 2-layer model doesn't hold anymore. So maybe you have just one object. So this is a point of study that we should continue on. Corrections can be done, for instance, in post-processing, for instance, combining ascending and descending. And here you have also just some histograms saying that in this control case, result is nice. But we have also a preliminary result with biomass. So thanks to having a dataset in Alopé, Gabon, which was, let's say, also studied previously with this airborne AFRISAR dataset. We have this very small area, it's 10 by 10 square kilometers, more or less. We have canopy, but we also have an open area. And having an open area, we can play the game of calibrating this by locking everything onto the phase of one point in the bare area, no? Because the APS, let's say, scale is comparable with the scene size. So we assume that APS is constant, basically, within this area. Processing the data like this, so you have the LiDAR DTM from airborne campaign, what we estimate from biomass, and the difference of both with respect to Copernicus DEM, which is a DEM coming from a TandemX mission, basically, and so represents the digital surface model, so the canopy. And you see the agreement is actually pretty nice. Of course, let's say the averaging and details are a bit different, but the result is indeed nice. Then let's say the ground phase estimation is indeed the very first and very important step of a DTM estimation, and also has the twofold purpose of getting the data ready to do tomography or estimating forest products, for instance. But if we want to go to a DTM estimation, we have to take an extra step, which is basically the separation in these phases of the terrain contribution from the troposphere contribution. How do we do this? So we went back to basically the classic interferometric literature and evaluated different approaches. So our objective in the end is to develop an approach which is simple and operational, because we want this to work, let's say, in a first round on the tomographic phase data, but then possibly to continue throughout the mission, no? To have, let's say, a probing of the DTM level throughout the mission. So the troposphere is, as you may know very well, being attendance of Fringe conference, is the lowest part of atmosphere, which causes extra delay due to variations of atmospheric conditions locally with time and season also. Usually it's modeled into two components, a stratified one depending on elevation, and a second part which is turbulence, which varies locally and represents small scale contribution. So the classic approaches in literature are the space-time approaches, so permanent scattering interferometry or OSBAS, for instance. So they exploit the fact that APS is correlated in space but not in time, and the information we want to retrieve from the data is the converse. And also that you have redundancy from many acquisitions. The model-based approaches usually model these into these two components, stratification and turbulence, and there are also approaches using weather models integrated with GNSS. They usually give you an information which can be converted into a compensation phase screen, and there is also machine learning, of course. So challenges for biomass. So we are mainly trying to map structure of forest and their evolution in dense humid canopies, equatorial belt. So with a lot of volume scattering, of course. So APS is changing over short distance and time, and this hinders a bit the applicability of weather models. We will see this in a couple of slides. But also, if we want to do this stack-wise, we have a limited number of acquisitions, because maybe we can get 8 or 10, let's say, because of extra orbits, but we won't get much more. The nominal stack is still 7. So we cannot use permanent scatterers or SBAS, for instance. Since we're not machine learning guys, we didn't go for that way. So I would say we stick with the model. And the first step, so we tackle this in 2 steps, is indeed addressing the stratified part. The stratified part can be addressed by a very simple model, basically a linear model, or maybe a slightly more complex one if you put on top of that more orders of a polynomial. And the assumption is very simple, that this component of the APS, especially for a strip map system with, let's say, 140 kilometers SWOT, so you have over the entire SWOT a correlation between your phase and topography due to troposphere. So you can try to estimate this linear trend, maybe in the complex domain, to avoid phase unwrapping. You may also remove at each trial a 2D plane over the SWOT to account for any non-perfect orbital compensation. And optionally, you can try to track a higher order polynomial. Here you see an example from SAOCOM. That's where we started, because we didn't have at first biomass data last year. So you see an interferogram, you see DAM, this is an area in Chad, a volcano, and you see the histogram indeed shows a correlation. So if you start from the original interferogram, you can try to fit this linear trend with or without an additional plane removal. Without, you see there are more leftovers in the phase. And this looks cleaner, looks more like, well, residual topographic errors due to non-perfect DM compensation, I would say, but especially a fractal-like pattern, which is that of the turbulence. Since we wanted to assess also the weather model use, we tried to benchmark this with GACUS, which is a very popular choice in literature. And you can see there is still a difference. So with GACUS, there are more leftovers. This is even clear if we look at the histograms, no? So again, the original, you clearly see the correlation. The GACUS flattens a bit, but not as much. And our correction brings it more flat. We think there is a reason for this because, of course, weather model provide information which is useful, but there are caveats. One is the low resolution, spatial low resolution, so there's no fine scale. This is not even the biggest drawback. The other two are, of course, the GNSS coverage, which can be sparse, and also the temporal resolution. And this is not really a limitation maybe for stratification, but more for the turbulence, because turbulence can change in less than an hour. Another example, just to further corroborate this, on Mount Fuji, which is more complex scenario, more humid, more complex topography, and also more vegetation and human settlements, you see that GACUS does not manage to remove this, especially on the Mount Fuji itself, whereas our correction works nicer. Then preliminary examples with biomass. This is more or less the same area in Chad. You see the histogram, you see the interferograms, so compensation happens to some extent, but there's still some left over. And also there are these fringes. We think this may be also to residual, non-compensated, low ionospheric frequencies. Now, if you saw Stefano's presentation, you know that the ionosphere compensation that we put in place, we still have to investigate better how to compensate the low frequencies. And then the last part is the turbulent APS removal. The approach here is very simple. After we have the stratified, we just exploit open areas to read the phase, because their DEM is already DTM. We interpolate wall to wall, and we bring this away. Here it's just simulated on SALCOM. You see the residual is indeed remaining over turbulence. Distance-based interpolator is a good choice, a good compromise. After that, you are left with fitting the phases to estimate the DTM itself. The problem is, in dense forests, we are lacking open areas. So in this case, you can still try to attempt the fitting. It will be a bit more noisy, but especially we lack absolute reference. So this is a point of further investigation. A very preliminary example on biomass in Brazil. So you see the interferograms with stratification, the stratified corresponding histograms, the cost function of the complex exponential, which is basically based on weighted sum of residuals weighted by INSAR coherence. The fitting performed on the barycenter of the phase histogram. And then you see the open areas mask, which is really sparse. And then we show the fitting of the phases without the stratifying and with the stratification. So without the stratification, you see the dynamic of the heights, the differential heights from DEM is more compressed and also not very physical maybe. And instead, if you do the stratification, it gets much more good looking. But this is still preliminary, so more in the next conferences, I guess. So just wrap up. So our DTM estimation chain is tightly and heavily linked to phase calibration in its essence. So the ground phase estimation is a very important step. And then we have to decouple from terrain, the troposphere, and this happens in two steps: the stratification and hopefully wall-to-wall interpolation and removal of turbulence. It's supported by preliminary results, which are nice, but there's still more work to do. And we think it's a good point that this is independent from external corrections, because they would be heavier to maintain for an operational mission. Some points to address: again, correction of artifacts in the ground level estimation, whether to use or not a higher order polynomial in the stratification, availability of open areas, and of course more validation with actual DTM references from airborne campaigns, along with interplay with the previous processing and especially ionosphere. That's it. Thanks a lot.
Do you prefer to take questions now or to give the second talk and then?
It's the same. I don't know if somebody has a question.
We can ask for question now.
To ask.
Thanks. Very nice results. I have a question regarding the atmospheric removal. Once you do the stratification removal, how much of that turbulence is in the phase? Like, what's the largest, in the examples you have shown, what's the largest phase variation that you still get that is left at P-band?
But you mean after the stratification?
Yes.
Okay, maybe not much. Actually, I don't have a number in mind, but I think that the most important component is the stratified one. So if you don't destratify, then you get funny heights, let's say. If you do the stratified, it already looks like, so you can look here, these are differential heights with respect to COPDEM estimated after the stratification. I would say still a bit lower, because I would be expecting some tens meter more, maybe, but it's already the same order of magnitude, let's say, of what we are expecting.
But that should still be like spatially smooth, I would guess. I mean, are they? So I don't really see that as a huge problem, or is that a misunderstanding on my side? Because
No. I don't expect it to be a huge problem. Just to make estimates more noisy. Of course, if you can do that, it's beneficial. Otherwise, I hope it's not the biggest deal we have to deal with in this very moment.
Okay, thank you.
Thank you.
Anyone else? No? So we can continue to the second talk.
Okay. Okay, and now we go to tomography. So this time faster start, because no more introduction about biomass. So this presentation is just meant to give you an idea of, let's say, what we do as standard processing and some more funny things. And also, I will come to this at the end, but it is also to answer a point maybe raised by Dean and maybe also a curiosity of other people. This is going to be something available to the community at some point as a processing software, open source. So the goal of tomography is just to generate a 3D. Very, very simple, apparently. And again, we start from stack of single images. We do co-registration. We do ionosphere compensation, which we know by now is one of the most important points, actually. And then, again, this ground steering, no? So this extra calibration, and also we want to put these tomograms with the terrain at 0 level. So 7 acquisitions in the TOM phase nominally. If you look in the catalog right now, there are also stacks with slightly more, also with slightly less, especially also in the COM phases when where let's say the situation was not exactly nominal. And then the final outcome is cubes. So for each polarization, or actually for each polarization combination, we can produce 3D voxels, both in SAR coordinates and on ground. So let's just have a look at single steps, step by step. So the first step is, I would say, trivial. It's just co-registration and stacking, and we do it in a very simple way. So you can just align images on a rough basis based on orbits and topography. And I would say orbits are not super fine like the Sentinel ones, but they're really good. At least they allow you to carry out all the later processing. And then we do, of course, an extra step of data-driven co-registration. And in this case, we use incoherent speckle tracking, which is simple as safe choice. So you see an example of interferometric coherence over this stack in Papua Nova Guinea. Just with geometric co-registration, coherence is very low, and after data-driven co-registration extra step, coherence gets reasonable. It starts to look like biomass coherences with higher ones on step 1 baselines and lower one due to the spectral shift going outwards, increasing the baseline. So ionosphere, again, maybe this is more for people who just popped in and haven't seen the previous presentations, can be a pain in the toe, because in some parts of the world it's really intense, and Co-registration is not enough to address this, but also, let's say, previous literature was actually focusing on a single layer ionospheric model. We experience from the data themselves that this is not always the case, and rather, we at least from a modeling point of view, then we would need physicists to go more deeper into this. We need to model it as a multiple layer medium. And actually for forest, usually situation is not so extreme, but sometimes you can see funny things and the wilder ionosphere. This is an example over Amazon River. You see this F-spread phenomenon, which causes also SNR effects and gives you this grating lobe pattern all over the image. So basically your processing has two choices. So we assess coherence. If co-registration is enough, fine, we go on like that. If it's not, you saw Stefano's presentation this morning, we put in place this machinery to estimate with screen diversity the layered or single layer ionospheric structure, and we compensate the data accordingly. No? And here an example again to see the extreme case in Antarctica where co-registration is not enough, coherence is really low. After this machinery, magnitude is high and just low ionospheric frequencies are left. Of course, low frequencies are left. So again, the ground steering is very important. The ground steering, just to, let's say, look at it from a different perspective, at least compared to previous presentation, is the process of phase calibrating a stack. And in doing this, you try to do two things. First of all, to have a common reference, of course, and to link the common reference to a physically meaning feature of the scene. And in this case, we want to link it to the ground. So the phases will look like that. So for an interferometric pair of acquisitions N and M, you have basically a differential APS between the two. Then you have the ground phase, which is the one that is a proxy for DTM and also puts the tomogram at zero height, which linearly depends by the height of the ground. And if you do this ground steering we talked about in the previous presentation, then you're left just with the non-triangular phase terms, which is the forest volume. This is the thing we want to estimate with tomography. So currently this is done by Polinser, but again we saw pure INSER is under assessment. This is an example on real data over La Lope Gabon, the full scene. Actually this is at least the first version that came out in commissioning phase, so you see there's just 5 acquisitions. So before the calibration, you see a lot of fringes, and then after calibration, phases look cleaner. In this particular case, a bit noisy because I think we used a small window, but it can be increased, of course. So some example, just to show nice tomographic results. This is the very first tomography that we worked on, Tumucumaque Park in Brazil, or rather at the border of several South American states. This was acquired in commissioning phase in October, 6 passes. More or less the progression of baselines, I would say, is in line with the one by the book, let's say. And so you see coherencies here, which are pretty nice, one higher than the others, but let's say more or less respecting the progression we expect from biomass, and then the phases after calibration, of course. And then you see the tomograms. Here we have the 3 polarimetric channels for the slice that is highlighted over this Pauli composite from a single look with a dashed line. You see the ground is nicely at 0, and you also see some differences in the scattering. So HH bears more energy at the ground, HV bears more energy higher than the ground, VV is somehow in between. And you also see the change of scattering in correspondence of features like this river or open area here. If you want to know more and to read about the results, there is this nice web story on the ESA website in which you find the same and also a bit of polarimetry layer by layer. So the ground is nicely red, reminding of a double bounce. So this is a Pauli composite. The canopy one, these are horizontal slices, is greener, so more HV, more volume. Another example, Alope National Park. Here it was, let's say, a bit more of a stress test for us because it was less nominal. So we had one track less. So you see also in the coherence, in the coherences, there is a double jump and the lower coherence here. And also one of the baselines was actually not aligned with the expectations. But still, also I would say in this case, the results are nice. You see again Fourier tomography, all the 3 channels, change of features in correspondence of bare areas, and more or less similar feature to the Tumukumakwe example. And we also tried Capone. I don't know if it's clearly visible from the projector, let's say, but I would say just like expected, Capone is a bit cleaner and also maybe a resolution improves a little bit. Not much because biomass coherence is going very fast low, no? And so Capone is expected to behave like this, not to give a big gain. Just a very brief overview of something more experimental compared to the standard tomography, and this pairs a bit also with Laurent's presentation from this morning. So what do we need tomography for? Of course, to look at the structure of forest and maybe forest height and is the first thing that you can start looking at tomograms, but another thing is probably biomass estimation. So using the reflectivity at different heights to try to find a correlation to biomass and to then later estimate wall-to-wall maps. This is also one of the main objectives of biomass. So, for instance, here you see, again, on the Lope example, so this is AGBD from campaign data, and this is VH from biomass. It's the 30-meter tomographic slice, so you see there is a correlation. You can fit a model, train some coefficients, and then try to apply this also elsewhere. In this preliminary example, I would say results are already nice. At least there is not a big bias, let's say up to at least this 350 tons per hectare, then it gets a bit bigger for higher biomass. And in doing this, we plan to address all the points that can be addressed. So to implement radiometric corrections that can account for slopes and geometry, to compensate the reflectivity of tomographic layers for that. We can do also interpolation in case we miss a baseline, like the one we saw previously. Maybe it's not making a big difference, but we want to have this tool at hand in case it's needed. And of course, geocoding, so putting everything in the real 3D world. In int phase, we want to have tomography because of the 3 baselines, but we will have another technique which is tightly linked to tomography, which is ground notching. It was presented by Laurent from Famille. And this brings to the next slide. Basically, notching is combining by signal processing the images of the stack to achieve a suppression of some part of the forest and an enhancement of the other parts. So it can be applied both to notch the ground and enhance the canopy, or the converse. So you can speak of ground notching or canopy notching. This is possible if you have at least 2 acquisitions. If you have more, then you can better shape your filter, let's say. This is just a synthetic example, again, that shows with these 3 responses from 3 layers, if you design a good filter, you can suppress the leakage you have from the ground. And this, again, is Pauli composites. And in case you notch the ground, I would say orography is better highlighted and the image is greener. In case you notch the canopy, the image is more reddish, which is indication of double bounce. And another line of work which is also interesting is the study of temporal change, because of course, let's say, by standard tomography, you assume basically that your forest doesn't change over the acquisition time of the stack, which is 21 days overall for a 7-image stack. But actually, weather events happen, so you may have local variations indeed. And the funny thing is also that the spatial and temporal baselines of biomass are intertwined. So you progress 3 days, but you also increase the baseline more and more by this 15% of the critical baseline spacings. So an idea can be, for instance, to compute tomography standard way over an area, and then group, for instance, all the tomographic profiles that you think belong to a same type of forest. From these, you can, by an eigenvalue decomposition, for instance, try to derive a basis of function that should represent your forest shapes, so a kind of a dictionary of shapes, if you wish, which are, of course, the eigen vectors. You see an example here. You may try to use also Polinsert to announce this ground volume separation. So you can do this game on volume-only tomograms, if you try to separate first ground and volume by Polinsert. And then you can express basically your reflectivity like this, no? Like a sum of these functions. Usually 2 components already give you a lot. It may not be perfect, but it's already something. And then you're left with the coefficients to estimate. Which is a mixing coefficient that basically regulates the amount of, let's say, volume and ground contributions based on this basis of functions. It can be used also as with a single baseline, this approach. So, and in this way, you can account for variations, no? Because you're not mixing or averaging effects over more than 3 days. This is an example. So in here, you see a very long strip over Peru. You have Jedi forest heights. You have interferometric coherences for 2 different pairs, spaced by 6 days apart in this case. And you see that for the same area, coherence has variations. You see the dark shapes change from an image to another. So in here you have the Polinsert ground phase, the phase of the ground, and in here you have instead the mixing coefficient that was estimated over this area with this approach. And basically going from blue to red, it means you are giving more importance to the volume, no? The volume contribution matters more. So the guess for the time being is that these dark coherence areas may be caused by rain or weather effects in general, let's say. And if you look at the ground phase image and the coefficient image for each of the pair, you see that the dark areas correlate with higher ground phase and lower volume coefficient. So it may really be linked to some water content that is located on ground, as also was hinted by Irena in his previous presentation. So it's let's say the philosophy of this is not assuming that you have a single stable forest structure over time, but try to account also for variations. And this brings me to the end. Let's say I hope I gave you an overview of the activities we are doing, so standard processing and something a bit less by the book, let's say. At least for the standard processing part, there is an ongoing project in the framework of biomass activities, which is called Biotomex, and includes also the DTM estimation from previous presentation. Our plan is, let's say, by next year at some point to release all these algorithms as an open source software in Python language in the name of open science and with the spirit of biomass activities. If you want more information about our activities and the mission group activities, you can follow this link. And you will find some documentation, a link to the biomass processor, which includes a single image formation processor, interferometric processor, and the forest products estimation already. And that's it. Thanks a lot.
Thank you a lot, Francesco. Type of question? Yes.
Yeah, could you comment how you, on the specific example of the biomass estimation, how you approach this if you have like a full tomographic stack, or if you just have like this ground-notched version, like what is, let's say, the difference in quality of your biomass estimation that you can get from the, let's say, 2 approaches? Yeah.
Yeah, I would say, of course, 7 images or slightly more sometimes if you're lucky, but even already 6 give you maybe a better rejection of the leakage, especially if you go with the tomographic notching approach, like also Laurent was presenting. So you have more information and more degrees of freedom there. In the int phase, we will have just to go by the 3, which is already better than 2, but let's say a little less. But we hope this would be enough to address this maps retrieval. And then it's, of course, up to validation and investigation, yeah.
Okay, but you're not fundamentally doing something different in the 2 scenarios, where you, in both scenarios, try to remove the contribution from the ground and then...
Yeah, well, actually, let's say, for the time being, well, the standard approach, we started designing the notch for the int phase, which is done actually in a very simple way. So if you already phase the images by ground steering, you can just subtract 2 images. If you have 3, you can try to interpolate and generate, let's say, a synthetic secondary image to subtract to the master. Then we started looking into this, so designing a better filter. I think the door is still open to decide what is the best approach. Let's say we have to test and validate a lot, I would say, and then let's see by comparison. Thanks. Thank you.
Yeah, if you have time, thanks, Francesco. So if you go back to the biomass estimation slide, where you had the backscatter at 30 meters. Yes, this one. Now, for NICER, for example, we are using simple backscatter and correlate with biomass, and we see a shape that looks very much like this, without tomography, without P-band.
Yeah.
Can you comment on that? I mean, is this, I guess somebody, I'm on the tomography side, but I'm kind of playing the devil's advocate. Somebody looking at this as, 7 cycles, P-band, and I'm not even able to map the biomass of, this shape at least looks like the one that you would get without tomography at P-band, perhaps even L-band. Could you comment?
Well, I wouldn't say you get the same shape, actually. Let's say your comment, I see it more in line with the notch. Actually, we experienced that tomography gives you a better rejection, whereas the notch, maybe we have really to design a smarter filter than just subtracting 2 images. But yeah, I mean, it's not really, let's say, slopey, like a line that you would see more clearly, but it's already something. But also, this is also one test site. So the more we process, the more the experience that we build up onto this.
So maybe a better question, maybe I could have asked is, if you don't do tomography and you do the HH or HV backscatter versus biomass, do you see poorer performance when you extract biomass with this approach? I'm just curious. I'm sure this was asked before.
No, it's, well, HV still gives maybe the best correlation, but if you look at tomograms, I think you already see quite some things from the HH also. So yeah, all of them contain information. And then it's more really about how to fine-tune this approach or find what is the best balance, how to best use the information that we have.
Thank you.
Thank you, Marco. We have time for one more question. So if not, I have maybe just one. Because for tomography, we have 7 bars, it's okay. But what about the interferometry phase? How can we dealing with the atmospheres strong? How can we do multi-screen in that case?
Come again, so it's from the tom to the int phase, it's about multi-screen?
For the interferometry phase, we have just 3 baseline. Can we do multi-screen?
Yeah, of course you can do that. No, multi-squint, you can wear single pair. I would say, again, from 7 to 3, you lose a bit something. Also, it's more for the ground phase estimation. Then you can still do that. We will still do that, of course. But you have less acquisition, so it will be more noisy, at least.
Right. Thank you. Thank you a lot. Thank you a lot, Francesco.
Yeah, thank you.
So with that, we would like to welcome under course from Technical University of Denmark. So he will turn biomass from biosphere to cryosphere. Welcome.
Thank you. I'm giving this presentation, and I would also like to introduce my co-authors, Jørgen Dahl, John Merriman, and Julius Kokholm. They are, together with me, members of the Biomass Disk, and Jørgen is actually the PI for the ICE secondary objectives in the disk. Just a brief introduction to this, using biomass for ICE. So ice flow mapping is a secondary objective of biomass. It's expected there are some advantages to the P-band wavelength, so reduced interferometric fringe rate when we have the really fast flowing glaciers, and also an increased temporal coherence, so we rely less on the impact of, we don't have as much impact of surface processes like precipitation. Of course, the real big problem is the ionosphere, which is really bad at P-band, and especially also in the polar regions. And I will show some examples of this and what we can, some approaches to combat that. So a bit about the acquisition plan as it actually affects the ice velocity mapping. So if you haven't seen the biomass presentations earlier today, I can just briefly repeat. We have one swath that is repeated 7 times with 3 days separation, and then after 21 days, the satellite is rolled, the next swath is acquired, and then again for the 3rd swath. Then the satellite is moved, and so then it's observing some different ground tracks. So this means that we're not able to get a long time series like Sentinel-1 and potentially NISAR, but we get more like a snapshot temporal coverage with 7 acquisitions over one area. But that also gives us some advantages in relation to the ionosphere, as I will show later. I would also say I think INSAR is the only feasible way of retrieving ice velocity with biomass, because the range resolution of 25 meters makes range offset tracking really noisy. And in the azimuth offset tracking, that is mainly ionosphere that we are seeing, mainly the shifts due to ionosphere. But of course, we can employ the azimuth offset tracking to do co-registration. Also, since we only have INSAR, we can only do 2D velocity inversion in these diamond intersections of the ascending and descending tracks. But there is also potential to combine biomass with other sensors, and I'll also show this. Just a bit about the expanded ice mass. So the disk has been working with ESA to expand the ice mass of biomass. So now we are actually, from May, we acquire the grounding line in 100 kilometers inland from the grounding line, and 100 kilometers out from the coast is covered by biomass. So that actually also means we can, it actually sees the grounding line almost everywhere in Antarctica. This is some of the very first results that we had with our ice velocity processing chain. We have a mature ice velocity processing chain, and I should say we've not been using the stack product. We are starting from level 1A SLCs and then doing the processing with our in-house software. These interferograms are taken over Pine Island Glacier, which is quite fast, moving several meters per day. And this, the co-registration here was done using a DEM orbit and an external average, multi-year average velocity map. Actually, that was enough to get these really nice, I should say we also estimated a constant in range and azimuth using offset tracking, but we could get some really nice interferograms and some really beautiful fringes even on the fast-moving part of the glacier. We can actually unwrap this. We do also flatten these with the external velocity map before unwrapping, and then add back this phase after unwrapping, because that allows us to also unwrap some of these where the fringes are very dense. And of course, this has to be done prior to the multi-looking. But that allowed us actually to combine some of these acquisitions and make a 2D velocity map looking like this. And it actually looks really nice compared to, for example, offset tracking with central INSAR, which I'll show in a minute. We see there might still be some atmospheric effect in these blue areas here. If we compare to Sentinel-1, so we did also Sentinel-1 offset tracking. So this was during the period where we didn't have the one-day repeat, so we used the 6-day offset tracking. And we basically used all the Sentinel-1 data from that period there, and we got this velocity map on the right. And if we compare with biomass, it's actually, we see that because biomass relies on INSAR, it's less noisy, and actually the coverage is also better because we have really good coherence also on the fast-moving ice. So just a comparison around some profiles of the biomass and the INSAR and the Sentinel-1 offset tracking, and we see they basically match, but the biomass results are just smoother and has a better spatial coverage. One thing we also did was to try and combine the biomass INSAR and the Sentinel-1 offset tracking, so we can use the INSAR line of sight velocities, and then when we do the 2D velocity inversion, we can do that together with the range and azimuth offsets from Sentinel-1. And that actually, I think, shows some, in the regions where we have an overlap between biomass and Sentinel-1, I think actually it reduces the noise quite considerably. Here in the left part, we see that we get a much less noisy velocity map. So I think that has also a potential. So this was some really fast-moving scenes where there wasn't the ionosphere was there, but it wasn't that obvious. Now we move to a different part of Pine Island Glacier. This is data from tomography, the latest tomographic cycle from May 2026 up here, and we are looking at this ascending and this descending track. And to characterize what does the ionosphere actually look like, we do offset tracking, and I'm showing here the azimuth offsets for the one descending pair and the one ascending pair. The color scale here is -1 to +1, and that's pixels, so that's 7 meters, ±7 meters. Sorry? Ah, yeah. At the bottom. Ah, sorry. Which one? This one. Oh, okay. Sorry. Yeah. Okay. So what do we see here is there's -1 to +1 pixel, and then of course sometimes the color scale saturates completely. But we see here that we have a number of interferograms which actually have relatively low azimuth shifts, and then some that are really affected by the ionosphere. And what we then did here was to first we did the standard co-registration, so not adaptive, just with these DEM orbits velocity map and a constant range and azimuth shift. And we see then when the ionosphere is bad, we get decorrelation. If we do an adaptive co-registration, so we use the azimuth and range shifts, and then co-register using these everywhere in the image, we see we can recover the coherence, but there are still some, I think there's still some phase artifacts in this one that, for example, here that we don't see in the others. So the adaptive co-registration can recover the coherence, but there are still some phase impact. And I want to just the same for the other direction. We see also this one we recover coherence in most of the image, but the phase is completely destroyed. If we try to then do 2D velocity inversion using these, I tried then using pair 1 from the ascending and pair 1 from descending to make one map, pair 2 from ascending, pair 2 from descending to make one velocity map, then it looks like this. So the first one here that's where one of them was really bad. We see something that really looks strange. And we can compare this to, I made also Sentinel-1 one-day interferometric velocity map, so we can compare everything to this. And we see actually most of them look good, But what we also can do is, because we only need one velocity map in principle to get a velocity for this period here, so we can just take the interferograms that have the lowest ionosphere and then combine them, and that's what is shown here, what I've done here. And that actually matches very well the Sentinel-1 map. If we just look briefly at the statistics, we see also that doing this with combining these good interferograms, that actually gives us a relatively nice agreement with the Sentinel-1 one-day product. Then I'll show some other examples here. This is from Smith Glacier down here. And this is from the period where this is also from the period where we have Sentinel-1 one-day interferometry. And I'll show first the Sentinel-1 interferogram, which I think looks really nice also. Really, I think these are really beautiful data. But of course, the fringe rate is high, and there are also some areas where we do get in the shear margins where we basically cannot really retrieve this with Sentinel-1 INSAR. We lose coherence here. But if we take a biomass interferogram, so of course it's a different geometry, but actually we see the shear margins, actually they are quite well defined here. So this is with the standard co-registration, and if we do the adaptive co-registration, we do recover some coherence here, although back here it's still bad. So since I didn't have crossing orbits here for biomass, so I just did a line of sight velocity, so unwrapping calibration, and then plotted this here. And then to compare with Sentinel-1, I did 2D velocity from Sentinel-1, so 2 INSAR pairs from Sentinel-1, and one ascending, one descending, in order to make a velocity map, which I then projected into the biomass line of sight direction. And then it looks like this. So we see there's a good agreement, and actually biomass has better coverage here in the shear margins where Sentinel-1 loses coherence. There's also some features here which I don't really know what it is, but it doesn't look as if it's really there in Sentinel-1. And I did also see this in a completely separate interferogram from two independent SLCs, so it's definitely not due to the atmosphere. But what it is, it could also be some kind of artifact. I don't know yet. But I think still it seems that biomass can supplement Sentinel-1 very well. Another example here is from Evans ice stream. So Thomas Nagler showed some Sentinel-1 results from the one-day phase in this area on Monday. We found also some biomass interferograms here. So this is one example here. This is one with we were really lucky. There was almost no ionosphere, and I think these interferograms are just really beautiful with biomass. If we look at the stack, so now we look at all the 6 interferograms that we can make from the 7 pairs. We see also in this case there are really some that are corrupted by ionosphere. So this one is bad. These ones are really bad, and the colors here indicate that probably the second to last SLC was just had a really crazy ionosphere. So I'm only showing the 3-day interferograms here, but of course you can also, if the fringe rates allows it, you can also do longer temporal baselines. For example, if you don't have a lot of ionosphere in the last one and the first one, you can do long temporal baselines, and then you increase the sensitivity to motion. If we look at these interferograms, how they look just with the standard co-registration, I think this one actually looks good. If we do the co-registration, I don't know if the coherence is increased in most places. I think down here the ionosphere is probably so bad that probably they couldn't even be focused correctly. But what we can then also do so in this area, we also have the grounding line in the image, and we can do double difference INSAR to retrieve the grounding line. So I did that between these 2 images, and that is shown here. So we see it matches the measure's grounding line very nicely here, and we see these fringe belts here, which indicates the grounding zone. So, this can also be done, of course, in other parts of Antarctica. I have some examples here, one from Pine Island Glacier. So we see here, we can see the grounding line here. Of course, there is some noise here, but this was just one double difference interferogram. Also Thwaites, which is also a challenging area. We also see the grounding line here from Sentinel-1. From the biomass, and which I think would be impossible to see with Sentinel-1, at least with the 6 days. So that's, I think, is also a good application of biomass. Another thing, something we've been working with a lot in Sentinel-1 data is looking at these local vertical displacements due to subglacial water propagation. And this was actually quite interesting. We saw that on Pine Island Glacier, which is really fast moving, we saw one of these bullseye features here, which we associate with subglacial water propagation. So it's water that's filling in somewhere under the ice and pushing up the surface, or water leaving this area, and then the surface is subsiding. I haven't done an exact analysis here, but I think in Sentinel-1 we can only see this, at least with the 6-day pairs, we can only see this on the the slower moving parts of the ice sheet, but here we can actually also see it under the fast moving ice. So I think also of course, we don't get long time series, which would be nice if there are some longer events. But this temporal resolution of 3 days could actually also provide some interesting observations, because sometimes these water propagation, it can propagate really quickly during these days, so you would be able to track, for a short period, you will be able to track with high temporal detail what's going on. So conclusions and further work. I think biomass shows promising results for ice flow mapping, although there are challenges with the ionosphere. The acquisition plan and the requirement of crossing orbit that limits the pure INSAR coverage of biomass over the ice. But of course, we can combine with Sentinel-1. And I've just say here Sentinel-1 6-day repeat offset tracking, because that is sort of the standard acquisition going forward. Of course, it could also be combined with NISAR if we want to. Further work is needed on the ionosphere mitigation. So we are just doing now the data-driven co-registration, but the phase must also be handled. We've done some initial experiments using the biomass stack processor and with this multi-squint correction, but I think this is still too early so we haven't really got any good results yet, but I think there's also a lot of fine-tuning and maybe further investigations to be done. But I think actually the fact that we have all these 7 repeat acquisitions, that means we can often get good estimates of even though there's ionosphere in a lot of these acquisitions. And finally, grounding lines and this subglacial hydrology dynamics, they are other, I think, interesting applications of biomass. Thank you.
I have a question.
Yes.
Actually, two. So the first one is more technical. On average, to produce those velocity maps, how many interferograms do you need to process?
So to produce a velocity map, we only need 2 interferograms, basically.
2 interferograms to disambiguate the...
So one ascending and one descending.
Okay,
yes.
Ascending and descending.
Yes.
Okay, great.
Yes.
And my second, the other question would be, what is your approach when the ionosphere is too bad? So are you just discarding the interferogram?
Yes, so we haven't made an automated chain yet, but I think it would be basically discarding these interferograms. So I think the approach we'll probably be using is to do all the possible combinations, also the longer temporal baselines, and look for the ones that are where there's not too much ionosphere, looking at the azimuth offsets. And of course, if you can do a long baseline interferogram, you have much more sensitive to the ice flow, and the ionosphere is the same. So.
And then a question that I needed to ask for the summary session tomorrow.
Yes.
Do you think that biomass is more complementary to Sentinel-1, or it is just better than Sentinel-1?
I think I would say it's complementary to Sentinel-1. I work also a lot with Sentinel-1 ice velocity. I would say it's this coverage of both the temporal and spatial coverage of Sentinel-1 is really nice. And I think biomass can be a good complement, definitely.
Can I just follow up on your last point? Don't we see different things with biomass and Sentinel-1? So are we assuming that the velocity is the same when you compare? I'm not an nice person, so it might be yes. So, but isn't this like, you know, difference in what we see impacting into the combination and the comparison and everything?
That might well be, but I think that's difficult to say from these data, because they're all. I think it's difficult to do for example, if you wanted to do tomography and you then also have the ice flow to deal with. So I think it would be different to separate these things. But I do think, especially on the fast-moving glaciers, we have a lot of surface scattering. I think because there are a lot of crevasses and stuff going on, and so I think there it's probably a good fit to this. It might be different in the interior actually, but if we really go to the slow-moving parts there, I think the ionosphere is probably also challenging. Yeah.
Thank you. Thank you, Anders. Just linking to this. So, do you think, on average, the situation regarding ionosphere is like you showed, or even worse?
I would say it's probably a bit worse than because for a presentation you want to also show some results, something place where you have results. I think it also depends on where in Antarctica. I guess if you go to East Antarctica near the magnetic pole, then it probably becomes more problematic. But I have seen some examples of data where there was basically no interferograms that were useful. So that does happen. But I think we will often be able to at least extract some velocity maps, I think.
Thank you.
I have another question. Do you think that it makes so? Since we say that biomass and Sentinel-1 are more complementary than substitutes of one another, do you think that it makes sense to envisage a synergistic use of the two? So like you can use Sentinel just as a prior, because it is not so much degraded by the ionosphere.
Mm-hmm.
And then on this basis, like use biomass to complement Sentinel, so like you can fill in the gaps where Sentinel is not coherent or go at a higher resolution, maybe?
Yeah, yes, definitely. I think that's a really good. I think that would be the way to go. Also, this this regions where Sentinel only can work with offset tracking and it's very noisy there, we can reduce the noise by combining with biomass line of sight velocities and then combine them in the correct way. Yeah, definitely.
Okay, thank you. We have to move on. Thank you a lot, Anders. So with that, we move from a very cold environment to a very hot environment. We welcome GB Besky.
Thank you very much. Hello, everybody. I would like to take you to the desert now. It's another secondary application of biomass. This talk is just a follow-up of work that I presented during Polinsar workshop in Ljubljana, but now we decided to join forces with Laurent, Stefano, Yang Hai, and also with Francesco. And so, where we are, why biomass for the desert? First, let's have a look if we can learn something from that, whether this is suitable for geological applications. Can it provide any unique insight? And what is the capability of P-band and Polinsar in imaging on characterizing subsurface, geological surface? because since with this unique low frequency radar, we can expect some penetration. But if so, how deep is the presentation? Can be model the surface bedrock structure. So maybe we can already deliver some numbers on that. So first of all, geologists like to know where they are. So where you are now. We are now in the heart of Sahara. It's the highest mountains in Sahara. This volcano, Emikusi, was already presented by Francesco when he was talking about these atmospheric corrections. However, of this nice, beautiful landscape that you can see, this is very unpleasant place on our Earth because of climatic zones and also because of political situations. So no ground truth data at all for this moment. There are also only some published materials by the groups of Libyan and Chadan geologists that we can find in literature, because this area is on the border between Chad and Libya. And what is more, here we have one of the oldest rocks that exist on our planet, exposed on the surface, and this is the reason why geologists are interested in this, because we can learn a lot about these early days of history of our planet. And also they contain a lot of interesting raw materials, like these rare earth elements, some radioactive stuff. That's why it's interesting for us, and usually it consists of this highly metamorphosed Precambrian crystalline rocks. You can see on this cross section, and on top of that we have various sedimentary rocks and basalts. So specifically today I would like to speak about this tiny area at this northern tip of the Tibesti Mountains. It's inside Libya. If you will look carefully on the published geological map, it's not very new, but this is only available at the moment, 1 to 1 million. You will see it quite easy geology without any complexity. That consists at the southern tip we have this very old rocks, lower Proterozoic lower Tibestian formation rocks. Then on top of that we have various sedimentary rocks from Eocene, Paleocene, and also Jurassic and Triassic sandstone conglomerates. From Paleocene and Eocene are usually limestones and dolomites. On top of that, we have a big pile of basaltic rocks, different kind of flows, cones, stratovolcanic rocks. And on top of that, we have aeolian sands that masking the rest of the geology in the area. So let's have a look how it looks like on optical image. On optical image, we don't see much. We see primarily these basaltic rocks and generally just aeolian sand and some structures that we can try to interpret. So let's do magic now and put biomass data on top of that. And this image becomes much more clear now. We can see through the desert. There are some interesting strips. If we will go a little bit back, you can see that this is following the structure of sand dunes. This is something that appears at the beginning when we see the picture. And there's also a lot of interesting stuff that I would like to show you. First of all, let's have a look on that sand dunes. The sand dunes are also present in Copernicus DM. If they are present on DM, then we have some numbers. If we have some numbers, we can measure how high these dunes are. They are quite significant. There are 35 meters, 70 meters, 34 meters. And since they are visible on this on the biomass image, and due to that we cannot see through the sand in this area, we can see that this depth of sands, it's unpenetrable for P-band radar. So at least we have first information about the penetration depth from this just simple analysis. And if we compare this with geological map, we can see that in a big portion of the image there is a confirmation that this geology, what we saw on the map, is present on the on this P-band image. But in the northern part, we can notice that it's not like that. There are some differences. So let's look into details. Okay, first of all, I didn't yet mention that we are just looking at the Pauli composition. We saw today a lot of Pauli compositions, color compositions in different presentations. And what is interesting here, that we have only blue color mostly. So it means we have mostly surface scattering mechanism, just some little areas with double bounces, and almost no volumetric scattering. So it means that this sand surface, it's really, this radar signal penetrates through the sand and not create something like volumetric scattering mechanism. Let's see this first, the southern part. Let's start from the south and go to the north. We saw this remains of this lower Tibician, the oldest rocks, and we see these structures of these metamorphic rocks, and also small granitic intrusion that was also tectonized during this metamorphic metamorphic processes. In this part, we have this Eocene sandstones at the surface, and the rest of the area is covered by basalts. We can see the big area covered by basalt, but you see that it's also not uniform. There are very bright areas and very dark areas. The dark areas means that the basalt surface is very flat. Probably we have this typical lava flows, and on the other areas we have more rough surface, probably with some pumex and some other stuff related, other products of eruption, not only pure basalts. Let's go a little bit more north, and also notice this part. It's just one of the processing issues due to very low backscatter area in this part. So this green color that doesn't come from volumetric scattering, but it's just processing artifacts, and processing is still evolving. Francesco promised that we will have soon much better data for our analysis. So okay, let's go a little bit more north in the center part. First of all, if you look carefully, we can notice some linear structures that are could be interpreted as fault and fracture zones that creates boundaries between different rock types. So it means that it was also tectonized later on. There was some tectonical activity that fractured these sediments into pieces. Also, still we can notice these sand dunes, and between that we can interpret different rock types, like these basaltic rocks, which are similar. These three outcrops have very similar structure to this big basaltic area, and these reddish colors that Probably it's related to some double bounce reflection type. It correlates with what is on the geological map, Jurassic and Triassic sandstone and conglomerates. Probably this area is this below the sand, of course. It consists on some boulders, some small rock parts that this double bounce type of reflection was developed in this particular area. And what else? This very unified blue color without any structures, according to its location. It's this Paleogene Impression sediments, dolomites most likely. So everything is under sound, and it's in the northern part we have something that was not mapped on this geological map. Probably it's also Paleogene, Eocene sediments. You can notice some boundaries between the area. They're following the same shape. So I would think that this is also horizontal layers of different rocks. And also the surface of that rock might be very rough because we have very, very high backscatter here. So probably we have also the boulders in the size of radar wavelength. It means half a meter, 70 centimeters, something like that. And what else we have interesting here, this Pleistocene and Paleo streams that are evident in this, especially in this area. They are developed in this Jurassic and Triassic sandstones, which are completely invisible on the surface. So now let's go to get some numbers from the data. So there was some processing of the data done by Yang Hao. Especially we focus on this part where we have at the surface just pure desert. Here is just a biomass intensity map that you can see pretty much the same that we observed on this Pauli decomposition. And regarding the methods, we did ionospheric correction according to what was described by Stefano today. And also we were trying to extract this underground structure, the surface that lies below the sand. So the problem is similar, but in other round what we have in tomography, that it's very hard to get this the terrain surface. So we did the procedure that Francesco described very well, and also it was also his idea to try to find some points for calibration of our data. Of course, in that part it was rather easy because we have a huge exposure of bare rocks, but on this area we have pretty much nothing. But if you look carefully if you zoom in into some optical high-resolution data, you will find some tiny rock exposures, some bedrocks are on the surface, and we can use these tiny spots to calibrate our data, at least to try. This is the result of the processing, the best that we get for the moment. These are preliminary height estimates relative to Copernicus DM, and this is the area of the bedrock part that is the most closest to the surface. Unfortunately, we lost due to multi-looking that with window 160 by 160, which is 4 by 24 pixels. We lose the information about these paleo streams. However, we can see very clearly some tectonic structures, some faults and fractures that cutting this part of the bedrock. And we can also notice from the color scales that everything is between +5 and -5, 0 in fact, because there is no yellow color. So between 0 and 5 meters, maybe a little bit more, it is something that we can measure as a bedrock structure. So this results correlates with what we measure on the sand dunes at the beginning. That if and it's more or less the depth of the penetration that we can have. These are just preliminary results that it needs to be further analyzed in the near future. And going to the conclusions, yeah, of course, there's geology and pollines are easy. And what? We can confirm that biomass is a good tool for study geology in arid regions. And also the biomass penetration capability can be confirmed with direct relationship with subsurface geology, because I showed you on this analysis that all that part of this geological map could be interpreted and draw again with new geological boundaries between these different units. And also this preliminary results from sand desert environment indicate that these underground structures may be detectable down to approximately 10 meters below the surface. I believe that in future we can verify that and put here even more accurate numbers. And yes, the sand still have more secrets to spill, and I hope in the future we will have some much more interesting results to present. Thank you very much for your attention.
Okay, thank you a lot, GP. Yeah, time for question, everyone.
Congratulations. So you say good, but this is amazing. I'm a bit biased, of course, but the complementarity here seems to be more with Sentinel-2, Sentinel-3, Landsat, optical systems that are used to create or to, I don't know, improve these geological maps. This is something that you actually check. So a sort of complementarity with optical mission or hyperspectral missions.
Yes. We did also some analysis with hyperspectral data, but not exactly for this area. On the southern part, where you have really this bedrock on the surface, then you can really interpret that and also use that, because these types of rocks are in different parts and also buried underground. So if you will have some evidence on the surface and you know that this is specific type of rock, then you can extend your interpretation under the surface, of course.
So we are complementary to those.
Yes, these are the complementary source of.
This is a game changer in geological remote sensing, right?
Yeah, it's something completely new that never been described before.
Wow. Okay.
Thank you. Anyone?
In the images that you showed, did you use like a single SLC or a single backscatter map, or did you stack all the acquisitions that you had, like to increase dynamic range, beat down speckle, and so on?
Yes, I did this kind of analysis, trying to stack all these images and remove the speckles, but in fact, the improvement was just at the minimal level, so I decided just to do it on the best quality image from the stack that was available at the moment. Maybe after reprocessing the data, this stacking technique will help, but so far it was not very helpful.
Okay, thanks.
So maybe I have just one question about, can you comment about the 10 meter below the surface, where it's come from, or how can you quantify its number?
It's came from the analysis of this tomography data first, and also this preliminary analysis of this height of the sand dunes that are evident on this data that are not penetrable by the radar.
And its sensitivity to polarimetry, co-bond or cross-bond is the same for 10 meter? I mean, with co-bond maybe it's better penetration, or it's the same with the cross-bond?
I don't know. Okay. According to some previous laboratory studies, for a P-band, the penetration depth was about 2 meters. But what we see on that data, it is for sure some more. Of course, yeah, we are planning to maybe in the future to do some real field work to compare with the real data, but definitely not for that specific part of Sahara.
Okay, maybe one more question, because this is in very hot environment, people searching for underwater. Is there any chance to use in B-band to search in underwater?
There are water reservoirs over Sahara, but they are much deeper, and I don't believe that we can use that for water detection. Of course, why not to try in some other specific areas? But I don't believe that we can use it in maybe in some winter conditions, which is a little bit less dry. Oh, this is also the data from winter. Yeah. That's it. It could be also that those paleo streams are, we can distinguish them because they are less dry than the neighboring desert.
Okay, thank you a lot, GP. Stefano.
Thank you.
Okay, so at this point we have the discussion session. So we can invite the other chairmen to join us, Laurent and Muriel.
Just here.
First, I wanted to confirm the typo, ZB, so thank you very much for pointing it out. So the dates are actually much sooner, so please feel free to register for the webinar. Now we can go to the seat questions. Stefano.
Okay. So okay, the first. So we have four. Great. Okay. So the first one is I think that we try to pass the message that biomass implement a complex processor because it also includes interferometry, and all the products are generated by interferometry, and also it will deliver this product, which are the level 1C, which means that the data so it delivers co-register stacks of 7 images that have already been phase calibrated, meaning that in the ideal case, if we do everything perfectly, the ionosphere has been compensated for, so coherence is good, and also the ground phase has been compensated for, meaning that virtually when you read that the phase is 0, it means that you are on the terrain. This is as good as we would like to be. Ideally, of course, in practice, it means that there will be errors, there will be artifacts, so we don't have to hide. Let's say we're doing our best, but it will not be perfect. Maybe in some cases, your processing or even a traditional processing will be better. So I think it's important, since we are here at Fringe, so you are the representatives of the interferometric community, to hear your opinion about this. So what are your feelings about this processor that Biomass implements? Bring the microphone, but you take notes. Who was it?
I think, yeah, really great presentations all around. I think it's great that ESA is going this one step further to promote or to produce and then to promote these like higher level products of like different kinds. I think the one thing that I was either missed or were not talked about during the sessions is how when you have these stacks, how the neighboring stacks compare, because there's a lot of adaptive processing between scene to scene, from stack to stack, and so I'm curious to see what if I want to do a mosaic and put like neighboring stacks to one bigger area picture. How well do they match? Do you have requirements on that? Yeah, I was curious.
No, indeed, everything is done frame-based, like I was mentioning in my presentation. So indeed, we are observing right now some inconsistencies when we try to put them together, because for the moment, we do not manage to have this consistently done across the data tech, because everything is data-based in terms of correction steps. So I think indeed, this is something that we have to look at, because of course, in a perfect world or where all the corrections work as they should have, you should have some sort of consistency. If not, some small things that we could try to tackle at level 2B or level 3 or whatever by simple smoothing over the borders, or doing things in a consistent higher level product. But I think that we still miss a bit of work to do things which are globally good, that of course the things are working and they have limitations, as Stefano was saying, that end up in some corrections not being fully consistent. Still, I think that it's important to use the data and to try to fix these things together. So which is also something that to me connects with the last question that I put here. Because we hear a lot of people asking for data and processors, and then we put the data and the processors out there, and now we need people to actually use these things and contribute, because we are putting a starting point there that we want to evolve and to improve until the maximum that we can. So, I don't know, that's my opinion.
Maybe one short comment. I think we will need your feedback when the products are provided to the community at level 3.
They are right now,
yes,
by the way. So
yes.
the level 1C are being generated and available right now.
Yes, and the level 3, for instance, product for AGBD and FH will be linked together, because we will use biomass allometric relationships to estimate them, to correct for bias or variabilities. So there will be different level of processing. One question could be, would you like, as a community, to get the ground SLC product as this is done for NISA? No, ESA doesn't want to.
I think that if you go to your question, because the problem is similar. Now, if you want to provide the geocoded SLC, you need to make sure that the corrections which are spectral based are all done properly beforehand. And this is the same issue we are facing here, because people usually want, and they are up to using the data, if the data is good and processed correctly and everything works perfectly. If it doesn't, then they want to process the data themselves rather than trying to help and support into correcting this in an operational manner. So to me, this is a challenge that we need to try to overcome together somehow as a community,
The question is more, would you like, as an interferometrist, to look at coherence maps in ground coordinates? Would be useful for you? Are there some things that we could not do with these tomographic slices? maybe for people working on movement, I don't know, on motion. Marco?
So I have to think more about the tomography, but I think you can geocode properly tomographic layers, right? I mean,
this has been done.
Yeah.
This has been done, yes.
Oh,
this has been done, yes.
But okay, the tomographic layers, okay, but what about the geocoded SLC?
No.
That's not...
Only tomography, so powers.
Right, powers, I'm sorry. Yeah, what I was thinking is the geocoded SLCs. I don't think I have to think more. I don't know if you can do the tomography easily. Yes, but maybe you can. I don't know, with some corrections or additional specific processing. But what I can say is that we have seen with NISAR a spike of access and usage of geocoded SLCs, even from people, even from me. I didn't have time, and I had to use geocoded SLC, and I was happy. I was happy, and I've seen this from other people too. So I suspect that if we move to the geocoded world, not as a final product, earlier product, I think this will be beneficial for the tomography community, provided that all the corrections are done properly, or at least are understood, the errors that remain in the data, because that's the key, really.
I think that the people got used with Sentinel data to have geocoded remote sensing information, and this is the first question they ask me. People who are not specialized in radar is, are the product geocoded? Can we compare them to our map? It's coming.
So to go back to the first question, so then shall we conclude that up to checking the consistency across neighboring stacks, you are all happy with that? This is what we are gonna write down. So speak now or never.
So I just wanted to say something. Here, I'm saying. Right. I just wanted to confirm about the geocoding of the images or products, because now we are facing with all this cloud computing, and we actually compare the different products images, and there's a really high demand for having the cloud computing formats and geocoded, so that actually we can avoid many of the errors by just when we process something. So when there is less this ready analysis data there, so we can basically focusing on the analysis itself. But if there is some problem in the pre-processing, it can be, for example, with the flagging. So for example, there's this flag, this taking care about these images and so on. But I think this is really a good way to go. Thank you.
Maybe on the same topic, so with airborne data, what we did often is to work not with geocoded SLC, but with ground projected as a SLC, meaning that one coordinate was azimuth and the other the ground range, but focus according to the DTM. I think that this projection has some advantages because you can more or less easily do some filtering because the spectra are easier than when they are in that long. And you can geocode it with a simple rotation and translation. So it's almost it. If they're focused on a DTM, you can do it. On the DTM, I mean. That can be an intermediate or a compromise between the two, I don't know.
At this point, the tool to perform this rotation should be provided to users.
You provide also the tool to perform the geocode, and so if in the end you have to put an input to a tool, then it's not the big difference if you're starting from the GRD or from the SLC, no? So exactly, yeah. So the joke.
So for NISA, we went the other direction. We allowed some imperfections with the geocoding, and then we provide still the range Doppler SLCs if somebody wants to do the proper correction processing can do it. So we didn't go for that intermediate processing. Yeah.
With biomass data, you have not very big data files, so to geocode them, it's rather straightforward, and it's not much computation time. So I think it's not a big deal like with Sentinel or with Nicer. They are just small files. So.
That is true.
In the product, we have an amplitude band with the geographic roots, so you should be able to open it directly in QGIS, in whatever GIS software. So I don't know if this is still not sufficient for your kind of use.
You mean to make a plugin for QGIS too?
No, already there. If you try to open,
So shall we pass to the second one?
Yes.
Marco, synergy with Nicer.
Okay. Yeah, sure. So I guess one of the questions that we can pose for this group is whether we see synergies. What does the community think in terms of synergies with Nicer? And this could be, of course, in general with the biomass mission, but also Sentinel, could be multi-frequency, in general. This is in a broad sense. What type of synergies do you see, and what are your expectations really from having an L-band machine like the one you have seen today? It's going to give you L-band data globally every 12 days, twice actually, ascending and descending. So, so this is a new frequency, relatively, it's not a new frequency because we had Pulsar, we still have Pulsar, and we saw some presentation today, but definitely with time series and global coverage is a new measurement, similar to Sentinel. So, any thoughts on what is the challenge or the opportunity there, or what agency, maybe space agencies, can do to facilitate that synergistic, combination of the 2 or 3 frequencies?
Could you provide quad-pole data for the areas that are not available for biomass, for Europe and North America, for example?
So quad-pole is available on a selected sites. And so there's some sites in North America. I don't think there is any sites in Europe. There is definitely the full India country is covered with quad-pole in the descending paths. And there are some calibration sites here and there. But you heard Paul Rosen this morning. So the observation plan is revised every 6 months. And in fact, we already added a little bit of more polarimetry in the last round, and so we're actually even exercising the deterred polarimetric mode, so no gaps. So it's gaining a little bit of more importance than it was before. So if there is a push, especially with the biomass mission, maybe we could increase,
As a community, maybe we can recommend this kind of things to ask for that in the future.
Yeah. What you showed actually is a good basis for proposing new data.
One of the, please.
Yeah, maybe a comment or question as well. Okay, I'm not really from the application community, but when I see, let's say, synergies and accessing the same or let's say at least similar signals from all the various sensors, we have to think about data reduction in some sense. And I mean, the geocoded SLC, especially the way NICE started now to produce it and also ship it, the importance I see is to provide the data reduction correction layers. So troposphere, ionosphere should be available consistently across the sensors so that if they are being used in a synergistic way to access a signal, whatever that signal is, at least let's say the nuisance signals, which we consider is ionosphere, troposphere, and maybe other effects, should always be part of that, so that people are really, let's say, try to attempt to really compare a signal and not, let's say, not disturbances.
Well, so maybe a quick comment. Yes, there are actually already all these layers and corrections. Of course, on the geocoded SLCs, it's a little bit harder, but on the earlier products, like the ETAD type of layers are. Across the missions, you mean?
Yeah,
like,
so even across the missions. I mean, that's the thing a bit also, let's say, which makes, let's say, also GPS, Galileo, all these kind of systems are comparable because they have a common framework of data reduction.
Yeah, that's definitely a bigger effort, but yeah, we should. I think we're going slowly.
Yes, exactly. So you already, I mean, you showed how you can form the interferograms from the geocoded SLCs, and you already have the steps of also forming, let's say, geocoded differential phase screens, and they can also simply be picked by already having the layers available in the geocoded kind of data cube or stack. And if these kind of layers are then also provided really for all the sensors there, then the whole thing really starts properly showing the signals and not just, let's say, nuisance from our perspective.
You can comment more, but Roselle is sort of going to that direction, so it's actually getting closer.
No, indeed. So for Sentinel-1, we have it separated from the product, but in the GSLC, CSLC world, this will come hopefully together as well. Nicer, we have it. Biomass, we don't, but because, well, we haven't looked into this yet. Good. Harmony will have this as well. The point is that, okay, for the model-based things, this is maybe easy. We can even attempt to have consistency. For the database corrections, then it becomes a bit more challenging, no? Because we are using split spectrum, multi-layer ionosphere correction, which are all a bit different and are providing different things. But at least trying to get that this information is provided with the products and the layers are more or less defined, no? So it's something that we can attempt at least.
Yeah, so I'm not trying to say that all have to do the same data source, right? So I mean, as we saw, the missions have different means of retrieving the different, let's say, nuisance signal, but the important bit is they are provided and they're also kind of applied then by the community that they really use them in order to show comparable results then, so that not all the time, okay, here we still have the troposphere in there, here is still the ionosphere, here is still the whatever.
Of course.
Yeah.
You don't have the ocean tidal loads, no? In the... Yeah. Okay.
You missed one. Yeah, I think so. But there's an opportunity to add it.
Maybe one of the synergies I see is the temporal axis. I mean, the sampling of NISA will be very dense, and with biomass, for products like forest disturbance, we will measure once every 9 months. And we need to understand what's going on in the middle, in the meantime. For the moment, we plan to do this with Copernicus, Sentinel-1, Sentinel-2. But an L-band sensor would provide an information which is close enough to P-band. And so the point would be, I don't know if this is possible, or can some products of NISA, could they be easily accessible from the map so that users could use them and load the information they want? I don't know if this is something that can be envisaged.
It's already, I think it's already available, yes. It's everything already accessible, and I don't think this was highlighted enough, but everything, all the nicer data are in the AWS cloud and in an cloud optimized HDF5 format. So the map, at least on the NASA side, is within the AWS cloud, so it's seamless to pull. Yes, from the ESA side, I think there has to be, what they call it, an egress cost, and so somebody needs to pay something somewhere to transfer the data. And I think that is supported, actually. If Franz is here, I'm pretty sure that ASF is able to support that payment of the transfer costs. I'm pretty sure, actually, yes. It'll be slower, perhaps, but...
That would be great, because there would be many applications for this.
May I have a
Yes,
comment?
we're going to write a recommendation about this.
I just have one question about how NISA and biomass in terms of calibration. We have a transponder in Australia and in...
Sorry, I just wanted to add that we have really applied a monitoring project to monitor huge landslides. Successfully use C-band from Sentinel-1, but many areas are completely decorrelated in C-band, and we are experimenting with L-band. First of all, ALOS, but we want to experiment as soon as possible with NISAR. And now I would like just to maybe confirm, I heard that biomass cannot acquire data over Europe.
No.
Is that true?
Yeah, this is true.
Yes, it's true. Okay.
Unfortunately.
So maybe that such synergy that C-band, L-band, P-band elsewhere might be that it penetrates deeper. And I don't know about the coherent stability between L-band and P-band in humid conditions. Can it be used, interferometry of P-band, let's say in 1 year temporal baselines? Similar like L-band?
This is an open question, I guess. In 1 year, we will know. We still haven't formed interferograms at 1 year, no?
No, because in theory our stacks are, we haven't repeated the coverage yet, no? So we are completing the one global coverage with the 7 images, and then we will have the several repeat the int phases, and then we can try to play. But this we will only know in a couple of years, no? And regarding the exclusion zone, so indeed we are not allowed to acquire over North America nor Europe, which with biomass, which then of course reduces the areas that we can use, because we are not allowed to operate there. There was still some faint hope of discussion about having some calibration sites or super sites inside those areas, where we could try still maybe to get some agreements to operate biomass. So perhaps one good thing, and this was also mentioned by Irena before, is that we work on defining what these super sites could be in terms of interest on synergies. And then at least we can try to focus the attention on some areas where maybe this could still be feasible.
And also, if we look on the mission lifetime for biomass and the acquisition strategy, so those things also exclude this kind of application that you said. So it's just mission for another purposes.
Okay, just one question about how we exploit the reflector in Australia for NISA. Is there any using, or just let it be? The transporter in Australia, which we use for calibrate biomass. What about NISA use?
What was the question, Dean?
The reflector in Australia, which we use for calibrate biomass piston.
Yes.
Yes. Do you use it for NISA or?
No, I don't.
No.
We don't. I mean, for NISA, you mean the calibration sites
Yeah, right.
that you have in Australia? Is that?
Yeah.
Yeah. So we don't. Do we have calibration sites in Australia? Probably. Okay. So we have radiometric calibration sites. And I don't think, and I'm sure there are no Australian radiometric calibration sites. There are also geophysical science calibration sites, and I don't recall if we have any geophysics related, solid earth related calibration site in Australia. But that's what we, so we have in Oklahoma and Alaska, we have the corner reflectors, and so that's where we're calibrating images radiometrically. Then we have the calibration of the science algorithms, and there are many calibration sites spread out. I know for biomass there are about 30 for the biomass map, not the biomass mission, the biomass map that NICER will generate. There are about 30 sites scattered around the world. And then other disciplines have other sites, you know, GPS. When I say discipline, I mean cryosphere or solid earth. They have GPS sites or typically GPS sites actually that they are somewhere located. So, and actually that map is online. You can consult that map.
Okay. This is about not a question about the complement between the NICER and the biomass. That's for biomass we have a land to have the products of the forest high and forest carbon, for example, biomass. What about NICER? Do you have a similar products, or is there any complement for that one?
So for biomass,
for example, forest high. Is there any plan? No.
We're not generating forest high.
Yeah. And then why not? Because this morning you try to do it.
Oh, okay. So the science goals from NICER are in the ecosystem area is biomass, basically, disturbance, crop area, and inundation, flooding. So these are the 4 products that NICER could generate. Now, there are, of course, other scientific investigation, like my personal investigation. I'm going to try to get the tree height suboptimal using temporal decorrelation, but it is not a goal of the mission.
Okay.
So it's not a project that is going to be funded by the NICER mission. It can be, but it was not designed for that, let me put it this way. Unlike the biomass mission was built to get the height, and so the baselines and all that. So NICER has a very narrow baseline. Actually, if they can make it 0, everybody would be happy.
Because we don't have the data in North America, that's why we need NICER, yeah.
I see, yeah, well, yeah.
We have product.
Yeah, we need to wait.
Yeah.
Right.
So the last one is, what are the most exciting new applications that biomass opens up to the scientific community? New applications, so...
Biodiversity. Because
biodiversity, yes.
Yeah, because usually that's where I talk a little bit with some colleagues who work on biodiversity, and usually they explore a lot with the spectrum information from optical data. And now they're very excited to explore the structure information from forest. And we are doing to work together to explore such kind of new application, biodiversity.
Biodiversity, since it passes through structure, for this reason it is new. Is that correct?
The plan because they see quite a lot with the spectral information up to now, and then they want to explore have more information from structure. I mean,
from the structure, etc.
From structure of the information from radar. Okay, we try to, how can we say, give us some more information, some indicators, some metrics from radar data for them. Biodiversity.
Okay. So then I think that one new application, one future application is about ionosphere, because biomass is hyper sensitive. So okay, there is a need to put this together with atmospheric physicists, but I think that the potential is there and it's very clear.
Yeah, the first results clearly show that biomass is very, very sensitive to the presence of water, rain, humidity, soil moisture. I mean, the water cycle was not a planned product for biomass, but it could be a very nice domain of application.
Agreed, yeah.
What about archaeology? Is this something that you ever thought about, you know?
I think this goes with the desert application, more or less.
Yeah, that's geology, but archaeology.
The techniques should be very similar.
Well, yeah, I mean, it's something that is difficult to predict. So my personal take is that if there is some like a giant structure, giant ancient structure hidden beneath the sand, they would have seen it with L-band already. So I don't expect like something spectacular, but maybe I'm wrong. Just a gut feeling.
Yeah, it'd be interesting.
But something is being done. Indeed, we received an input by a group of archaeologists, and this is being considered. So maybe I will be proven wrong.
Back in the past, some L-band data were used to discover some features, some linear features, some of very dry areas. This is why I meant it was correlated to desert. You need the way to penetrate, so it will probably not work in humid zones.
Not only sand, also in forest area.
Yep.
Oh yes.
So if you think to South America, there is a lot to discover.
Something we could discover when we estimate the DTM over specific regions below the forest. We could see some unlikely structure, and then yes, why not?
Why did we change the session?
Can you go back? Yeah.
No.
Are we late? Are we late?
Can we go back? There is the last question. Yeah.
No, well, I think that for new applications, we need to stress geology. So any further comment on this?
Yes, there is still a lot of to discover. We started to focus on this tomography data to make as much as possible out of it to measure real penetration depth and to establish the topography of bedrock surface. I still see that there is a big potential for that for many areas, many desert areas in the world. We already did some examples for Sahara Desert and also for Gobi Desert, and all of them shows very high potential. The data are not easy to process because of this very low backscatter, but I think we are step by step, slowly getting into the point.
Thanks. And
one of the outcomes of the such studies could be could address scientific questions, large scientific questions, not only related to geology, but to anthropology, to the former water cycles, and to understand history.
Yeah, exactly. Because I just personally focused on that bedrock structures. But what we saw, and what I also put on the presentation, these paleo streams. So it means all this geomorphology, how what is development of that environment before glaciation, how it looks like before the desert was formed. This is the kind of questions that we can answer with this data.
I think we're running. I think we covered some of these questions. These were additional questions that came from the current in-submission session. So we covered them, and I think we are about to end this. But yes, but maybe I'll touch on the most provocative question that I think we already talked a little bit earlier. So are the GSLC, the geocoded SLC, the future of SAR products? So I know I just wanted to point out, so working on the NISOR project, I've seen that the costs of generating products. And so often the community doesn't realize how expensive and complex is running a ground segment and then generating higher level products. And so it is possible that in the future, space agencies might just give the geocoded SLCs. That's it. No range Doppler SLCs, no interferogram, nothing. Just the geocoded SLCs to save costs and manage. I know it's a bit provocative, but I just wanted to throw that question out there for Muriel so she can complain. No.
Complain again, because okay, if you want to give the GSLC on top of the SLC, I'm fine. The problem to me, if you really want to cut the SLC, and then you have, by whatever reason, a suboptimal split spectrum or multi-squint correction, and then you don't go back, no? So
one danger could be to lose the physics. You lose the Doppler, the range, you mix it. Yeah, but
it's nice that, I was just going to say that it's nice that Sentinel-1, Next Generation, and Roselle are going to try that geocoded SLC, sounds like, right? That's the plan. That's the direction. It's an experimental mode, so we are hoping that maybe next Fringe, this community will show us whether it's a good idea or not. Right, I think.
To be fair, you have to go to the higher latitudes as well and see what's going there, and then we can do. So,
is Paul on the room, Rosen?
Not.
No, because at the last Fringe we had the same discussion, and the answer was of Paul was NISAR will demonstrate it, the GSLC.
That's right.
But NISAR hasn't demonstrated it because it's just there yet. And I think that we need maybe 1 year more and of usage of this data in a variety of use cases to understand pro and cons. And only when we'll have these pro and cons, we'll understand where it can be used and what is its limitations, I understand.
Yes, one caveat there is that the current generation of the geocoded SLC is not perfect. It can be improved. Right, exactly. So at the higher latitude, I can tell you there is not going to work very well currently, but maybe there are some additional corrections that one can apply to make it better in the future. So yeah.
Split spectrum and everything you apply globally and for all the thematic areas, or I don't know, for glaciers, these kind of things, you're doing the same kind of processing? Okay. 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 But the co-registration you do with it, but I mean in general, are you doing cross correlation or something, or? Okay. Okay. So for the geocoded SLC, you use just model. Okay. Okay.
Maybe another point in this GSLC stuff. I think that it's the first conference in many months that I haven't seen that where the AI has a strong focus. In all the AI in this conference was pretty limited. And I think that one of interests of the GSLC could be indeed AI, machine learning, and foundation models. And this is where I do see that it can bring something, because it's physics unaware, so as Laurent was mentioning. That could be the product of choice for machine learning use cases.
Perhaps we have to work together to define some use cases to see where we look at together with NISAR and in preparation for Roselle to see where we go with this. No? Coffee? Anybody would like to say something else, bringing some to discussion?
Now or never.
Yeah, it's now or coffee, no? So. Now we have the poster session, so then thank you all very much, and let's all join the poster and see the complementary research which is being shown there.